Good morning. We're going to give it another couple minutes just to let everyone log in.
Can you hear me?
Yeah, hearing you.
Great.
And your slides are visible?
Great. Looks like I'm all set to go whenever you give me the word.
Excellent. Thank you. Good morning. Welcome to the second day of the Charm Workshop for 2021. We're going to start our first session off with a talk by Dr. David Hardy, one of our longtime collaborators, giving us a update in the latest efforts in supporting heterogeneous computing. AMD is, of course, an early adopter of this technology, so it's going to be good to hear their perspective on where things are going now. Please go ahead whenever you're ready, David.
Okay, thank you, Eric. Thanks. It's my my honor to be a part of this workshop, and I am happy to be presenting our work on NAMD, our recent GPU developments. And I'll talk about some of the challenges that we're facing. So let's see. There we go. So NAMD is a parallel molecular dynamics application written in C++ with CharmMPI objects, and it runs on all major operating systems on laptops up through supercomputers, specializing in parallel scaling of large biomolecular simulations. Besides basic dynamics, it has many advanced features, including enhanced sampling methods, alchemical free energy methods, a collective variables module called Colvars, and also unique to NAMD is the ability for users to modify NAMD's behavior with TCL and Python scripting. So we have over 25,000 registered users, And maybe even a better measure of our impact on the community is that we have over 15,000 citations for our NAMD reference papers. And so we've been involved in many investigations now of the SARS-CoV-2 coronavirus. So here on the right, I'm showing you some results of a simulation on simulating the spike dynamics of the spikes of the coronavirus. So when we're doing molecular dynamics simulation, most fundamentally, we're integrating Newton's equations of motion. So we will integrate this for up to billions of time steps. And most of the computational work is involved with calculating the forces at each step. So we have a number of bonded forces that characterize the covalent bonding between atoms. And then most of the computational work of the forces is in calculating the non-bonded forces. And so these are the forces due to the van der Waals forces, which is modeled with the Lennard-Jones potential, and then the electrostatics forces. And the parallelism for MD simulation is limited to each time step. So if I take you through a computational workflow for MD, we'll initialize the particle positions, and we'll use those positions to calculate forces between the particles. And these forces are used to then update the positions. And we loop this for millions or billions of time steps with occasional output that produces these reduced quantities, energy, temperature, and pressure, or a snapshot of the trajectory where we'll output the position coordinates at a time step. And most of the computational work, maybe as much as 99% of the computational work, is involved with calculating the forces. And the rest is then due to the update of the positions. So in order to parallelize this, we are limited to just parallelizing over this force calculation. And so NAMD's approach is to use this hybrid decomposition of both data and work. And NAMD was fairly innovative in this regards. So the idea is that you have a spatial decomposition of atoms into what we call patches, these fixed volume regions in space. And then the forces that move the atoms are calculated in parallel at each step between the adjacent patches. And then we have this work decomposition of then the interactions that we call we characterize these with these compute objects, okay? And so these are the interactions between neighboring patches. And so by considering both the data and the work together, this gives us a lot more stuff to parallelize. So if you think about it in terms of this diagram on the bottom right-hand corner of your screen, and consider that center tile there, well, think of that as a patch. And then you've got these interactions between that patch and all the surrounding patches that we're characterizing by these purple diamonds. And so then if you think about this in 3 dimensions, and then you account for Newton's third law, you've got 14 of these purple diamonds for every patch that you have. So this gives us a lot more stuff to be able to parallelize and then load balance. So if we look at the data flow between time steps, then we have these, again, we're starting at the top here, where the top row denotes the patches and the atom coordinates in the patches. And so then we have this multicast operation where we're sending the atom coordinates to these compute objects. And so these will be non-bonded computes that present the majority of the work, and then bonded computes. And then after forces are calculated by these compute objects, there's a reduction operation that sums the resulting forces back into the patches. And to handle the long-range electrostatics, we use an approximation called particle mesh Ewald, or PME. And so this involves a different communication scheme that goes on in parallel with the other stuff. So there's a point-to-point communication that then is basically enabling this 3D FFT that takes us to reciprocal space, and there's a rather fast summation that's done in reciprocal space, and then there's a reverse 3D FFT to take us back to real space, where we sum the contributions of those forces. And so when we were introducing GPUs, and this was back in 2007 when CUDA was first developed, we started by offloading the largest amount of work. That was these non-bonded computes. And as GPUs became more capable, then we could move more work. We could move all of these bonded computes that don't really give us nearly as much work. But the point is that as GPUs got faster, we needed to relieve the CPUs of more and more work in order to get good performance on the hardware. And finally, on modern systems today, like the Summit supercomputer, we also offload the parts of the PME algorithm as well, the charge spreading kernel and the force interpolation kernel. We do this in a pretty clever way. We double the order of accuracy that you would normally run PME at. So instead of a fourth order accuracy calculation, we do an eighth order accuracy calculation that allows us to use twice the grid size. So we double the grid size. That reduces the entire bandwidth of the communication by a factor of 1/8. And so all of these things together allow NAMD to scale really well on not just CPU-based computers, but now on GPU-based computers as well. So here I'm showing you the scaling performance of NAMD running on Frontera and on Summit. So here I'm showing two different systems. These are both benchmark systems made from this STMV, satellite tobacco mosaic virus. It's about 1 million atoms. And so just over 1 million atoms. And so the smaller assembly of STMV into a grid of replicated grid of 5 by 2 by 2, that gives us about a 21 million atom system. The larger system in a grid of 7 by 6 by 5 replicated STMV virus systems, that gives us a 224 million atom system. So this is a way we generate synthetic benchmarks to test the scaling of NAMD. And so NAMD got to be involved in some high-profile research and simulation of the SARS-CoV-2 coronavirus just last year. This was done on both Frontera and Summit, and this was in collaboration with Romy Amaro's lab at UCSD. And the whole effort won the Gordon Bell Special Prize at SC20, and the project involved over 1 zettaflops of NAMD simulation. Although most of the simulation involved characterizing the spike proteins and the conformational sampling of this spike protein assembly, the big scaling run that we did with NAMD was the group was able to construct the viral membrane of the coronavirus with embedded spike proteins. And this whole thing became like a 305 million atom system that then we were able to run at scale across almost all of the nodes of Summit, up to 4,096 nodes of Summit. And so we were really pleased with the fact that we were able to get over 50% efficiency running this at scale. And you can also think in terms of since there are 6 GPUs per node, that's about 24,500 GPUs in total. So the whole thing was roughly 12,400 atoms per GPU. So this is quite a remarkable scaling for NAMD here. And all of this uses our original GPU offload scheme. And the idea with this scheme is to partition work between the CPU and the GPU. So we, let's see, I just lost my time clock, sorry. So in this scheme, we have the force calculation on GPUs. And so here I'm just showing the division of work between what's run on the GPU versus what's run on the CPU. And really, we don't have that much left on the CPU. Okay, it's like the integrator and rigid bond constraints, and then perhaps certain enhanced sampling methods that might be used for a given problem. And so this original GPU offload scheme was good enough until the release of Pascal in 2016. The idea that GPUs before that just weren't that fast. And the profiling back on a Maxwell system that preceded Pascal shows that the GPU is fully utilized. So the streaming forces that we do with getting the forces from the GPU computation back to the host CPUs, this really allowed good overlap of the CPU and GPU computation. However, when we started benchmarking on newer GPUs, this really started to reveal problems in how we were using the GPUs. Okay, so here we see going from Pascal to Volta, the hardware has like a 70% performance improvement, but NAMD benchmarked, NAMD back in 2018 benchmarked on this, only gave us a 20% performance improvement. And if we look at the profiling, we see why, okay? It's because we're really bottlenecked by the CPU and everything that's left on the CPU. So here you see in the plot that's done with Insight, the profiling plot done by Insight Systems here shows that the force calculation, real large gaps here in the light blue line that indicates the force calculation on the GPU. And so really, we need to utilize GPUs better. The idea is that the majority of our users are actually running system sizes that are less than 1 million atoms, and these are suitable for a single GPU. And so really this addresses the need of the majority of our users too, to develop something that's a much faster utilization or a much better utilization of GPU. So the idea is that we must transition the code then from a GPU offload scheme to GPU resident. So in a GPU resident scheme, the idea is that the data stays on the GPU, and you can do the integration there on the data as it stays on the GPU. And so if you compare my cartoon representation of timelines of the two schemes, you see then that even when we're calculating forces and streaming them back as fast as we can to the patches in order to progress to the next integration step, okay, we're still leaving gaps between how we're using how we're calculating on the GPU. And so we want to collapse all this down. And so instead of aggregating position data and copying to the GPU and streaming back, what we're doing is that we have a transition where we're taking the integration position buffers on the GPU and we're filling the position buffers for the force calculation. And so then we do a fetch of the force buffers, and we need to sum those together and convert those, okay, so we're using now a structure of arrays form on the integration part of the code. And so So this is basically how our GPU resident scheme looks. And we see then the profiling shows really no significant gaps in the timeline anymore as we're going between these integration steps now. So we've gotten rid of most of the CPU bottleneck. Okay, here I'm showing you no CPU bottleneck. It turns out that there's still some bottleneck that will become apparent later. But if we look at the results now, the performance results from this, we see that this is more than doubling our performance across a wide range of system sizes here. So here I'm looking at system sizes from this 23,000 Jack benchmark up through the 1 million atom STMV benchmark and some systems in between. And so we're using the GPU resources much better than we had been. And this is great news for us, for our users. It's even more striking when you look at how we're using GPU dense hardware, say like a DGX2 that has 16 V100s on it. And so if you compare the aggregate throughput that we can get with this new scheme versus what we're able to get with just with the NAMD offload scheme, it's a night and day comparison right here. So our goal then, once we had really good single GPU support, was to be able to support GPU dense architectures by scaling a single simulation across multiple GPUs on a single node. And the idea is that also upcoming leadership class supercomputers will also have many GPUs per node. So really doing this work helps leverage these resources that are coming. So when we adapt NAMD scalability to the GPU resident version, the idea then is that we're going to do a similar decomposition of data and work among GPUs, but now we've got to aggregate compute and patch data per thread to launch these integration and force kernels. And so we're going to maintain a single thread per GPU in the first version just to make things easier. And then we'll be exploiting the fact that these GPUs are tightly coupled, or peered GPUs. So they're connected by NVLink, or preferably NVLink, but maybe PCIe. And so the issue then is that these GPUs need to communicate information among themselves during the simulation. So what we have to do is we have to update the atom positions in each patch during the integration, and then perform a position multicast to the compute objects and compute new forces. And so here's the position multicast. And finally, it goes to the next slide. And our first version made use of the Nickel library. This is the NVIDIA Collective and Communications library, just to get things working quickly. And so the idea is that we could express these multicast and reduction operations as all reduced primitives. And this got us a first prototype of this working. The problem is that this results in wasted communication. And so it's better performance if we do the communication on our own, but I'll show you some of the performance that we were able to get here. So we were able to get some modest scaling here out of going ahead and using then Nickel for doing these communication collectives between the GPUs. And when we look at the profile, we see that the force reduction and the position multicast are taking a lot of time, a lot more time than the integration itself. And so it turns out that these are even accounting for 40% of the GPU kernel execution time when you're running out to 8 GPUs. And so what we needed to do then was replace nickel with point-to-point force sum reductions. And we tackled that first, where we were basically replacing these with the nickel communication with a specialized kernel, and so that we could only sum the pieces together that we needed to sum. And we did something similar with the multicast as well. And so these two things together gave us a lot better performance than what I showed you on the earlier slide, not quite doubling performance all the way across. And we also introduced a spin lock barrier into Charm++ as well. This helped overcome some CPU thread synchronization latency issues that we were experiencing. And we now are getting even better scaling on the DGX A100 systems. One reason for this is that this is only an 8 GPU system rather than a 16 GPU system. And so here I'm showing you some dramatic examples. The bottom red line might be what a practitioner, the parameters that a practitioner might choose. Okay, but if you decrease to an 8 angstrom cutoff, which might be which you might use with the amber force field rather than the charm force field, you can get close to doubling your performance, not quite doubling performance. And then the green line shows a much more radical treatment where we keep the 8 angstrom cutoff, but then we're using hydrogen mass repartitioning so that we can run at a 4 femtosecond time step throughout. And so we still see in that graph that we are not scaling wonderfully out to 8 GPUs. And so there are some improvements that we can do. And the big improvement is that PME is posing a bottleneck due to the way that we're calculating everything. Right now, we're assigning PME to just a single device. Now, this is because the FFTs really don't parallelize well across GPUs. But this is causing severe load imbalance for us. And so the idea is that if we were to even do something like assign just a single device exclusively to PME, we would be running a lot more effectively. And we could probably even do a better load balancing scheme. PME itself, as I showed you before, has different phases of its calculation, and the charge spreading phase and the interpolation phase is stuff that can be distributed in parallel across GPUs. And so we might exploit that as well. But ultimately, we will get better scaling performance with a scalable algorithm. And so we are looking at replacing PME with the multi-level summation algorithm. Now, we have an initial implementation of multi-level summation in NAMD, but the first version of it really doesn't treat periodicity as you would want to treat it. So it makes certain assumptions like requiring your simulation cell to be charge neutral. And we've done some research since that first implementation that has shown the correct way for MSM to be able to treat treat periodicity. And what this really makes it look like is that PME can be thought of, or MSM could, I guess, could be thought of as a generalized version of PME, where we are doing hierarchical grid calculation in real space up to a courses level grid. And on that courses level grid, then we need to do a 3D FFT then to do the remaining calculation in reciprocal space. But the idea is that now we can make this 3D FFT as small as desired. And so we're going to be looking at this for both our CPU-based and our GPU-based codes. But future improvements now to the GPU resident version, we're also bottlenecked right now with the atom migration part of the algorithm. This is where you're updating the spatial decomposition so that as atoms move, atoms will end up moving to neighboring patches. And so the atom migration part updates this spatial decomposition to get atoms assigned to their correct patch. And the problem is that this part of the code falls back to the CPU for now. And you can see in the profiling that this requires a huge amount of time to do what NAMD is doing on the CPU to do the atom migration and reload everything onto the GPU. In fact, atom migration for this example here is equal to about 48 MD steps. Now, the way we're mitigating this right now is that we're making our patches a lot bigger, and then we're only doing the atom migration as we have to. Now, NAMD's default for the CPU-based code has been 20 steps per migration. And so clearly we're not doing this here as we're running on the GPU. Okay, so this is going to take us quite a bit of work to do because there's a lot of supporting data structures that now need to be ported to the GPU. And that's why this hasn't been done so far. Now, ultimately, we want to do multi-node scaling of our GPU resident code. And so we've looked at maybe the simple case of what if we were to scale between two DGX-like nodes that and then use the RDMA hardware acceleration for the InfiniBand or switch that is connecting these things. Well, that's a really low-level approach that might be the most effective way to take care of to scale across two or just a handful of nodes. But ultimately, we're going to need Charm++ here again for our large-scale runs. And so we'll have to look at using GPU direct communication. And also load balancing, we'll need to understand GPU workloads. So another challenge we have is supporting new GPUs. So we have, we are working with people now at AMD. Josh Ramos started this process, but now Julio, who used to be a member of our NIH center, now is with AMD. And so we're working there to use Hipify to translate the CUDA to HIP. And this is really nice for us because there's no need for a direct HIP implementation. But there are some tweaks that are required in order to support the AMD GPU hardware. So they have a different SIMD vector size, it's 64 rather than 32. And we also need a workaround for the texture memory interpolation that we do on the NVIDIA GPUs. So we already have a GPU offload version available, and Julio has developed a GPU resident version, and soon we will be able to release that. We've also been working with Intel as well to support their GPUs. In this, we are porting the CUDA kernels to DPC++. And so that's done with Tareq from Intel and Jaemin Choi, who is with the PPL. And so this is a significant enough change that it's requiring its own implementation. Now, fortunately, we're assisted by a conversion tool, but there is significant modifications that are required after the conversion. And so they will be telling you more about our work in this upcoming lecture immediately following mine. Another challenge we face is feature support of the GPU resident version. So we have standard integration working, we have just a few advanced features, but we have other features that will require extensive porting to GPU. Chief among those is this collective variables module. Right now, that runs on the CPU, and it wants to run things every single time step on the CPU, okay? So going back to the CPU every single time step, that's sort of like attaching a boat anchor to the code right now. And so that's, we really need to do some careful work there to try and port what we can from Culvars to get this kind of support on our GPU code. So that concludes my talk. Thank you. And I just want to recognize sort of the larger GPU programming team we have. Julio Maya at AMD, David Clark at NVIDIA, Tareq Mollis at Intel, and then Jaemin, Choi, and John Stone, both at UIUC.
No, thank you, David. Do we have any questions regarding the talk? Yes, I have one. One of the slides where you were looking at optimizing the system, you changed the cutoff and a few of the methods. I guess is there a trade-off there in some other like accuracy or robustness?
Well, the choice of cutoff is really more of a modeling choice. I mean, the CharmM force field that NAMD is really tuned to use, it prescribes a 12 angstrom cutoff. So the parameterization is done with a 12 angstrom cutoff. The Amber force field is parameterized with something along the lines of an 8 or 9 angstrom cutoff. And so that's really more of a decision that would be based on more of a modeling decision. But it does have performance impact here. So
interesting. And I guess what would someone choose, the Amber model versus the Charm model?
Well, I think it really depends on what system you're studying and what you feel best captures the what best models what you're trying to investigate. So
all right,
so I see hands raised in the chat here.
All right, not sure why I'm not seeing that, but whichever.
So
I see Michael Norman has a question.
Oh,
yes,
yeah, please go ahead.
Yes, thank you, David. Excellent talk. I just had a question about your Ewald force calculation. You mentioned that you went from 4th order to 8th order, and there was an associated change in grid size. I wasn't sure whether the grid got bigger or smaller.
Bigger. It gets bigger so that you reduce the overall bandwidth on the communication.
You mean the spacing gets larger?
Yes, the grid spacing gets larger.
So I would say the grid gets smaller in terms of number of computations.
Yeah, okay. I was thinking in terms of the grid size being the spacing, the grid spacing. Yeah, I said that wrong.
Okay, so that's to relieve the bandwidth requirement.
Yes.
And are you still doing that with the GPU resident version?
No, we don't need to do that now. In fact, so we've got 2 different implementations of a PME even on GPUs. And so the GPU resident version uses an implementation that where all the kernels are designed to run on the GPU. And for some reason, and I'm not exactly sure why, maybe it has to do with the use of atomics or the way that the higher order methods are implemented on that particular kernel. But that's actually slower to run that way on the GPU resident version.
Okay, thank you.
Yeah.
Thank you.
So
and it looks like Kingbin.
Yeah. Hi,
Hi.
Jaemin.
Yeah. Thanks for the very interesting talk. So my question is, I want to understand why changing the nickel to the point-to-point rather than the collectives actually improve performance. Can you explain that?
Well, it's because we were, instead of doing a pure multicast with nickel, we were doing a total send of everything to all the GPUs with nickel. And so that was implemented again with a reduction operation, but it was reducing. So you had basically a big array of positions, and you have zeros everywhere that you don't have the positions you're holding. And so when you sum all the positions together, then across everybody gets, all of the positions, if that makes sense. But then you're doing a lot more work than you actually need to do.
I see. So basically you have a customized or reduced that avoid summarizing those zeros.
Well, yeah, we went ahead and basically did, something that looked more like a point-to-point multicast operation to send positions out, and again, a point-to-point reduction operation to get forces back.
Mm-hmm.
Yeah.
Another question. I guess there would be a next talk about porting to NAMD to Intel GPU. So my question is, why we actually ported on top of DPC++, or maybe have you considered like a level 0, which is kind of at the level of CUDA? I mean, it's a little bit lower level, but probably more similar to CUDA.
Well, I guess the alternative for us would have been maybe an OpenCL implementation, but again, that's something that would have been implemented in addition to our CUDA kernels, because the NVIDIA GPUs don't run OpenCL nearly as well as they run, CUDA code. OpenCL really has a lot of uglier setup code to it. So it made sense, since we were going to have to, do a complete rewrite of this, to go ahead and choose, something that would be, a higher level language rather than a lower level language. And the other nice thing about DPC++ is that Intel is positioning this to be a multi-vendor solution. And so it's a solution that, whenever the technology matures, should allow us to run across other vendors' GPUs, and also across, take advantage of SIMD that's present in CPUs as well.
Okay, yeah, I guess that makes sense. Yeah.
I see Arnold Tharrington has a question. Hi, Arnold.
Hi,
Can you hear me? Offline and
Yep.
Can you hear me?
Yeah.
Yeah.
Okay, I was wondering, does Charm++ have a capability to automatically migrate objects on a GPU? I mean, if there's a chair that was resident on a GPU, theoretically, is it looking at that, or is that something in works now? I'm just curious about that.
Not that I'm aware of, but I think the Charm++ people could answer that.
Yeah, actually,
directly.
Yeah.
Jaemin should have a talk about that.
Yeah, there's a talk this afternoon about having fully resident Charm applications on GPU systems at 4 o'clock.
Okay, that's 3 o'clock my time then. No, 5 o'clock my time then.
All right.
Okay, thanks a lot.
Yep, thank you. All right, so let's transition to our next talk, which is delivered by Jaemin Choi about his work with Tareq Malas of Intel for porting NAMD to the oneAPI.
I have lost my control here to actually be able to stop sharing my screen. Let's see.
Let me
Where
start
is it?
sharing my screen, see if that kind of kicks you out.
Okay.
Okay,
Great.
Looks like
is it
that worked.
working?
Thank you.
Sounds great. So let me start in full screen. Okay, is Tareq here? I think you
Yes.
should- Okay.
Can you hear me?
Tareq, yep.
Okay. Good morning, everyone. My name is Tareq Malas. I am an application performance engineer at Intel. Today, I'm going to speak about the work we have been doing, Jaemin and myself, in enabling NAMD to have a portable version that is efficient and works across different devices through the oneAPI. Okay, so today we have a challenge that each kind of data-centric hardware typically needs to be programmed using different languages and libraries, requiring maintaining separate code bases. In addition, inconsistent tool support across platforms means developers have to waste time learning different sets of tools. That means that developing software for each hardware platforms requires separate investment with little ability to reuse the work to target a different architecture. So Intel's solution is the oneAPI industry initiative, which delivers a unified software development environment across CPU and accelerator architectures, which provides freedom for the developer to choose the hardware that serves their needs the best. Also, without compromising performance, it allows high utilization of the used hardware. And also it provides peace of mind to the developers in that this is an open standard and it's compatible with existing programming models and languages. So talking more about oneAPI, it includes a unified language and libraries that deliver full native code performance across a range of hardware, including CPUs, GPUs, FPGAs, and AI accelerators. oneAPI is a foundational programming stack and is used to optimize middleware too, as you can see in the figure here. So in the middlewares and frameworks that sit on top here, like the TensorFlow. So here, optimized user and industry applications sit on top, some of which leverage middleware and frameworks. And here through oneAPI, there's support through Compute CPP and hipSYCL and some experimental features from Intel compiler that allow running, that's starting to allow running the oneAPI on other vendors' GPUs and hardware. So now, why are we using oneAPI why are we porting NAMD using oneAPI? So we would like to support NAMD to run efficiently on Aurora exascale supercomputer that's upcoming at Argonne National Lab. And as mentioned before, and David did cover some of this in his presentation, that using data parallel C++ provide us several advantages, as you can see listed here, and ranging from using modern programming language, which allows it's more sustainable. It has less work in less work in getting the code ported as opposed to doing it with OpenCL. And having this open source and open initiative can help us and really develop the code further. And again, the portability is one of the key factors that we have a target of making this using the same programming language based on C++ to enable efficient execution on CPUs, GPUs, FPGAs possibly. So just giving an overview of NAMD, I believe David already covered this in more details, but here we are looking at where's the time spent in general or the computations. And here we can see that when there are millions of loops for time steps, most of the work is spent doing force calculations. And in particular, the non-bounded force calculation is the time dominant or the dominant one in terms of the work that's done. So the first thing we started with was the porting the force calculation to data parallel C++. And now I'm going to hand it over to Jaemin to cover the optimizations and the work that we have been doing in porting the code.
Sure, thank you, Tareq. So let me continue the talk. So just first want to briefly mention again how Charm++ is used in this in the work with NAMD and oneAPI. So we use Charm++ to improve the level of parallelism in NAMD. So what we do is we perform decomposition of both the data and the work. So the atoms, which are the data, are decomposed into certain fixed volume patches within the system. And then the forces, which are the work that move the atoms around, are calculated in parallel at each step between the adjacent patches. And this work decomposition, as you can see on the bottom right diagram, where we decompose into compute objects that handle the interactions between the adjacent patches, creates a much greater amount of parallelization and also facilitates the measurement-based load balancing in Charm++. And Charm++ also allows us to migrate the atoms around to different adjacent patches and allows us to update the domain decomposition every certain number of cycles. And as you can see in this diagram, we are kind of offloading the computational heavy force calculations to the GPU, and that includes the bonded computes, the non-bonded computes, as well as PME. So we started off by porting the CUDA code to DPC++, since CUDA is a very stable code base that runs well on NVIDIA GPUs. So we started with NAMD 2.14 that is able to scale to large scales. And NAMD 2.14 contains about 38 source files for the CUDA implementation, which is roughly 16,000 lines, and also 8 CUDA files that contains the kernels, about 7,000 lines. And when we for example, we ported the non-bonded force terms to DPC++, which is the most computationally intensive part of the force computations, we had to port about 13 files. That includes about 7,000 lines, as well as 11 computational kernels. So I also wanted to just briefly discuss or talk about how DPC++ differs from CUDA and what DPC++ can provide. So with DPC++, the application programmer can provide what each thread in DPC++ kernel will execute in parallel as a regular C++ function, rather than a global kernel that you have to do in CUDA. And you can also use C++ exceptions to catch the errors that can occur using things like a try-catch block. And in terms of memory management and data transfers, they're all asynchronous by default in DPC++, and they're also associated, all of them, including the memory allocations and deallocations, they're all tied with a cycle queue. And in terms of the shared memory allocations that you can use in CUDA, you would have to change them to local memory accessors that need to be created before the kernels are invoked. Whereas in CUDA with shared memory, you would typically do the allocations inside the kernels themselves. And also another important feature in DPC++ is that it does not assume a certain SIMD width or the size of the warp, like the number of threads in the warp or a subgroup in oneAPI terms. So we should eventually generalize the warp-based mechanisms that are in CUDA, so that we can kind of use different SIMD widths for different hardware architectures. But maybe for like debugging purposes, if you want to enforce a certain SIMD width, you can also do that by using this required subgroup size flag in the code. And another tool that I wanted to talk about that kind of helped us greatly in this porting effort from CUDA to DPC++ is the DPC++ compatibility tool built by Intel that allows you to significantly accelerate the code development. So when we did this implementation of porting the CUDA version of NAMD to DPC++, DPCT saved us about more than 80% of the manual coding efforts, because it was able to kind of detect all the different CUDA API calls that are being made, as well as the kernel code, and convert that into DPC++. But we did have to kind of manually perform a lot of transformations to for things like warp intrinsics and atomics that are used in the kernels. And one important advantage or a feature with DPC++ and DPCT is that the tool allows you to kind of keep the original CUDA code in comments, and that will allow you to compare, the original CUDA code versus the DPC++ code that has been outputted by the tool. And this is a kind of a good source for you to practice the DPC++ syntax. And in terms of the porting strategy, how we ported NAMD from CUDA to DPC++, we used a divide and conquer strategy by using preprocessor switches to kind of decouple the different components in the CUDA code in NAMD. So this allowed us to significantly reduce the development and debugging complexity. And the separated components include the non-bonded force terms as well as the bonded force terms, and the device utilities that are used to kind of manage the device execution, as well as the particle mesh EWALT or PME phases. And DPC++ allowed us to use oneDPL, which allows you to use the standard algorithms in C++. In this case, so we were able to use the C++17 parallel sort and scan operations on the offload device. And just to dig a little bit deeper into the DPC++ offloading of the force computations, so we were able to successfully offload the DPC++ kernels of NAMD to the different hardware, Intel hardware. So this includes the Xeon CPUs, as well as the Gen 9 integrated graphics cards, and the DG1 and ATS discrete graphics cards. And we are also able to enable multi-GPU and multi-node scalability as well with DPC++. And of course, our implementation includes the DPC++ offload code management in NAMD. And that includes things like the interfacing with CharmMPI for communication and runtime system features, and performing data management, including data transfers as well as storage, and also allowing the use of multiple CPU threads to offload to multiple different DPC++ devices. And with this work, we were also able to validate different benchmarks, including ApoA1, which has about 90,000 atoms, as well as the STMV benchmark, which has roughly 1 million atoms. So offloading, I also wanted to talk a little bit about how we offloaded the particle mesh EWALT phase in NAMD with DPC++. So there are two different code paths for doing PME in NAMD. One is Jim Phillips implementation that is enabled by this PME offload flag. And the other is anti-package implementation that uses this use PME CUDA flag. So we completed porting of both of these code paths with DPC++. So again, we did the first pass with DPCT, which did a lot of automatic updates for us. And then we also did manual updates to kind of change the work level intrinsics and the atomics, as well as some of the surrounding code paths to kind of, which includes the things like creating local memory accessors. And we also replaced the QFFT calls with oneAPI FFT so that we can use this on the Intel hardware as well. And as for PME, also validated correctness on a single GPU using Gen 9 and ATS GPUs, as well as CPU offload to the Xeon processors as well. And I also wanted to mention that DPC++ improves vectorization, as it allows us to use a flexible vector width, or the size of the work in terms of the number of threads. And this allows us to kind of optimize performance better to different architectures that may work better with a different SIMD width. So what we did to enable this was to change the CUDA work level primitives to a more generalized code. to support DPC++ subgroups for different subgroup sizes, so that we can aim for efficient vector computation on different target architectures. And now with this, I'll hand it over back to Tareq to kind of wrap up the talk.
Thank you, Jaemin. So what we are next doing is, first, we are working to make sure the implementation of data parallel C++ is ready and stable. And we are planning to merge it into the public repository so that it's available for the NAMD community. Also, from as you have seen from David's talk, there's the ongoing work on preparing the GPU resident code path of NAMD and we are now working on porting this implementation to data parallel C++ so that it's available to have higher efficiency GPU resident implementation. Now, throughout this work, we are actively working on optimizing the code using Intel vTune Profiler, Intel Advisor tools to optimize NAMD and make it ready for the Aurora supercomputer GPUs and for future GPUs. And of course, at some point, we plan to experiment with NAMD data parallel C++ performance and functionality on other vendors' GPUs. Okay, next slide, please. Okay, so one interesting thing that came out of this project is that it was very challenging to port a large application and have it to work correctly. Now, in applications like NAMD, where you are dealing with large irregular arrays or large arrays of structures, and these arrays of structures are being processed through many kernels. And then it's easy when something is off, when you have logical errors, it's difficult to find where's the source of the error, because usually the code crashes really when you have a NaN or something that's really out of the limits. And for people who are working on porting applications or working on optimizing codes that they're not familiar with all the science and details, it's more difficult to debug because the ranges or the orders of the numbers are not always clear what is physically correct or not. So one thing we observed this work is that when we are doing this porting effort, we are not changing the algorithm. We are running the same algorithm, doing the same calculations to model the physics. Also, almost all of our changes are on the offload kernels or limited to the offload kernels. We are not replacing or changing the host code or the CPU code. So from this, we came with this idea where we could capture all the all the kernels inputs and outputs, all the arrays of structures, all the structures, arrays that goes into the kernels and exit the kernel and dump them to disk. Then, and this would be done on the reference implementation that we know it works correctly. Then what we do is use relative debugging and loading these files when we run the testing, the code that we are testing, and we would do element-wise comparison for each data point that enters the kernel and exits it. So with the so what we did here is we developed macros that would allow the user to capture and linearize any complex array of structures and store it to files. And these arrays of structure live on the device memory. So these macros do all the work of copying the data to the host, linearizing these arrays of structures, storing them to unique files for each occurrence or time step. And also when it comes to comparing them, the utility also does all the work of loading data from disk, copying data from the actively running GPU, and doing the relative debugging. And in this work, since we have the truncation error and we have some tolerance, we do not do exact comparison. We allow the user to set the threshold of what is an error and what is not. Now, so this tool helped us a lot throughout the development, where whenever we have an issue in the results, we would turn on this utility, and it will allow us to find the first occurrence where we have a difference in an array we know which element of the array is different and how much different it is. So we could jump in directly on that kernel, producing that data, and find debug that particular issue. And this tool has proven also helpful even within data parallel C++, where sometimes we are developing code and working on it on CPU, offloading to the CPU device, and it works. Then when we start offloading to discrete GPU device, we run into some correctness issues. And so by turning on the capture mode on the CPU run on the same code, then we would turn on the debug mode on the GPU run. And what this would allow us to compare, to have a relative debugging with fine detailed comparison between the CPU and the GPU execution of the same code. So finally, I would like to acknowledge many teams and parties for all the work that made this possible here. And with the next slide, I guess we have this concluding. So if you have any questions or comments.
All right. Thanks to our speakers. I haven't seen any hands raised yet, but I had a question about where you think the sort of current efficiency utilization is for the use of the Intel GPUs in AMD.
Can you elaborate more on your question?
So yeah, I guess how much more optimization do you think is required to actually hit the maximum utilization?
Yeah, sure. So in fact, the original GPU implementation was highly optimized for GPUs in general, and for with the concept of being aware of the SIMD units or warps. So I believe GPUs are in general have the same let's say high level behavior or characteristics. So I would expect that different GPUs would have similar performance in general, but at the end of the day, you can always go and find certain pipes or paths in certain GPUs where you can do some tweaks. But I would expect in general that the performance would be similar on different GPUs.
All right. Looks like we have a question from Phil. Go ahead, Phil.
Okay, I can read his question.
Yeah, I wanted to ask, the debugging utility you described, is that portable outside of NAMD? You know, is that just something you can like stick in a tiny library with a header and use for anything in this space?
So it's, I mean, so there has not been an effort to make the utility standalone. It's more integrated inside NAMD. I mean, first, it is available in NAMD. That will go in the public release, and I believe it's accessible through the development branch of oneAPI currently. So it's not written. I mean, there's no standalone version of it as a short answer.
But the code's available, and
yes, so it is. I mean, when we developed this, we made sure it does not impact or interfere with NAMD itself. So it is a standalone header file that can be included by any file that will use it. And it uses macros to basically, I mean, the reason for using macros was really to have a static counter inside the macro. So every time you inject a macro, it will have a counter that will increment at every time you generate a file. So you don't have to try to capture what does your application do, and I mean, how does your application track time steps? Where is the time step counter a variable? So to avoid all these issues, this utility tries to be really as independent as possible. So yeah, I believe it is possible to with moderate effort to use that utility somewhere else.
Yeah, if I remember correctly, there isn't anything like specific tied to NAMD in that header file. It should be usable by other applications as well.
Okay, thanks.
Thank you.
All right. see any further questions, but we can have breakout sessions later. So thanks to both of our speakers, and let's transition to the next talk, which will be by Kayahan Saritas of Yale and Kavitha Chandrasekar of the Parallel Programming Lab on the Scalable GW software for excited electrons using OpenAtom. Please go ahead when you're ready.
Hi, I hope you can see the slides.
Yeah, they're visible.
Good morning. This is Kayahan Saritas. I'm a postdoc at Yale University, and I will be presenting the first half of this talk about our code called OpenAtom, which is a scalable GW software for excited electrons. So a bit of background on the electronic structure calculations is that typically when we talk about a Schrödinger equation, it's primarily a many-body system, and it's a many-body problem, which means that you're trying to simulate multiple ions and electrons in a system, and you're trying to understand what their Hamiltonian looks like using the Schrödinger equation. But typically in the material science field, what people have been using is that they are basically simulating all the many-body interaction of electrons into a term called exchange correlation functional, and turning this problem into an effectively one-body problem. And here, this problem includes the kinetic energies, the ionic potentials, Hartree potential, and the exchange correlation functional, and then it can be diagonalized, and we can solve for the wave functions and the energies of the ground state of the system. And so when we look at what are the accuracies or the computational costs of performing calculations which involve different approximations to this many-body Schrödinger equation problem, so we can see that, for example, density functional theory stands around hundreds of atoms and has a computational scaling of order n cube, and being the number, the system size or the number of electrons. So it gives reasonable relative energies of the structures, and this is often what you really need in the material science community to understand what are the trends are changing from one structure to another. But there are also cases where you would need much higher accuracy, which would be around the realm of the chemical accuracy. And for those, you need to go to a more complex calculation methods, and GW is the one of them, which has a scaling of order n to the fourth and third and fourth basically. And the other drawback from the density functional theory is that we mentioned about the exchange correlation functional that's simulating the electron interactions, but there are basically a plethora of different approximations to this many-body problem, and often you might be in a position where you may not have a good guidance of what to pick, and being able to work with a method that can provide near chemical accuracies are useful in that sense. And for the GW, the method itself mainly focuses on the excitations of electronic excitations of these materials. And these are important basically to first understand whether a material is metallic, semiconducting, or insulating, basically, which is a basic materials property. And so we want to understand what are different more exotic properties of light and matter interactions, and which can be related to a lot of engineering applications such as photovoltaics, lasers, and luminescence. And from what we see in here, you have the ground state of electrons, and then you will be exciting those electrons into conduction band, and this is also an inherently a many-body problem. And from GW, when we compare the band gaps, which is the energy level between the valence and conduction band electrons, we see that the GW compares really well to the experimental band gap energy. So that's exceeding the accuracy of density functional theory. But the challenges with the GW method, which we will be talking about in the rest of the talk, are that it's memory intensive. It also requires much larger number of conduction bands, so which would be required to basically simulate the effective screening of the electron interactions. And it would, for that reason, it would require large and dense matrix multiplication, and like, it has an unfavorable scaling of order n to the fourth. But our goal is to make this software like efficient and highly scalable, and also like we will be talking about our method to reduce this scaling from order n to the fourth to n cube. So on the left is the main steps of performing a like GW calculation. And we start with the wave functions and energies that we take from a density functional theory calculation. And these are first, the wave functions are first transformed from reciprocal space to real space. And then like using the real space wave functions, we calculate the static polarizability matrix, which is shown on the right here. And so the rest of the steps I will talk about, but the main idea is to get the inverse of the dielectric matrix, which is epsilon inverse here. So the reason to use this FFTs first from reciprocal to real space and then from real space again back to reciprocal space is that our idea is to use the inverse dielectric matrix is like a property that's quite smooth in the real space, and for that reason the inverse dielectric matrix is smooth, and like for that reason you would need a very like a small R grid to perform the simulation for the static polarizability matrix, which is shown in here. So although you spend the extra effort to do the FFTs in here, but you gain some like computational you reduce your computational cost basically by like reducing the grid of the real space by transferring the calculations into the real space. But still we have order n to the fourth scaling in here, which are coming from the fact that we are multiplying the valence and conduction bands, and we have like inner products of like two like different inner products of these different states in here, so they all add up to order n to the fourth. But our way of reducing this scaling from order n to the fourth to n cube is actually like involving like different manipulations of the denominator in the polarizability calculation. So we had seen this term like where the polarizability in the real space is calculated in like this, and we have the EC minus EV, the energy of the conduction and valence band in the denominator. And so this is how we were able to get to the n to the fourth scaling. But our method of reducing this scaling can be realized using Laplace transforms, where we basically can transform the denominator into this Laplace transform and then make the EC and EV terms separable from each other. And when we have this the denominator in the separable form, then you can also able to like distribute the multiplications to the valence and conduction bands separately. And so that would basically give you that instead of a multiplication of like that comes from like having double loops in here, you're going to have like the sum of these two terms, as these are now separable, and it will effectively turn like from n to the fourth to n cube scaling in here. And so there are also some like technical issues like that must be dealt with by like, using this scheme, because not every like denominator. So in order to like represent the denominator using this Laplace transforms, like you would need, you may actually need a lot of quadrature grids to be able to like simulate different energy scales using like the same quadrature grid. But in order to prevent that, we have proposed this windowing scheme where we basically slice the valence and conduction energies into different windows, and like by using these window pairs, we are now effectively like using an offset value to the quadrature like values that we use in the e to the minus EV and EC that we like mentioned in here. And so with that result, we are able to reduce the number of quadrature points that are needed to like simulate, like they calculate the denominator in here, and that also like brings the cost of the like cost of performing these calculations as well. So the final part is like maybe as not as like the expensive as performing the polarizability calculations, but it's also like similarly expensive is to calculate the self energy. And so for the self energy, we have this term where we have the Br and R prime, which are the plasma pole residues. And if you look at like the main expression that we see in here, we have like the inner products in the denominator and the difference of energies in the denominator. So that seems very similar to the like the polarizability expression that we had seen before. So we can also apply the same like reduced scaling to this expression as well, which is the dynamic self energy here. But there's a caveat that like the denominator in here can be close to zero in like some certain cases where like in polarizability, if you have a semiconducting system, then it is guaranteed to be not zero. And so in order to be able to simulate this, like calculate these terms, we have developed the Hermite-Gauss-Laguerre quadrature, which can effectively deal with the this denominator like approaching zero, like for the points that are approaching zero. And we have some more results on like the performance and the accuracy of our like method compared to like the n to the fourth method, which is the typical way of like performing these calculations. And we had seen for the like the silicon atom, for example, we can effectively reach the same the gap energies, which is like the one metric that we can use for the accuracy of these calculations. And we are seeing that the ratio of the computation compared to the n to the fourth method is about 1/3 and 1/4. And also for the manganese oxide system. And so we had also like compared the performance of this code with respect to the other codes that are existing in the literature. And so we are seeing that the band gap error for the CTSP like W, which stands for the method that we use for the with the Gauss-Laguerre quadrature, and you're seeing that the ratio of computation and the error changes together basically, but this is a result of being able to use a different number of quadratures, and you can effectively change the accuracy of the quadrature method that you can use. And like by increasing the like accuracy that you use in the quadrature, the way you pick the quadrature grids is able to give you like more accurate results overall. So with that, I want to like transfer to Kavitha to be so that she can continue with the rest of the talk that would involve like a more recent like coding developments in the work.
Kavitha, you there?
Yeah, I'm trying to share my screen.
Okay, I'm stuck in the chair.
Can you see my screen?
It's visible now.
Okay. So yeah, I'm going to be talking about the parallel implementation for GW with Charm. Basically, we've had several stages in the GW parallel implementation with Charm, and the most recent part of what Kayahan talked about, the N-cube method, we had finished more recently. I will just go over the GW Charm implementation a little bit in detail. For the N-power 4 method, which we did initially, we had data distribution such that we had multiple char arrays. Some of them, the input vectors, the state vectors are 1D char arrays, and the P matrix, which is the most computationally intensive part of GW, is a 2D char array. In order to compute using the N-power 4 method, we typically duplicate the occupied states, which is one set of input state vectors on all the nodes, and then we broadcast unoccupied states in order to compute the F vectors on each node. And this broadcast happens in stages because there are a lot of unoccupied states, and we would run out of memory if we tried to cache them all. We also have an F cache, which we eventually reuse some of our F vectors for future sigma computation, which Kayahan was talking about. Just quickly, some pseudocode on the N-power 4 method on how it's computed is for all the unoccupied states, we do an element-wise product of the state vectors for occupied states with all the unoccupied states. This essentially results in the N-power 4 computation cost that we have. Eventually, we also do the sigma computation. The computation itself is much less compared to the P matrix, and additionally, we've also cached some of the effectors that we need in the future. So for the N-cube method, we let Kayahan talk primarily about, we have windowing, which helps us reduce the computation. And the computation does not require the element-wise product of all the occupied states with all the unoccupied states. We calculate something else called the row and row bar, which are also matrices. And in the end, P matrix is element-wise product of the row and row bar matrices. So the row and row bar matrices are primarily just products of the occupied states alone, and unoccupied, so there's no interaction between occupied and unoccupied here. So this is just a representation of, this is just a representation of computation of row and row bar using the occupied and unoccupied states and the computation of the P matrix itself. The parallel decomposition for N-cube, one of the initial ideas was to also partition the unoccupied states as before and communicate the unoccupied states to neighboring nodes as we compute one of the stages, a previous set of unoccupied states. So this is more like just to overlap the communication and computation. But in the end, we just decided to go with caching all of the unoccupied states because we only need portions of the unoccupied states on each node, depending on the tile that is there. And for the large data set that we have, this still fits with our memory requirements so far. So there's no need of partitioning. We're also caching all the unoccupied portions of the unoccupied states that we need. These are some of the results we previously had, but we did a few more reruns with all the vectorization flags enabled on the Stampede, KNL, and Skylake nodes. We saw pretty good scaling for the N-cube method. We ignore some of the setup time. That is just a one-time cost initially for all the caching of occupied and unoccupied states. So the scaling is very good, and the results are an order better than the n power 4 method. We also did this for the large data set, and we obtained good scaling for this as well. The memory requirements of this are much higher, several GB on each node. But since we are still partitioning all our state vectors and only storing portions of them, we are okay so far with all the memory requirements. So the scaling is also reasonable for the n-cube method, and compared to the n power 4 method, again, it's an order faster, and it's much easier to run on smaller node counts as opposed to the n power 4 method. Just to touch upon the parallel implementation of GW diagonalizer that we've been working on. The S matrix that is obtained after the epsilon matrix computation, which comes after the P matrix computation. We're performing diagonalization, which is again easy to do now that since we're doing this in Charm. There's interoperability with MPI that we're making use of here, since the scale-up actor teams that we use for diagonalization are part of an MPI library. We launch an MPI process per PE, and this is a work in progress, but yeah, this is the next step that we're implementing currently. We have to evaluate performance. That's all I have. Any questions?
All right, thank you to both of our speakers. Do we have any questions? I guess I have sort of one. The reduced order approach requires some selection for the windowing method. Is that relatively straightforward to determine what that should be, or is how difficult is it basically for someone to determine what a good choice would be?
Yeah, it can be determined on the fly. So you can basically tune the how many quadrature points that you're going to need based on what accuracy you need from the calculations, and that will be a single parameter to set for the quadratures, and the rest of the cost can be predetermined, and then you can determine the whole windowing scheme on the fly.
All right. Thank you. Since we're a little short on time, it's probably best to shift to the next speaker. So, Simeng and Kavitha will be presenting a talk on distributed load balancing strategies in Charm++. You can see your slides. Go ahead when you're ready. Not hearing you.
Hello? Is everything okay now? Okay.
Hearing you. Go ahead.
Okay. Hi, everyone. I'll be presenting the distributed load balancing strategy with Charm++ effort. And Kavitha will present the second half of it. We will quickly go over three major load balancing strategies: prefix, orthogonal recursive dissection, and diffusion, with the centralized and distributed implementations. And we implement those load balancing strategies with applications that are iterated, that cares about spatial locality with coordinations, and need to scale well on large nodes. Charm++ load balancing infrastructure gives us a great tool to migrate char objects in a systematic way And there are two major supporting structures that you can implement upon. The first of which is tree LB. You can configure it 2 to 4 levels of the tree structure. To my own interest, I will demonstrate the 2-level structure. Let's see, we have a chart array of sets 10 locating on 4 different PEs. With the infrastructure, we will collect data to a root PE, and on that root PE, we will run the strategies to make migration decisions and ask the PEs to execute those migrations. And for this 2-level structure, I may use the term central LB interchangeably. The second supporting structure is distributed LB, which is relatively new, and for some of the old projects, you may not try with the distributed LB, and I hope my experience and Kavitha's experience can provide some help. So for the distributed LB, since there's no data communication at the initialization step among PEs, the initialization will be very fast, and each PE will make its own individual decisions on the migrations. I'll be presenting the prefix-based load balancing with the project Paratree, which I work for. And if you want to know more about the Paratree project, which is an embedded simulation project, you can refer to the workshop yesterday by Joseph. So let's first see the comparison of the centralized and distributed implementation of prefix. All the experiments I will be presenting today are done on the STEMP2 cluster using the SKX nodes, and on each node there will be 48 cores. So at a first glance, we kind of have the impression that the distributed LB scales a lot better than the centralized version. To better analysis the runtime, let me decompose the LB time into 3 stages. The first stage is the initialization time, where the infrastructure will help us to collect object-related data, for example, like measured runtime of entry method or the communication graph. And then the second stage is the strategy time, where the load balancing infrastructure will execute our strategy and figure out migration decisions. And then at the end, the PEs will execute the migrations. For the initialization step, this graph shows the runtime of the initialization stage alone, scaling from 1 node to 128 node. And with 128 node, we have like more than 6K cores. And we can see that the distributed LB has very good scaling at the initialization step because there's no communication needed. But for the prefix LB, since we cannot reduce the reduction to collect the data, so we have to pay penalty for that. So this may be an alert, like if you're targeting at great scalability with large nodes, you may consider the distributed LB. We now move to the strategy time analysis. For the centralized version, we need the sorting algorithm and place the object to the expected PE, comparing the current position with the average. And for the distributed version, we can use the recursive doubling technique, which imposes a runtime of log P to figure out the prefix and then make decisions on each PE at the same time. So the distributed version scales a lot better than the centralized implementation. At the end, we can see that for the migration time, it's highly related to the number of objects that need to be migrated. And with the same strategy, it's roughly the same. There's not a big difference. So as a quick summary for this experiment, we can see that for the centralized LB, it may perform very well with smaller number of nodes, but then the penalty of reduction, the penalty of reductions for the initialization and some inefficiency of the strategy runtime may occur. And next, I want to present the ORB-based LB. For the orthogonal recursive bisection LB, our goal is to partition the universe into number of PE blocks with even measured loads. And for the centralized algorithm, we can use selection to find a splitting coordinate along the longest dimension of subspace. And for the distributed algorithm, let's define one partition to be all the effort that's needed to find a splitting coordinate. And to do so, let's look at an example. We have a P array of 8 objects, and we will assign a leader PE for this round of partition. It will broadcast subspace boundary coordinates to all the PEs, and all the PEs will reduce a histogram banding of object loads that's within this subspace. And once this data is collected at the leader PE can check if the optimal bin splitter satisfies the tolerance we define. And if yes, then we successfully partition this universe into 2 halves. If no, we can zoom onto the optimal bin and reduce the search space by a factor of bin size and repeat the process. However, we may repeat too many times, and for each time we need to do broadcast, reduction, and go through objects, which can be very costly. So we made a small improvement that if the optimal bin has less than threshold object, we can just simply collect coordinates of those objects directly and do the split at the leader PE. To find number of PE partitions, and we're trying to do it as parallel as possible with this distributed infrastructure. The strategy I came up with is to do it by round. So for the first round, we only know the bounding box of the whole universe, and we assign one leader, which is P0 at this time, to make a split to divide the universe into halves. And once we have the bounding box of 2 sub-universe, we can assign 2 leader PEs and doing their own solutions. And in this case, we need 3 rounds to successfully create enough partitions for this case. Because we have concurrent broadcast and reduction at the same time at different rounds, we need to make multiple reductions with different routes. This functionality is currently not well supported by CharmMPI++. We do have a solution called sections, but it's not bug-free at this moment. So what the strategy I came up with is to have a dynamic mapping between PEs, PE index, and the root, so that the communication pattern forms a spanning tree. And I will show the animation of how this can be done. So basically, this animation shows 2 reduction paths that can be executed concurrently. And since they have different root and due to the mapping algorithm from the senders to the receivers, I will avoid exploring the critical path. Now I want to show the strategy time for the ORB, both the centralized version and the distributed version. Unfortunately, my algorithm has a pretty bad runtime for the distributed version. And as you can see, it does not scale very well with increasing node, and adds up all factors together. The centralized version actually win in terms of scalability. As a quick summary, I present an analysis of the LB runtime with a three-stage composition. And I think the rule of thumb would be that you should try to implement a distributed LB version of your strategy if the runtime is less than the initialization cost of the centralized version. You can also compare the strategy runtime as well. And for the distributed ORB, I do have the plan to improve it. For example, like I won't recursive to the PE level, but instead recursive to the node level to reduce the amount of communications. And once we recursive to the node level, we can use the diffusion algorithm to balance objects on each node. And now let me hand over to Kavitha.
Okay, thank you, Simeng. So I am also talking about a distributed LB, but this is a slightly different implementation. It is a diffusion LB. Sorry. In this case, the strategy performs diffusion with neighboring nodes. And for each, instead of PEs, primarily because we're focusing on reducing the communication. So for each iteration within the diffusion, the neighboring nodes exchange load values. And the idea is that the overloaded neighbors would send load tokens to the underloaded neighbors. And this kind of diffusion is done only within the neighbors. And this is done for multiple iterations till the load reaches a threshold into average load value. And at the end of this, we perform the actual load balancing, and this is the step where we, or migration, where we also incorporate communication graph, primarily trying to minimize the external communication while migrating the objects. And once before we do the actual migration, we do intranode load balancing of the tokens using a centralized strategy. We have an implementation of greedy and also for prefix-based within node load balancing strategy. In order to compute neighboring topology, we're working on multiple ways to do this. One would be to directly map probably the application communication graph to the node topology graph. But one way to do this that we currently have an implementation is to find for the application the k highest communicating neighbors. And then we consider neighbors to be symmetric, and therefore we can have at most 2k neighbors. And then these neighbors are currently just logical nodes. We don't have a mapping to the topology, and selecting such highest communicating neighbors could result in a disconnected graph. So we also do connected components computation to make sure that there's no disconnect between the nodes. This is just an example of how the load is diffused across nodes. So we have overloaded nodes in the center and the underloaded in the outside of this graph. So the overloaded nodes tend to diffuse loads in iterations to their neighbors, and those neighbors in return would diffuse their load across iterations to other neighbors till we reach almost average load on all the nodes. In order to, after the load tokens are passed, like I mentioned, in order to do the communication aware part of this, is primarily trying to find the objects to migrate to other nodes. We try to select the object that has maximum external communication. We look through the COM graph to find this. We have a heap of objects based on their communication, external communication bytes. In addition, we also make sure that this external in addition to the external communication for an object, we also make sure that it has maximum external communication to the destination node that we're trying to send the object to. This is an example experimental run, just a small scale run on Stampede 2, where the strategy time for diffusion LB is somewhat comparable. Diffusion LB is comparable distributed, but that just depends on the number of iterations. If we have a lot more diffusion iterations, it could be much higher. For a small number of nodes, this was comparable, and we find that diffusion LB has almost close to the lowest number of external communication bytes after the LB is done for the the communication bytes primarily for the application itself. Greedy, as we might expect, has the worst because we do not have a defined strategy. It results in the objects having a lot more communication. Diffusion LB tends to be closer to defined, but it's still much lower because it takes the actual communication graph into account before migrations. That's all I have on diffusion strategy. I can take any questions.
All right, thank you. Phil had a comment where they have some relevant work over in the VT implementation. Very histogram data structure. He has a link in the chat. But as we are running really short on time, and it's probably worth starting our break now so we can pick back up at 11.
Tareq, I wanted to make one comment, and then if there is urgent questions, then we can take just one or two for a minute. The comment was, I think Kavitha's, if it is not clear, the idea is that you would use some graph partitioner or ORB to do the main load balancing. Then after that, every case step, the next several load balancing steps, you will just do this diffusion load balancing. So it's a refinement strategy, but it depends on original being reasonably coherent partitioning of the graph. That's one. And the second point is, it may or may not have been clear, but the only migrations of objects that happen are from a node to a neighboring node. Neighbor, of course, in this topology. Right, Kavitha? Even though the tokens might travel, but the objects go only to the immediate neighbor.
Yeah, we have a graph of, we have a list of neighbors for each node that we compute initially, and the diffusion only happens across to the neighbors. It does not go beyond.
Right. And the fixed point computation with tokens is happening at every load balancing step. Previous versions of a diffusion type balancer that we had in Charm were actually saying, well, we'll just balance among the neighbors, and eventually after many steps of load balancing, things might be okay. Here, this is one step of load balancing where we're reaching a fixed point computation. That's an important distinction to keep in mind. Okay. And we're hoping for many applications, this crop of distributed balancers will be eventually very useful with all kinds of optimizations and so on. Okay. If there are no urgent questions, then we'll indeed take a break for 6 minutes, and we'll start our keynote talk by Alex Aiken on time.
All right, thank you to our speakers, and yeah, back at 11.
We are in a break, in case you're wondering why we are so quiet.
I figured that was the case. Should I go ahead and share my screen? Are we ready to?
Oh, yeah, share your screen that way, at least. Yeah, that way. Sure, we'll wait for maybe a minute afterwards.
Yeah, no problem.
Yeah, oh, that's working. All right. Welcome you all to the second keynote of the workshop. I'm pleased to welcome Alex Aiken, whom we have been trying to get for many years to come to Champaign for our workshop. And in the end, we ended up doing it virtually, so we got to get him physically sometime in future. Alex Aiken is a professor of computer science, Alcatel-Lucent professor of computer science at Stanford. He got his degree in computer science and music from Bowling Green State University, then his PhD from Cornell in '88. Then he was at IBM Almaden Research Center, which I think is where I might have run into him, but I'm forgetting that now. But I remember his research on the race conditions in parallel computing, because for non-deterministic programming models, that was an important thing for us. He was a professor at Berkeley, and then joined Stanford in 2003. His research interests are in programming languages, and is an ACM fellow, recipient of ACM SIGPLAN Programming Language Achievement Award and Phi Beta Kappa Teaching Award. And is also former chair of the Stanford Computer Science Department. He's chosen for the talk today a very interesting and provocative topic, which is of great interest to me and probably everyone here in this community, which is about the parallel programming culture. Years ago, I remember reading a blog where someone compared the rate of turnover in programming languages in the broad programming community versus in HPC. And now that the broad community within quote is starting to do HPC, what's happening to these two cultures? So Alex, without further ado.
Well, thank you very much for the kind introduction, and it's a real pleasure to be able to speak here. I appreciate the invitation. I thought I would talk today about these two cultures and what future trends might imply, from some observations about them, and then what that might mean for doing research. So, on the one side, as was said in the intro, you have the HPC community, where the dominant paradigm is to program in a combination of MPI, OpenMP, and now also CUDA. And on the other side, you have this big data and machine learning community, which I'll just refer to as the big data community, sweeping in all the machine learning work, as well. Where you have tools like Hadoop and MapReduce, Spark, TensorFlow, and PyTorch. And you might ask, okay, is there any relationship between these two communities? I mean, is there actually some interaction or maybe some tension between them and the way they develop software? So we have two examples of large scale, high performance software development, or at least using very large machines in these two communities. And what's different and what's the same? So there probably is some overlap. I mean, there actually is definitely some overlap, but it's kind of hard to judge how much it is. And there's clearly a lot of stuff that's either on one side completely or the other. And the other, immediate observation to make just from the start is that, these aren't the same size communities either. All right. So the big data community is huge, being commercially supported and incentivized by profit. The HPC community, while there is a commercial side to it, is much, much smaller. All right, and the big data community is growing, at a rate arguably quite a bit faster than the HPC community. So, keeping those two things in mind, that there is some overlap and that one of these communities is much larger than the other. You might ask, okay, is there going to be convergence? Will there be increasing overlap? Maybe the big data community is going to eventually absorb the HPC community. And the stage is set for this, all right? Because if you look at the underlying hardware platform that these two communities use, it has been convergent, all right? And now it is almost the same. There's a couple of differences that are still notable. And I'll say more about this shortly, but if you're building on the same hardware, then you would expect your software tools to share a lot of commonalities, and then the economics of software where there's no need to duplicate things and there's no interest in building two things that do exactly the same thing, would start to take over, and you would start to see a real convergence and coming together of the two communities. Well, so then you might ask, if they're thinking about long-term convergence, what are the barriers? I mean, so what's going to keep these communities apart, or at least slow down the rate of convergence? Because maybe there's interesting problems there to work on. And I think one way to frame this is to think about their priorities. I mean, so when people go to write software in the HPC community versus in the big data community, I mean, what are they trying to do? Okay, what are they trying to accomplish? So if I think about the priorities for the HPC community, I would rate them as performance is number one, all right? And then productivity. So people care about, being able to produce the software as quickly as possible, provided they can get all the performance they want. And then correctness is kind of down the list, all right? And I don't mean that pejoratively, I just mean that, making sure the code works. You're willing to do crazy things for performance that might make it more difficult to reason about correctness. Okay, so performance definitely sticks out. You're not going to compromise on performance just because you might be uncertain of the correctness of your code. And then in the big data community, I think the priorities are basically the same, just in a different order. All right, so they actually care about the same things. These are the three most important things for the big data community, but productivity is on top. All right, they care most about how quickly the human beings can produce the software and how productively they can use the software. Performance, they want as much performance as they can get without sacrificing productivity. All right, and then correctness. It's everybody wants their software to work, but you will if you have a more productive interface that maybe is it allows people most of the time to write things correctly. But in certain situations might cause them some problems, but overall it's more productive, then they'll go for that. All right, so that's the sense in which productivity is a higher priority than correctness. And I think if most people I've talked to kind of agree with this view, I'd be interested to hear about other views. I see a comment in there, that scientists and engineers and analysts care a lot more about correctness than computer scientists. I think that is true. But you have to be a little careful about what you mean by correctness. So the scientists, engineers, things like that, they definitely care about not getting the wrong answer. Okay, that is definitely true. But if the software crashes occasionally, all right, it doesn't produce an answer, and then you can rerun it, and it will work and give you the right answer. And none of the other software does better than that. Okay, like it's not 100% reliable, but it doesn't generally produce the wrong answer. The scientists, engineers will still go with the best thing that's available. All right, so we can. So let me see. Yeah, it's really just optimizing time to solution under different conditions. Yeah, I don't know if that's true. I mean, at least in the HPC research community and the DOE community, I think performance is a goal in itself. I mean, people evaluate themselves on the performance of their codes. And so, like, if two people are working on the same problem, often the measure of goodness is, this code is more performant than that one. So I guess it is time to solution in the sense that I can finish my run more quickly than you can finish your run, even if it took me much, much longer to write the code. So in that sense, yes, it is time to solution with just a different metric for how you measure that, where the endpoint is. Okay, I guess also where the starting point is when you start measuring the time to the solution. All right, so these two differences in attitudes, I think, create, obviously are going to create differences in platform performance and programmer productivity. Okay, but they also create differences in the scale of the computations people do. And so I think, the HPC community, for example, does generally much, much larger scale computations than the big data community. And also in the economic model. Okay, so and there, as I just alluded to, what you see in the HPC community that seems to be very strong cultural traits, that people are willing to spend enormous amounts of time writing software to get a bit more performance. Okay, and that is just not the way the big data world works. Once it's good enough or at least tolerable for performance, they're done. Okay, they're not going to spend any more time making it better. All right, so coming back to this question about overlap. Another way to kind of get at an answer to this question is to think about who would switch. Right? Like if I wanted big data people to switch to using HPC tools, would they do that? And would HPC people switch to using big data tools? And I think it's fair to say, based on my conversations at least, with people who work in the commercial world using kind of data analytics and machine learning tools, that the percentage of people who would switch from big data tools to HPC tools is approximately 0%. All right. The HPC tools just don't address their problems. Okay. But also they just don't have the skills to use these tools. All right. They're not going to learn to program an MPI. They're not going to learn to write OpenMP and CUDA directly. Okay. These are just, they're just living in a different world. And the HPC world is really inaccessible to them, I think. At least the standard HPC tools are inaccessible to them. Thinking about the other direction, who would switch from using HPC tools to the big data tools? Well, if the performance improved by switching, everybody would switch. Okay, because performance, I think, is if you had the same, if you could get the performance they want and have the kind of the productivity that the big data tools provide, then I think there'd be no question everybody would switch. If the performance were at least comparable or not overly harmed, some would switch, but some would not. All right, and if the performance was 10x worse, then nobody's going to switch. Okay, so people aren't going to accept a 10x hit. And I think there are a lot of people in the community, in the HPC community, who wouldn't even accept a 2x hit. All right, partly because of the nature of the very, very large scale computations they do, and 2x could be a lot of time. All right, if you have a computation that runs for weeks and then it turns out that now it has to run for months. And to put some actual quantitative numbers on it, here's a chart, all right, that I think gets at actually quantifying the difference in the performance of the different tools. So this is some work that we did last year comparing 15 parallel distributed computing systems, from both big data, from both kind of machine learning, big data community and the HPC community, on a variety of workloads. And let me explain. I'm just going to take a minute to explain what this chart is saying. Okay, so so this is for a particular application. It's a particular kind of, this particular computation pattern, just a simple stencil. Okay, so we're just measuring the time to compute a very small simple stencil pattern, nothing else. And then on the y-axis is something called minimum effective task granularity. All right, and the idea here is that this is the amount of time you have to spend in the computation in the units of compute that you do between communications. All right, so if you have chunks of computation that run for seconds, and then you do a bunch of communication, and then you go back to doing a bunch of computation that runs for seconds, you can hide a lot of runtime system overhead, in a system like that. Your runtime system, the actual, implementation of the infrastructure on which you're running, doesn't have to be very efficient if it doesn't have to engage very often, and you're mostly spending time in application code. All right. As that granularity comes down, as you start to communicate more frequently, have to move data around more frequently, and your language or runtime system implementation has to become engaged more often, and you're spending less smaller blocks of time in the application between those moments when you transfer control to the runtime system, then you start to notice overheads in those systems. Right. So what this is measuring is the point at which, for this particular pattern, a system achieves 50% efficiency. You're spending 50% of your time in the application code, and 50% of your time in the infrastructure code. All right, and you can see that down here, like MPI really does well. All right, I'll also point out that Charm++ does very well on this chart. Okay, so Charm++ is generally just a little bit above MPI. And you can see here, this is a log scale on the y-axis. I want to point that out. All right, and so the difference between things like MPI and Charm++, if the minimum task granularity that they can support is something like 5 orders of magnitude smaller than what the big data systems like Dask, TensorFlow. Actually, TensorFlow is kind of here, so it's not quite as bad as some of the others. But it's still orders of magnitude higher, and then you have things like Swift and Dask up there at the top. Okay, and Spark is at the very top one and didn't scale past 2 nodes for this particular pattern. All right, so this really shows just the huge range, of what of implementation techniques and kind of overheads that these 2 different communities are willing to tolerate. And I'll just say these other lines in between here are things like the task-based systems that I'm interested in, but also other combinations of things. Another thing I'll just point out, which is kind of interesting, and this is not really quite relevant to my talk, is that you can see that as your machine gets larger, the minimum effective task granularity goes up for all the systems. All right, and so as the diameter of the machine gets bigger, and the speed of light starts to impact how long it takes to send messages across the machine, and no system can really achieve much better than about 100 microseconds minimum task granularity. Here's another one for a more complicated pattern. All right, and so this one has a lot more task parallelism in it. And you can see the story is a little more mixed here at the bottom, but it's basically still the same set of systems that are performing reasonably well. And it's the same set of systems up here at the top that are different. And not all the systems are measured here just because some of them just ran for so long that we couldn't run the benchmarks. Okay, so just digressing for a moment about the hardware. The hardware platform drives the software abstractions. Okay, I'm a real believer that the hardware, that the reason we have the programming systems we do is because they reflect important properties of the underlying hardware. And the current slow motion revolution, the one that's taking a decade or more to play out, is the rise of accelerators in HPC hardware platforms. Okay, so we have GPUs today, and other specialized hardware like FPGAs is already starting to appear, and presumably we'll have more specialized processors in the future. And in new supercomputers, 95% of the performance is in the accelerators, and this has been true for a while. So every DOE machine, for example, since Titan, and all the future machines are accelerator based, and way north of 95% of the flops in the exascale machines, Frontier and Aurora, will be in the accelerators. Okay, and the trade-off here is that this greatly complicates programming. Okay, the nodes with GPUs on them are actually pretty complicated to program. Each node is now a distributed system of its own, but switching to the GPUs can greatly increase performance. And I think this is the ground where the convergence will happen. I mean, this is kind of the standard platform, at least for the next decade. And so, the kind of hardware constraints will shape how the programming systems work and whether these two communities come together. All right. So, trying to put some nuance on the kind of blunt statements I made earlier about the value on performance in the HPC community. Yeah, so the HPC community values performance until it gets to be too hard. All right. And the truth is, if you look at HPC systems out there today, what they actually do, many of them actually don't perform very well. And the number one reason is they don't actually take advantage of the accelerators. They're still CPU-based codes. And it's just too hard to go and do all the software engineering with the existing HPC tools to move them over. The switching cost is so high that they just end up, kind of locked in, at least currently, to a situation where they don't take advantage of most of the performance on the standard platform. And while the big data community values productivity, that's only until the code turns out to take forever to run. Okay, and organizations do spend inordinate amounts of time tweaking for performance. So another way of thinking about it is that they have these priorities, they have these cultures where they kind of start out on a path where they're going to focus first or use tools that give them an advantage in one dimension, and then they're going to spend time trying to get back what they can in the other dimension. So they're willing to pay a cost on the back end after they already have the software and they see how it's working, to try to, do as well as they can in their other priority areas. And sometimes this doesn't work out so well. Sometimes, even groups that highly value performance wind up with codes that really by most standards, by any objective standard, aren't very performant on existing platforms. Or you wind up in a situation where, even though you thought you're using a productive platform, the performance is such that you spend a huge amount of time trying to do workarounds, through very opaque tools where you don't really have much control over the performance. So, coming back to the hardware platforms for just a moment, I mean, the main limiter, I think, in current and future systems is data movement. It's by far the most expensive part of any computation, especially as you scale up. And adding accelerators just makes this worse because it adds more levels to the memory hierarchy. And so it complicates the data movement picture quite a bit and also introduces capacity constraints where you actually have to worry about whether things are going to fit in the smallest levels of the hierarchy. And mostly we don't have programming abstractions today in standard tools for things like locality, how you're going to partition data, for this world, and how having flexibility in how the computation and data are placed in the machine. All right, so these are things that I care about, but I think it's generally true that most of the programming models either hide this in heuristics in the runtime system that you don't have control over. That's kind of standard for the highly productive or the big data kinds of systems, or you kind of have limited interfaces for doing any of these things. Okay. Yeah. So what's the evidence for that? I'm just looking in the chat here to see if there were questions that I should answer. I think I'll leave those for the end. Okay. So the evidence for this is, first of all, some things that I've worked on. S3D is an application that we worked on and showed that it was 7x off its potential. An HPC code that could be dramatically improved by taking better advantage of accelerators. Same thing with large graph analytics. So the CPU-based state-of-the-art was basically 10x off its potential. And then machine learning, so some work that showed that we could actually scale standard machine learning workloads, and make them run quite a bit faster for training, at least, than standard tools. Okay. And so, this was through a combination of switching to GPUs and doing, more intelligent data partitioning and then and placement of the data and computation. So now I'm going to switch gears and talk about a little bit about where productivity comes from and how that might, and what we could do. And I think most of us are probably more on the HPC side than the big data side. So I'll probably focus a little more on HPC kinds of things now. And I think productivity comes from libraries ultimately. So the ability to write libraries is really key. And if you think about just how many widely used parallel libraries there are for HPC versus say how many widely used libraries there are for an ecosystem like Python, it's night and day. All right, so Python is really designed to encourage people to write reusable libraries that become and for people to build further abstractions on top of those libraries. A lot of HPC codes, there are widely used libraries, things like BLAS, and some other packages that are popular. But for the most part, a lot of HPC code is written from scratch each time somebody writes an application. All right, and that's limiting for productivity. So let me say a few words about NumPy. A very popular big data Python package, for mostly dense array computing. So I'm going to assume that most people know what NumPy is. It's a very common building block in other Python packages. So it's used in lots of other popular, particularly machine learning libraries, and it has a lot of drop-in replacements for one GPU. Okay, so there's been some effort to accelerate NumPy on GPUs, and since it provides kind of a nice high-level array processing abstraction, you can work at replacing each of those, implementing the NumPy interface on GPUs. Okay, so the things are up at the level of matrix multiply and other operations of kind of that granularity, and so you can easily imagine providing a NumPy implementation that runs on GPUs. And to use NumPy, you just say, import NumPy in your code. All right, so this is not my work, but this is some work from NVIDIA on doing the same thing for just parallel and distributed computing. All right, so Legate NumPy is a drop-in replacement that will take NumPy programs written in Python and run them on either on your laptop on a single GPU up to things like Summit. All right, and it's only one line change. So this is an effort to really have exactly the same interface that NumPy provides to programmers in Python. So there's no other changes other than just importing the library. Okay, the different implementation. And so here's a simple example of using this. Here's a Jacobi solver, which is like 7 or 8 lines of code in NumPy, and here it is scaling out to 256 GPUs. And you can see the weak scaling is not amazing, but again, for the amount of work that you did, it's not horrible. And you get you run on GPUs with basically no effort. All right. And you can compare the CPU and GPU scaling here, and then of course here's the NumPy line here, just with the normal implementations. Okay. And so just the size of the matrix here that you're using, it spans a vast range. Okay, from even the smallest matrix here is not that small, but the biggest matrices here are really huge that you're solving. So, so the way Legate NumPy works is that it takes, it's a dynamic system. So, as you're calling NumPy operations, those are getting fed into some interface that's going to partition the data, turn those into units of computation called tasks that get launched on the system. And then there's a bunch of logic to decide how to distribute those units of computation and the data around the various GPUs and memories of the system. This is fed into a runtime called Legion that I've worked on, and I've given talks at Illinois about in the past. So this is a task-based runtime that works at exactly this level of abstraction of taking in tasks and collections of data and then figuring out how to map them, and instructions actually on how to map them and sending it down to the machine. So, and so what Legion actually does under the hood is it computes a task graph. All right, so it figures out the dependencies between these tasks as they're coming in from the application. And then the mapper logic, the logic that says how to distribute the tasks around the machine, then assigns the tasks to CPUs and GPUs as instructed in a way that's consistent with the partial order given by the dependencies. Right. So at a very high level, that's what how the implementation of Legate AMPI works. So so to manage the data in this system, each of the ND arrays in NumPy is mapped onto what's called a logical region in Legion, and that's Legion's collection data type. It's just the way of describing large multi-dimensional arrays or similar kinds of things. And you'll have different logical regions for different shapes. All right. So for example, in this particular code, you have a region with an index space that's two-dimensional. All right. And so this A matrix will get mapped to such a n by n region. The B vector here will be mapped to a column, just a one-dimensional index space. And as you dynamically run through this program and the program encounters new objects that are being allocated, they just get allocated dynamically in these region data structures. Okay, so we'll have some 1D objects and we'll have some 2D objects. These are all allocated and partitioned and distributed, online as the system runs. All right. Okay, so let me show you some performance comparisons. With Dask, which is the other system that is a Python-based kind of task-based system, out of the big data community. Dask has a slightly different interface for handling work. You have to actually, the programmer actually has to make some changes to their program to say how the data is partitioned. This is handled automatically in Legate. All right, but other than this chunking, they're equivalent systems. You have to do a little more work in Dask because the programmer can either say that something should be chunked automatically or give the chunking themselves. And whereas in Legate, it really is just a one-line change to import a different library. Okay, and so I'm going to show you some plots here, and this was run on a cluster of DGX boxes, and we're only looking at weak scaling. So here's the Jacobi solver. All right, so you have the Legate line up here. You can see the CuPy point here. CuPy is a single GPU solution, so you can see that it's about the same as the Legate and CuPy kind of match on one GPU, and then CuPy doesn't have a distributed backend, so of course there are no other numbers for that. This is the GPU line up here. This is the Legate CPU line here, the red one, and then these are the Dask lines down here. And you can see that there's issues in these systems in kind of maintaining good scalability because of the metadata that has to be exchanged between the different nodes, to kind of keep the runtime system synchronized on its own coordination among all the different nodes. So Dask has some issues with that, but also it just has higher overheads, as we saw in that slide much earlier on task granularity. Fundamentally, Dask just can't support small tasks as a system like Legion. So the difference here on CPUs is about 10x, and the difference on GPU, the difference with the GPU code is about 100x. So Black-Scholes, this is a embarrassingly parallel application. We expect perfect weak scaling, which we see here with the Legate lines. You can see that Dask actually has some optimizations that Legate doesn't have. In particular, it does some task fusion, so it starts out a little better because it's able to increase the granularity of the tasks internally to a point where it's more efficient, but then starts to drop off. And the two Dask lines here are the blue one is the one where Dask does the partitioning of the data itself, and the pink ones are the ones where programmers gone in and tried to figure out the best partitioning possible. Another picture that tells the same story is a more complicated one with a preconditioned conjugated gradient solver. All right, so this is, so you get the idea. Okay, and I don't think I need to the story on this slide is much the same as the previous slides. Okay, so this is one approach to writing libraries. All right, and if I was going to characterize it quickly, I would say it's to implement important big data libraries using HPC techniques. So one way we can kind of answer the question, or get at the question of, could we have the same productivity? Could we be more like the big data community, is to take the interfaces that they have and see if we can implement them using HPC technology. And can we get more performance that way? But then by definition, since we're playing the same interfaces, we're providing the same productivity to end programmers. All right, so Legate is one example of this approach. FlexFlow, which is a replacement for TensorFlow and PyTorch, is another example. So this is a excuse me, a system for deep learning and particularly for training that takes advantage of more flexible partitioning and then computation and data placement to find better ways of implementing deep models than, say, PyTorch and TensorFlow can do. Okay, so there was a question about whether I will define, this a while ago now, I will define potential. And so I guess I'm not going to, and I see that was a while ago, so I apologize for missing that question in the chat earlier. Okay, so what are the important features here? One is, I think what are the features that you need in order to kind of get at how you could take kind of HPC techniques and implement approaches that are used or library interfaces that are used a lot in the big data community. Well, one I think that seemed to be very important is expressive data partitioning. So being able to slice and dice the data in lots of different ways. That was key in both of the projects that I mentioned. And then once you have decided how you're going to chop up your computation, chop up your data, plus also chopping up your computation, then the ability to tune how those are mapped into the machine. So how you're assigning tasks to processors and data to memory. That was another very important place where there was advantage to be had. Something else that seemed important was runtime decision making. So a lot of these big data systems are pretty dynamic. They're not static compilation approaches, and so in order to handle the kind of dynamic control flow and dynamic decision that's made in systems like Python programs, you need to have a dynamic approach. I think it'd be very difficult to do some of these things in fully statically compiled systems. And Legion is pretty extreme. So the runtime system I was talking about, Legion, is pretty extreme in all three of these dimensions. So it has these things in spades. So a really expressive, elaborate data partitioning system, a very dynamic and expressive system for mapping and making other kinds of runtime decisions. And I guess you can say these couple of examples show that, okay, this is sufficient. So we can show that there's more performance to be gained with the same interfaces, but it's not really clear whether it's necessary. Okay, so maybe simpler approaches could get the same effect. Okay? And I just don't know the answer to whether that's possible. Okay, that's one approach to kind of thinking about how we could build libraries, or how we could evaluate and get at the differences between the libraries in HPC and libraries in, say, the big data community. So another approach is just to demonstrate the ability to build general libraries for HPC applications, okay, and that will compete with the best of class HPC implementations, but are more productive to write or use. All right, and this would hopefully get at what the important novel problems are in building HPC libraries. So let me tell you about one example there of work that I'm interested in and have been working on recently. And I'll come back to what I think the novel issues are at the end. But let me just describe this problem and how we're trying to tackle it. So we're interested in implementing distributed tensor algebra. So if you have a tensor algebra expression, so something that looks like this, where you're doing some computations over large and multi-dimensional tensors, we're going to need to figure out how to partition the data and spread it out across the machine, and then we're also going to need to do the same thing with the computation. All right, so decide how to in conjunction with the data distribution, figure out how to distribute the computation as well. And this is joint work with Rohan Yadav and Fred Kjolstad, who I think many of you probably know. And so we're naturally using the Taco system here to do some of this work. And the goal here is just to compile tensor algebra kernels into efficient distributed implementations. And I'll show you the notion of productivity that we get. Actually, the notion of productivity is that we want programs that look like this. Okay, so like 20 lines of code. And I'll just quickly go through here. So here's the for example, this line here. That's for the source of the arrow is how you implement or express that tensor algebra expression. So this is pretty much just a transliteration from the math. For the data distribution, you describe how to chop up the data with a few lines of code like this, and I won't take the time to explain what it does. I'll show some examples as we go along. And then you have a schedule, okay? And the computation distribution says something about how you distribute the data and the computation across the machine. All right, and I'll say just a few words about that as well. All right, but this is typically these are the size of programs we're writing, like 10 to 20 lines of code. So we're going to model machines in this approach as hyper-rectangular grids of processors, okay, where each processor has some local memory. And we'll pick a structure for the machine that looks like the target computations. So then to distribute data, we're going to talk about how to map the dimensions of the tensor onto a given machine, where the machine is described as one of these hyperrectangles. All right, so we'll write things that look like this, where we say some dimensions of the tensor are mapped onto certain dimensions of the machine. Okay, so we're going to give names to the dimensions of the tensor and the machine, and then where the names match, that's going to tell us something about how the tensor is mapped. And let me just show some pictures. So it's probably easiest just to give the idea with pictures. So if I have a one-dimensional tensor mapped onto a one-dimensional machine, so the ith dimension of the tensor is mapped onto the ith dimension of the machine, that just means I'm going to chunk up the tensor in that dimension into the same number to match the number of processors in the machine. All right, so I will divide the tensor in chunks to match the number of processors in that dimension of the machine. If I say I'm going to map if I do this mapping, all right, what this says is, okay, I'm going to map the ith dimension, to the ith dimension of the machine, but I'm also going to take all the j elements and associate them in that same mapping. So that means that translates into mapping all the rows of the tensor into the machine. If I do it in 2 dimensions, then I get a tiled distribution of the tensor. All right. If I have a 3-dimensional tensor and I map it onto a 2-dimensional machine, then I'm getting pencils of the tensor are mapped onto chunks in 2D space of the machine. And now 2 other operations I can do. I can if I use the star here, that says I want to replicate the tensor in a given dimension. So here I'm partitioning the tensor in a tiled fashion, okay, in 2 dimensions. And then I'm replicating that along the third dimension. So copies of this same data are made in all all along the third dimension of the machine. But maybe I don't want to replicate it everywhere. Maybe I just want to map this 2D layout of the tensor onto just a face of a three-dimensional machine. So I can do that by just indicating 0 in one of the dimensions. Okay, so then only one copy of the data is mapped here, and the rest of the machine doesn't receive any copies of the data. All right, so this is just an expressive way. I mean, so you can get an idea of the kinds of things you can say, and I have some fairly expressive way of talking about how data is partitioned in the tensor and then how it's placed in the machine and also potentially replicated in the machine if needed. Okay, and so then for scheduling, tensor algebra naturally defines the iteration space given by the quantifiers that are in the tensor algebra expressions. And so scheduling commands are going to map the iteration space implied by this expression and into a timeline of the machine. Okay, and so we're going to apply scheduling commands to the computation. This is very similar to halide with the notion of a schedule there. You can do things like interchange the loops. Decide which processors will receive certain points in the iteration space. And we had a few new commands for distributed computation. Okay, so one is to distribute, that kind of distributes out the iteration space across the processors. Communicate is a way of hoisting communication. So if you have multiple small communications being done, you can kind of hoist that with communicate into a single collective communication. And then rotate is a way of handling systolic computation. So making sure that different parts of the computation don't all compete for the same data at the same time. So you can, if you have a bunch of processors are all executing a loop, for example, each one is executing a different copy of the loop, then offsetting where they start in the iteration space can reduce the amount of contention. All right, so that's just, there is a bunch of scheduling commands, again, very similar to halide if you're familiar with that reorder the points in the iteration space and manipulate and combine the communication to give you an efficient computation schedule. So what can you do with this? Well, so here are just a bunch of well-known matrix multiply algorithms, distributed matrix multiply algorithms. They're all expressible in this language of partitioning tensors and distributing and partitioning and distributing computation. So here's the full schedule for each one of these. In the right-hand side, the data distributions are given in this column, just to show you that these specifications are short. And then the description of the machine, how the machine is organized, or described as a multi-dimensional rectangle of processors. Okay, and then a little diagram here that gives you an idea of the communication pattern in these different algorithms. So some experiments to give you an idea of how this works in comparison with standard implementations or standalone implementations of these things. So here's on this particular machine, which is Lassen. Here are the number of nodes down at the bottom. It's, scaling by a factor of 2. Gigaflops on the y-axis. This black line is peak performance. Okay, so this is theoretical peak. And Cosma is the current world champion kind of custom algorithm. All right, and so we've taken the Cosma implementation as kind of a reference. You can see it almost meets the peak. And then all the other lines are variants of the classic distributed matrix multiply algorithm, distributed matrix multiply algorithms implemented in distal, all right, and then benchmarked on these systems. And you can see there's a couple of different classes here. So actually some of these are very close to Cosma, in particular the Cannon's algorithm performs quite well at scale. This kind of sawtooth pattern some of the algorithms are known to only perform well when you have a square matrix. All right, and so if your matrices have a shape other than n by n, then they suffer some performance loss. And so these, with this kind of weak scaling plot, these are the points where they're kind of hitting the ideal matrix shape. All right, and then the ones below are the ones where they're not. And GPU, the story is actually a little bit more interesting in that there's a bigger drop. Okay, so all these numbers way up here are in one GPU, and as soon as you start to go to 2 or to even go to multiple nodes, you see, you take a big hit. All right, and that's just because that's where you start to communicate. And you can see that the actual who's on top varies more here, and Cosma is not uniformly the winner anymore. Some of our implementations actually hit points above Cosma at various points in this plot. Some other pictures here are this is a comparison with the only other general tensor algebra library that's out there, CTF. And you can see that we're, there's one example here where there's some optimization that CTF is missing, and so we really do much better. But mostly we're a factor of 2 to 4 better, and this is just to show that we're competitive with the best implementations that are available for tensor algebra. And then there's no GPU implementation for tensor algebra, no competing GPU implementation for general tensor algebra. And so here are just some plots of weak scaling for various tensor algebra expressions. And this one down here in the lower right corner in particular shows that we still have some work to do. Okay, so this one really should weak scale well, and we've got a performance issue in the runtime system, in the underlying runtime system, that's causing this to drop off more quickly than it should. Okay, so what are the lessons from this approach to writing HPC libraries? Well, again, I think expressive partitioning of the data, at least reasonably expressive partitioning of the data, the computation, and control over the mapping of these things into the machine, these are all critical. All right, so you really want some way to describe that and to have a lot of to basically these ways of dividing up work and data just give you more options when you go to actually map it into the machine. All right. I would say that the key, what this taught me anyway, and this is something I didn't emphasize in the presentation, so this is a new thought. One of the things that's really different about writing parallel and distributed libraries is that you want libraries that are polymorphic in the data distribution. So to be a general library, you don't want it to have a fixed notion of where the data is going to live when the library starts. I mean, it really should be able to adapt to where the client is going to provide the data, and then also whoever's going to consume the data at the end, they should put the data there rather than in some generic place. And if you look at the way a lot of libraries are written today in the HPC world, at least the ones that are widely used, they tend to fix the location of the inputs and outputs, and which causes you to do extra copies. So when you call the library first has to copy the data from wherever it is to where the library, where the library's code expects the data to be placed, and then at the end you have to copy the data back out to wherever the consumer of the results expects the data to be. And that, of course, introduces synchronization and a lot of extra cost. And having libraries that are polymorphic in the placement of the data, both for the inputs and the outputs, seems like a key difference with kind of distributed parallel libraries and other kinds of libraries. So to summarize, I think the HPC and big data worlds have kind of converged at the hardware level, at least. So you have these parallel accelerated distributed machines The remaining differences are mostly in the networking. So the HPC people are willing to pay for much more expensive networks currently than the big data people, but that's actually also changing. The big data people are starting to put more high performance networks in their machines. Can we have both productivity and performance? So can we get the kind of interfaces that the big data people like with the kind of performance that the HPC people generally go for? And I think, you know, my feeling is that, you know, cautiously optimistic. There's some preliminary evidence that we can do that. And I think, you know, one way to approach it is through libraries that are built on top of HPC programming models that just provide more performance than the big data systems can provide. But I think it's still a lot of open questions here because libraries generally require a degree of flexibility beyond non-library code. And we're not that used to that in the HPC world. We tend to fix everything in place and not kind of provide the kind of polymorphism I just talked about, for example, which would really be needed, you know, to have libraries that were really flexible, you know, for different clients. Okay. So with that, I will stop and take questions.
All right, very interesting talk. Thank you. Questions? I have several of mine, but I should be polite. Tom?
A very interesting talk. I was wondering how, right, your data placement directives can deal with the multiple, you know, the hierarchy of memory layout that you mentioned. You know, for example, you know, cache lines in CPUs, or, you know, global versus whatever core specific memory in GPUs. Can you have that kind of expressivity as well?
Yeah, so I didn't talk about this, but data partitioning in all the systems I talked about can be hierarchical. And so it can match the kind, you know, you can choose to partition things to match the hierarchy of the machine if you want that level of control. You know, clearly, and we often do this. I mean, in the work that I've seen, I mean, that I've participated in, we often do, we'll have like one level of data partitioning for the node and then another data level of partitioning, say, for each GPU within the node. You know, for things like cache blocking, of course, that's managed by the hardware. You don't have direct control, but still, as is well known, you know, the partitioning can still be useful there because the kind of, you know, organizing the code, you know, down to that granularity around something that the hardware will then exploit, you know, can also give you added performance. So the short answer is yes, through hierarchical partitioning.
Steve Lemetta has a question. Do you want to ask, or do you just want to have Alex read?
Let's see.
I mean, I can read it too.
Yeah, so I think polymorphism, you know, should help you with the performance. It shouldn't cost you. I mean, you know, avoiding those copies and the extra data movement, you know, the extra synchronization.
Yeah, so
library should help, but
right, overall it's a win. But if you compile for the particular distribution you have, then you're going to get something slightly better, right? I'm wondering if, you know, what is that slightly better?
Yeah, right. So I think, yeah. So maybe the question, maybe this is in your question. So I would say I would put the emphasis in your question on this, you know, the value of the dynamic decision making. You know, so, you know, how much do you gain by making decisions at runtime when you have more information versus how much do you lose by having that overhead? All right, and I think that's very much open. I mean, there are certainly cases where having a fully static compiled approach is going to win over any dynamic approach. I mean, if things are really unchanging and there's a and global knowledge of the communication pattern, for example, can give you insight into how to do things better, static compilation approaches are going to be better. All right. The one thing I can say about, I mean, I've certainly found that dynamic decision making. I'm a static guy. I came up in the compiler community, and I believe in, you know, in compilers. But I've gotten, you know, hard experience has taught me that you have to have a lot of dynamic decision making in practical systems. If you're going to just work with other people's code and interoperate, you have to have a dynamic story as well. Okay, so ideally you'd have both, and you could decide
Right,
which one to
right.
use. From an engineering point of view, the dynamic one is the must-have.
Thanks.
Other questions? I have, oh, Simeng, go ahead.
Yeah. Hi, Professor. How do you think about the effort made by like MPI to provide the Python interface? And actually for Charm++, we have a Python interface called PyCharm as well, where we provide like plainer user interface, and it will convert to a real Charm++ program underneath, and the user can kind of like write fewer lines of code and have less syntactic concerns for writing the code while kind of enjoying the Charm++ support for free. How do you think about this approach?
I think that's a great approach, and I think that is. I think that's really the path forward for a lot of things. I mean, I think there is an opportunity, out there, because the big data models have shown that there are people who really, need to use supercomputer-like facilities, but don't have the skills, to write for those hardware platforms, and those people mostly know Python. And so providing them with easy on-ramps to use those larger scale hardware resources is a good thing for the world, and also I think leads to interesting problems. I think the key, if I was going to just say, I think the key question there is going to be, okay, is that going to interoperate well with all the other Python stuff that they want to use? All right, and that I think is the challenge, is how you kind of can you really make it composable in the way that the Python community expects. Sorry, Sanjay, you had a question.
Right. I was going to say, I think that a couple of connected points. One is your point about this machine, the second part of the abstractions you pick, where the machine was a three-dimensional brick, set of bricks. One of the problems with that is you sometimes restrict the number of nodes you would use to be a certain sets of numbers. And the only point I want to make is that the Charm++ idea there may be useful at the back end to virtualize this notion of bricks to be a virtual brick, so that they can be put onto 73 nodes if you want that.
Yeah. I think that's absolutely right. I mean, that's something that Charm++ I think showed, quite conclusively that was a good
And then
idea.
the question that that's following up from Simeng's point is that, and in fact, it's a question that I've been wanting to ask, is that it seems to be two contrasting things. One is a general purpose, like a legate approach, where you can develop all kinds of abstractions within that. And the other one is well before Berkeley started talking about dwarves, people in the community knew there are only about half a dozen different parallel data structures that we need to deal with, and trees and unstructured meshes, structured meshes, and so on. And we make frameworks for each one of them. And those frameworks may be written in assembly for all you care, but they can be composed as long as they're composable. And this compositionality is also very important from the point of view of parallel composition, but that's another tangent that I won't go on. What do you think about that, as opposed to legate, which is a high-level general purpose notation, versus specialized libraries that can be composed in an application?
Yeah, so I think as you said, I mean, first of all, I think the compositionality is the most important thing. All right, so the fact that that you have a model where the libraries can interoperate together seamlessly, meaning that you can do the kinds of global optimizations across libraries that you want to do. Things like how you partition the data, how you stage the communication. Provided that you have that kind of compositionality, then I think the approach of I think it's also inevitable that you're right, that there are going to be certain patterns that are used over and over again, and there are not going to be too many of those. All right, and then people are going to invest a lot of effort in writing libraries for those. I mean, you see this with databases, right? So relational algebra is one of those patterns that, and graphs are another example of such a pattern. Right? But there's still a long tail of stuff that people want to do that's customized. And so I think it's more of a distribution where there's a handful of things rapidly declining in importance that get a lot of investment. And as you said, they could be written any way you want. I mean, it doesn't really matter what's behind the hood, provided that they compose well at the user level. But then, especially in the HPC community, there are going to be, kind of custom things, right? So it doesn't quite fit the graph model that you've got because it's a slightly different kind of graph, and people are going to want to be able to do that. So having some facility where people can still, use the generic building blocks, but then add their own code, to do whatever the custom pieces they need for their particular application. I think, we still need all of that. I'm over time, so I need to stop. But thank you very much for the talk and the questions. I hate to cut it off, but I have to go.
Yeah, thank you very much, and I'm sure we will have other occasions to discuss and follow up from this.
I would love to, and if anybody has questions, you can feel free to send me an email. I'd be happy to continue the conversation.
Yeah, thanks.
Okay. Bye-bye.
Bye then. All right, we go for our lunch break now, right, Jaemin? And we reconvene. I haven't looked at the schedule, but I believe at 1 o'clock like yesterday.
Yes, we'll go to lunch break and come back at 1 p.m. Central.
Right.
All right, welcome back. We're still figuring out some technical issues, so we'll start the next session in 2 minutes. All right, so looks like it's going to work. So welcome to the next session. The session will be about adaptive MPI or AMPI. We're going to have 2 talks in this session. The first one will be by Evan Ramos, who's part of CharmWorks, and he will talk about CharmMPI from research code to production workhorse.
Can everyone hear me?
Yes.
Okay, sounds good. So yes, thanks for the introduction. My name is Evan, and I work at CharmWorks as a software engineer. And my talk today is about CharmMPI. So to give the very basic overview of what CharmMPI is, I'm going to assume everyone here knows what Charm++ is and what MPI is. But basically, what we're doing here is we take MPI ranks, which are usually OS processes, and we are running them as user-level threads that coexist within an OS process. And what this allows us to do is get some within-node communication that is both low latency and high bandwidth. And there's the added benefit of idle ranks that can yield to other ranks that have work to do. So that's a big benefit. How do we do this? We allocate each rank's call stack at a deterministic location. And because of that, all of the different nodes on a job can have the same open space available for each rank to move in as they need. And these can then migrate or even checkpoint to disk. Then we can use Charm functionality to measure the time that each rank spends and redistribute them around the job in order to balance the load and decrease the total runtime of your job compared to conventional MPI. And here you can see a diagram of what this, it's called virtualization or over decomposition, and how we co-locate multiple ranks within one process. So this is what it does. How do we do that? Well, it's a Charm++ program, and the ULTs are chars. These user-level threading is provided by a library we call UF-context, and it uses some pieces of assembly from boost context underneath, which is highly portable and highly performant. Then we have our special memory allocator called isomalloc that provides the deterministic memory positioning. We allocate call stacks manually as part of the CharmMPI startup procedure. And any heap operations that your code does at runtime, like malloc or operator new, are intercepted and run through isomalloc. So everything stays packaged up and can move around as a unit. Of course, there's one thing I'm leaving out here. What else is part of a program state? And that is global variables. So one persistent problem that, or a challenge that faces potential users of CharmMPI who have existing codes is that these global variables, there's no simple way to package them up and migrate them like the heap or the call stack. So here's a piece of code, you may have seen this before, that demonstrates what the problem is. And in a conventional MPI program, this will work just fine. But if multiple MPI ranks are co-located in one process, then this rank global variable will get clobbered, and who knows what will be printed by this statement it will be non-deterministic, who knows. Fixing this problem is time-consuming and difficult. Ultimately, it is the most portable way, but it would be preferable if there was some automatic way that the code could handle this for you. So for this talk, I'm going to skip some of the methods that are now deprecated and are dead ends in certain functionality and focus on what's good, so we can then get to all the improvements that we've made since, since I've begun working for CharmWorks. So here is TLS globals, and it involves swapping the segment pointer of thread local storage, and you tag all the global variables in your code, their declaration and definition, but fortunately not all the accesses throughout the implementation with the thread local tag. And then all of those are bunched up into a group by the system and the compiler, just as normal. And we can read the size and location of where this data is stored and swap out the pointer at runtime with a constant context switch, a constant time context switch that does not involve any system calls or any such overhead. And this method is well supported on systems that are commonly used for HPC tasks. On the other hand, you do still have to change your code to some extent. You have to open the file and add these tags. It's just not as intensive as getting rid of the globals manually can be otherwise. We also have a tool based on CLang and libtooling that promises to add these tags automatically. And the support is well tested on Intel machines, and we have support in progress for ARM and for Power. Of course, as I said, this method does still have some manual intervention required. So a more recent technique we've debuted just as of last year is called Pi globals. And this stands for Position Independent Executable Runtime Relocation. What we do is our tool chain will build your MPI program as a PIE shared object. This is very common. It may even be the default on many Linux builds nowadays because it allows for moving the binary around in memory. So it runs at a different location each time, and that can be very important for security purposes. So we take this functionality, make sure everything happens as PIE, and then CharmMPI will open this shared object dynamically. It will walk the header of the binary in ELF format. Currently, we use a glibc API to do this. And we find where all of the program segments are located in memory. And these PIE objects have the nice property that their global variables are always located in a certain position relative to the code, the machine code instructions, the text segment, as it may also be called. So we take all of this data, we duplicate it for each virtualized rank using our isomalloc memory allocator. And we have to do two more steps. We have to update there's a table of basically function pointers, and we need to change them for each rank so they point to the correct location for that rank. And then we have to find where the entry point is and call in. But once we do that, all the global variables in a program become privatized and migratable, and we didn't have to change anything to the code, which is a very helpful thing. So we introduced this technique at last year's Charm workshop, and since then we have made advancements. For one thing, we've refactored the initialization procedure so that the reading in of the shared object and the calculation of where everything goes only happens once. And that turns out to be very important when running in SMP mode or with pthreads, because otherwise you will get seg faults inside glibc that are not very debuggable. But we just avoid that entirely, and it makes everything very stable and reliable. We also combine this technique with TLS globals. For one thing, it goes for, or it serves to benefit the turnkey nature that we're going for. So if someone has an MPI code and for whatever reason they have thread local in their source code already, then this way it will just work, which is really important. And it can also show up when a code is linking to libraries built on the system. Like even glibc itself or gfortran has thread local data in it, and making sure everything goes as a unit is very important. We've also added some rank tracking infrastructure to AMPI's CHARM implementation. This is a group for those of you who have worked with this system aspect of CHARM that closely. This was done by my colleague Sam, who's up next. And we found this to be necessary because of the way user-defined reductions work with CharmMPI and with Charm++, because the function pointers differ by each rank. So you need to know what ranks are present in order to dispatch the reduction properly. We've also validated PyGlobals on ARM and Power, which is great. It just worked. We're very happy about that. And functionality is now merged to the main branch and can be activated with the PyGlobals command line parameter. So here are some examples of codes that we have run with PyGlobals. These include Minighost and Neckbone. Neckbone is a proxy app for NEC 5000. We've also run MFEM and Logos. Those are good because among these 4 codes represent C, C++, and Fortran, and each of these have some idiosyncrasies that we managed to handle correctly. And we've also continued a collaboration with a major ISV on their finite element analysis code. On the other hand, there are some codes that still pose us some challenges. You may remember these 2 from my talk last year. And the visual aids for explaining what's going on got messy, so I'll just try to explain what's going on. OpenFOAM is a very big code. There are lots of source files. It builds lots of shared objects. It pulls in plenty of other dependencies, I think like Scotch and Metis and so on. It also uses C++ features extensively, including having global variables that are C++ objects that have constructors that run as soon as we call DL open. And these constructors themselves initialize objects with virtual functions, which contain function pointers in their vtable. And they also read in file data from disk during startup. And this poses a problem due to the way that we handle relocations of the function pointers, the PLT, procedure lookup table, and things go wrong. And this is, OpenFOAM is probably going to be the white whale of getting this to work. And once it works, we'll be on very solid ground. MPI for Pi is an interesting case because it does some unique things. Well, for one thing, it uses the Python shared object to run. And it, one of the APIs that glibc provides is called DLM open. And basically, it just lets you open a shared object in a namespace so that it only sees symbols or functions and variables in itself, in its own namespace. And we absolutely would need to use that API to get MPI for Pi to work, because it itself calls DL open whenever you run an import statement in Python code. And we can't support that easily, if at all, during runtime after PyGlobals has been completely initialized. So what we would need to do is first call DL open of any modules that the Python programmer wants to import during the node level startup sequence. And then we would need to intercept those DL open calls during runtime and basically stub them out. We could check that everything has been loaded already, and if so, just return, or if not, error out and say, we need to do this startup procedure differently. In addition to that, the Python interface for modules exposes a lot of APIs used by pthreads, including spinning up new threads and using thread local storage dynamically. So we would need to write custom handling for that as well. So let me shift gears a bit and get to the part of the talk that more closely aligns with the title. So here's some history of CharmMPI. It began as a research effort named Adaptive MPI at the Parallel Programming Laboratory at the University of Illinois around 2001. And that work has continued until the present with more focused effort starting up in 2014. Now, we at CharmWorks got a Department of Energy SBIR grant in 2017 that has since concluded in this year. And as part of that effort, we made the program more robust, compliant to standards, and improved its performance, as well as its reliability and usability. So I joined CharmWorks in 2017, and around that time, these are some of the things that you needed to do in order to use AMPI. As the user of an existing MPI code, you had to go through all of these hurdles, these obstacles, in order to get it to work. First, you had to open up your build system, find wherever it called MPI-CC or GCC or so on, and replace that with the full path to our AMPI-CC. You had to handle any global variables that were present, as I've talked about. You had to change the entry point because the Charm++ runtime system needs to start up before we start your program, and that involved these steps here, including our MPI header before main. That added a preprocessor redirection for that symbol so we could call it later and it wouldn't interfere. Something similar with Fortran renamed the program statement to this particular subroutine. Additionally, you also had to remember some specific invocations when building and running your program. For example, one of our killer features is migration and load balancing, but you had to add these commands, module, our common LBs, and lincoln isomalloc in order for all of that to work. And that's just another thing the user would have to remember. Similarly, they would also have to pass this isomalloc sync feature and disable address space layout randomization so that all of the special things we do with locating code in deterministic ways work correctly across multiple hosts. And then, of course, they had to learn how to use our CharmRun process launcher, which has its own way of doing things. But this is what it was like in 2017. And since then, we've made significant progress. Just the goal of what we've been going for has been to have less to explain, less to remember, and fewer barriers to entry for anyone who wants to use our code. And we do want people in industry to be interested in this and hopefully support us commercially. So now our toolchain wrappers will automatically handle linking in everything they need. ISOmalloc sync is on by default. The implementation of that is cleaned up. That's why it was not enabled by default previously. You can export one environment variable and sort of activate AMPI, kind of like module load or something like that, so that you don't have to edit your build system anymore. You can just set that variable and build as AMPI in the new environment. We've added another way to pass flags in to AMPI CC so that you don't have to edit anything. It's very simple. With our PyGlobals method, you don't even have to change the entry point anymore. We can just check for main, and that works for C and C++. And surprisingly, it works for Fortran too, which is a very happy finding. We've also added an argument to CharmRun plus N that works more like the NP option of MPI run. So all of these improvements have culminated into a document we wrote called the CharmMPI onboarding tutorial, which is now available for users to look at, and they can get CharmMPI running on their own. Let's see, I have just 5 minutes, so let me go through this very quickly. We've also made things more portable. They work better. We've rewritten some things so that it's more streamlined and covers all the bases that it needs to, made things easier to use. And let's see, we've also made it improve performance, again, as I've said previously. So this is my final slide. Just as a case study, here's a success story we've had running lamps on CharmMPI. It's a very clean and portable code base, so props to them for that. As part of getting this working, they recognized that they had this issue where they were tokenizing strings using this C library function that has some hidden global state, and they replaced that in their own code with some custom parsing. We provided them a patch to fix one remaining issue with that, and with that all in place, we were able to successfully virtualize ranks of lamps. There was one remaining issue, and that was when we migrated, some of the file handles they were stale after migrating. So what we do to fix that is we intercept and proxy the file APIs like fopen and fclose, similar to how we intercept malloc, and we record that state in the AMPI rank and migrate that with everything else and reopen things on the destination so it all looks the same on the other end, and the program can just continue. So that's my talk for today about CharmMPI, and I'm glad to take any questions now.
Thanks, Evan. Do we have any questions?
Yes.
Tom?
So does the isomalloc, are there any performance issues with that? So should classic Charm applications like Changa turn off the isosync malloc, which is now on by default?
So you could. There is a small cost at that. Isomalloc sync involves a global broadcast and a global reduction. So if you want every last drop of startup time to be cleaned up, then you could disable that, and we could add something that will disable that by default. But other than that, it's not going to get in the way of your code.
Yeah, I'm familiar with the startup. I was just wondering if there's, after startup, are there performance issues?
After startup, if you're not using it, there's nothing.
Thank you.
And we have another question by Jaemin.
Yes. So I just have a comment on to share the file handle. Have you considered there's a new Linux kernel called the PID-FD, and you can basically pass the FD, just send directly to the other side, and then you can open it, and then you have a duplicate of that file, exactly the same. So basically, two processes are sharing the same file.
Okay, that sounds useful for, like for within one host, if there are multiple processes, they can share that handle.
Yeah.
Okay. Yeah, we can keep that in mind. I guess that still leaves the issue of migrating across nodes.
Right. Wait.
Do you mean even across nodes?
I think PID-FD works only inside a node.
No, PID-FD is used for referring to a process itself in place of a PID. It's not useful for actual file I/O.
What do you mean by not?
PID-FD gives you a file descriptor that references a process, the equivalent of /proc/1.
Well, you use a PID to authenticate, but you get a duplicate of the same file, exactly the same file.
It doesn't get you the file handles that the process
You get
has.
the file handle by calling PID-FD open with your own PID as an authenticator. So basically that gives you the security that nobody else can open or open the file. It's a security thing. Yeah, but anyway, it probably doesn't work across the nodes, but it works inside the nodes.
We will look at that. And I think there are
They're only available after Linux 5.6.
Okay. Yeah, there are definitely opportunities for sharing file descriptors between processes.
Right. Okay.
All right, I think we are right on time for the next talk. The next talk will be by Sam White, who's a PhD student at PPL. And he will talk about communication optimizations for adaptive MPI.
Okay, can you see my screen?
Yes.
And is that advancing?
It's advancing, yeah.
Okay. Okay, thanks. My name is Sam White, and I'm a PhD student in PPL, and today I'll be talking about communication optimizations for adaptive MPI. So this is more on the research side of things, hence the usage of AMPI as compared to CharmMPI. I'm going to give a quick introduction to AMPI. Evan covered most of this, so it'll be quick and mostly for posterity. And then I'll get into talking about two different communication optimizations that I've been working on recently. One for point-to-point communication and another for collective communications. AMPI, sort of the motivation behind it is that variability in different forms is difficult to address in traditional bulk synchronous programming models, and test-based programming models can address these issues much more efficiently and with greater ease of use. But having to rewrite existing codes to these test-based programming models can be difficult and require a lot of developer effort. So rather than rewrite these codes, we prefer to have a method of sort of re-implementing the programming API that they're already built to in order to convert them to run on top of our test-based runtime. So that's how AMPI works, is we virtualize the concept of an MPI rank and execute those as user-level threads. Many of these virtual ranks can share the same address space, as Evan discussed, and this allows us to do various things such as overlapping computation from one rank with the communication of another rank on the same core, You can migrate these ranks around for load balancing, etc. Evan discussed the drawback to this. The primary drawback is that you have to privatize the global and static variables in your code so that you don't run into correctness issues when, after you virtualize, all of these ranks in the same address space suddenly share the same copy of those variables. The benefits are over decomposition, asynchrony, and migratability, as has been discussed throughout the workshop. And this allows you to achieve dynamic load balancing and fault tolerance as well as different communication optimizations. We can take a quick look at an application running on AMPI. This is Lulesh 2.0. On the top, we see a run without over decomposition or load balancing. And you can see here the purple bars represent time spent in all reduce. And you can see there's a lot of imbalance here across the different cores. And that results in a lot of idle time spent inside of the all reduce call. After over decomposing and running with load balancing, we show a single PE at the bottom with 8 different ranks on it. And you can see that the execution of the various ranks on that PE are able to overlap their communication effectively with one another. Evan talked a bit about isomalloc. It's kind of the thing that really makes AMPI easier to use for existing applications. With Charm++, you have to write PUP routines or serialization routines for all of your data structures. With AMPI, we have this memory allocator that allocates your memory transparently into migratable code segments. And so this enables dynamic load balancing and fault tolerance with very little development effort needed. The same idea of virtualization or over decomposition enables different communication optimizations inside of AMPI. We have these multiple ranks that share the same PE, and that affords us the ability to optimize for PE local transfers. So in this figure, if rank 0 sent a message to rank 3, we can take advantage of the fact that they're both co-located on the same rank and only one of them can be running at a time to optimize that transfer. And then you also have many different ranks inside the same OS process or address space. So if rank 0 were to send a message to rank 62 in this figure, that transfer can all be done in user space shared memory, as compared to normal MPI implementations, which would have to use a inter-process copy mechanism in order to optimize that sort of transfer between ranks on different cores in the same node. In past work, I've shown optimizations based on the Charm++ zero copy APIs, and this really motivated the creation of those APIs because Charm++'s model of explicit message objects differs from MPI's model of user-owned buffers for messages. So we added these new zero copy APIs, which allow you to do more in-place data movement in Charm++, and we're using those inside of AMPI now. Based on that, we are able to optimize for PE local and node local messages in AMPI. So this figure shows that our latency on the left and bandwidth on the right is able to outperform process-based MPI implementations on this system Quartz at Livermore. And that's basically just due to the use of true user space shared memory rather than having to rely on CMA or KNEM or some other interprocess copy mechanism. But the question naturally arises after that work, where we were able to outperform some MPI implementations in shared memory. How could we improve this further? And we had a couple different ideas. One is to make more direct use of the shared memory within a node in AMPI, and I'll talk about that in a second, as well as allowing the completion of messages to be fully asynchronous. And in order to illustrate this, I'll show an example. Okay. So in this figure, we see 4 ranks on the 0th PE, all running on top of the same scheduler. And then we have rank 4 on PE1, and they're all in the same shared address space. Now, typically in AMPI, when you want to send a message, oops, go back. Okay. When you go to send a message from rank 0 to rank 4 here, we will send a message through the scheduler queue as is normal in Charm++. So we'll enqueue a message object there into that queue. Sometime later, that entry method will execute that's associated with rank 4. And what I'm showing here on rank 4 is the various internal data structures inside of AMPI that are responsible for message ordering and message matching. So after this message finally makes it through the scheduler queue and runs, it will be placed into this message ordering queue first. And after that, depending on if the message is expected or not, it will go into one of these other message matching queues. And if it is expected, we decrement this counter that says how many different requests we are currently blocked on for that rank. And all these requests are pooled internally. So there's sort of a dance here between different data structures inside of AMPI that are required to go from the message send to finally completing the message. And after a message is complete, if this is a rendezvous protocol message, we'll have to notify the rank that sent the message that that message is complete. And these various data structures can make it quite difficult to optimize things further. So one thing we did was take a step back and look at the MPI messaging semantics. And we realized MPI messaging semantics are stricter than necessary for many applications and really limit the communication performance in different ways. The two main semantics I'm talking about here are that messages in MPI are non-overtaking between a pair of ranks in the same communicator. So if you send 5 different messages between the same pair of ranks over the same communicator, they have to be matched in the same order in which they were sent. This means that messages have to be buffered until they're in order, and you have to keep track of these sequence numbers so that you know what order the messages were sent in on the receive side. The other semantic issue is that message matching in MPI is quite complicated because of the need to support wildcard sources and tags. The same message that you send from one rank to another can be matched by different receive calls. So you can match it with a receive call that has the exact same source and tag, or you can use wildcards to match those. And these taken together complicate the message matching data structures quite a bit. Previous research in this area and in the MPI community has showed significant benefits to relaxing the semantics of MPI communication. So Hong Vu Dang from here at UIUC and Mark Sneer's group showed a significant performance improvement for MPI thread multiple applications by limiting the semantics on wildcards and ordering. And then Mincy and Pavan Balaji demonstrated improved asynchronous progress support by not allowing wildcards and putting restrictions on message buffer allocation. And a new thing in MPI 4.0 standard, which was approved this summer, defines a new set of MPI info objects for conveying the application's use of MPI features or semantics to the MPI runtime. So when the user creates a communicator, there's now a standard set of MPI info objects that they can pass to the runtime that say, I'm not going to use wildcards or other features like that. based on this previous work and our ideas about AMPI, we decided to look into not allowing out of order messages, or into allowing out of order messages and not allowing wildcard receives. With those two restrictions, we know a couple things. First of all, message sequencing can be eliminated entirely. And second of all, each message will match to exactly one request. And we also know exactly which rank will fulfill that request. So each side of the send receive knows who's going to fulfill that request. And without these two sort of semantic restrictions, we can greatly simplify the data structures inside of AMPI for message matching. So this led to the development of a sort of modified AMPI runtime that I'm calling AMPI async. And this avoids message sequencing entirely and tries to do as much as possible directly through shared memory as it can. So one of the keys here is that message matching with no wildcards and no message sequencing can be done with a single concurrent hash table, as compared to the typical method of using two separate queues for posted requests and unexpected messages in MPI. With the full MPI semantics, it's quite difficult to make the MPI message matching multi-threaded because of these queues and the need to traverse them sequentially. But with this concurrent hash table design from Hongbu Deng's work, you can efficiently do this with one expected cache miss per access to this hash table. The other things that need to change inside of AMPI is that the number of blocked on requests that we keep track of in order to reawaken the rank after all of its messages for like an MPI wait all complete, that has to become atomic, and access to the request structures also has to be locked or atomic. With these changes and with a node group in place that will handle all communication for that node and can complete requests directly through shared memory. So a message comes in to the node group can look at the message and say, this is for rank 7. Here's rank 7's concurrent hash table of requests. I'll insert it into there and see if there's a match. And if so, then I can reawaken rank 7. This is illustrated here in this figure, sort of similar to the previous one. And the main benefit here is that when we're sending a message, we don't have to wait for that message to go through the scheduler queues. So the COM thread can complete communications directly and then reawaken the corresponding ranks. And this saves on user level thread context switches. So if a rank's communication can be completed asynchronously, then it won't need to context switch away to the scheduler and then lose its cache state as some other rank writes over that, basically. Another thing we looked at on top of all of this was that for PE local messages, some of these locks and atomics are unnecessary and can be avoided. So since we know exactly which rank will complete each request, and we know exactly which ranks are on our PE, we can maintain a separate hash table that doesn't have to be locked for all PE local requests and messages. So in this way, PE local messages don't have to go through this locked concurrent hash table. We also don't have to lock around the access to those request objects. When we create the request objects, we know who's going to fulfill those. And the counter can also be non-atomic. And then if you have multiple PE local transfers inside of a wait all statement, you can update that atomic counter once per wait all rather than once per PE local message as well. So we've implemented this on AMPI. It's we're calling AMPI async here. And we see ping pong performance, as can be kind of expected, doesn't really change much. It's slightly higher for the async version. And this is due to some of the locks that we've added and more complicated control flow inside of AMPI. But we're not really expecting benefit here because there's only one message that's being sent back and forth. And the real benefit we're going to see here is when you're sending multiple messages and the matching becomes an overhead. On the right, we have a multi-latency benchmark from the OSU benchmark suite. And we've modified it to send 16 I sends and post 16 I receives, and then do a wait all on those. And we see a modest improvement here for this case. It's modest because we aren't doing any real work between these. So this is kind of just measuring the message matching overhead. We've since looked at a few different applications. So this is still kind of early work, but looking at various applications is interesting with different communication patterns. So this is comparing AMPI async with and without the locality aware PE local optimizations to plain AMPI. And what we see is sort of a mix. So with Kripke, we see performance slightly decreases. And then for two different stencil codes, Jacobi 3D is a simple benchmark that we've written. And Plascom 2 is more of a full-scale application that's stencil-based. We see performance improvements of about 7 to 11%. And then we also looked at Lulesh, which gets a performance gain of 12%, I believe. And the key thing we think so far as to explain these differences is the number of neighbors that are concurrently communicated with. So in Kripke, it's a parallel sweep communication pattern where each rank communicates with 3 other neighbors at a time. And it's kind of a latency bound code because of the way of the parallel sweep works. So we don't see any performance improvement with the asynchronous support there. For Jacobi 3D, that is a 3D stencil code that has 6 neighbors. And we see a modest improvement there. Plascom 2 and Lulesh both have both full 26 neighbor 3-dimensional codes. And we see better improvements there. I'm still doing more work on tracking down the cache numbers and numbers of user level thread context switches to better explain the differences across various codes. So yeah, for future work, along with that more fine-grained performance analysis, we'd like to look at more applications. Support rank migration and load balancing. Currently, we're just assuming these are fixed. And currently, this is all sort of hardwired into AMPI. But we'd like to conform to the MPI 4.0 standards construct of allowing this to be done on a per communicator basis. And that can allow the application to potentially use wildcards for some aspects, but then maybe for the main iterative loop or for various modules to turn this sort of thing on. The next thing I'll talk about is collective communication optimizations. In past work, I've talked about the need for virtualization aware, shared memory aware collective implementations. And this is to basically avoid creating on the order of the number of virtual processor messages and memory copies into those messages. We've worked on making no-keep broadcasts optimized to only have one copy per node. And we use that inside of AMPI. And we're also looking to use more and more of the zero copy APIs for collectives as well. So I believe Nitin will talk about that as well. For reductions, there's also an issue where currently the charm reduction API relies on CK reduction messages, which dictates that the user create a per rank message, copy into that, and then it potentially gets processed directly out of that immediately. Just reducing the number of copies has led to pretty good performance improvements, about 2x for runs with virtualization here at the bottom for a broadcast. But the question that we are looking at is, what is the question that we're now looking at in sort of connection to the virtualization issue is, what about migration? Does that cause overhead during collectives? For point-to-point, we know that it is only in the time step following a load balancing step that we see overhead, because the location caches have to be updated. And I've tested broadcast and regular all reduce, and there's no significant overhead there either. But the more interesting problem is with collective algorithms that rely on rank ordering. One particularly interesting example of that is non-commutative all reduce. And that's what I'll talk about now, but it could also be applicable to gather and scatter operations. So non-commutative all reduce are interesting because they are still associative, as all MPI reduction operators have to be by the standard, but they are non-commutative, which means that the operations have to be performed in rank order. The associativity means that you can still apply reduction operations to partial contributions. You don't have to have the total order of them. It doesn't have to be done serially. But that allows some room for optimization. AMPI's current implementation doesn't really take advantage of associativity at all. What we do is we gather all the contributions to rank 0, we sort the contributions and apply the reduction operation in order, and then we broadcast out the results. So this gather broadcast leaves a lot of ranks idle during that serial sorting and application of the reduction operations. And so we had the idea that we could instead apply the reduction operations opportunistically throughout each step of an algorithm. This means that if we have some sub pieces of the overall reduction that are in rank order, we can take advantage of that. So the idea is to, at each step of the algorithm, try to sort as much as possible and apply the reduction ops as much as possible. What we've implemented so far is our 2 algorithms for the internode reduce. So before we get to the internode, we always try to sort and apply the reduction operations as much as possible in each node. But then for the internode reduce, we've implemented support for the recursive doubling and recursive halving algorithms. Recursive doubling is commonly used for non-commutative reduction operations because it has this nice communication pattern for that. Recursive halving is used more for like all gather operations typically, and not for non-commutative operations because it's inverted rank ordering. So I'll show examples of that. Recursive doubling, just to show a simple example here, this is using MPI maxed operator just for simplicity of illustration. But on the top, we have the processor number. And then here we have each processor contributing 3 ints for the max all reduce. And so recursive doubling, you first communicate with your neighbor processor, and then each step of the algorithm for log p steps, you communicate with someone twice as far away. So this naturally leads to a nice ordering of the contributions. So you can see that in the first step, each processor ends up with contributions from 0 and 1, rank 0 and 1, and then 0 through 3 for the first half of them, and so on. The important thing is that the message size there always remains the same at 3 ints. When you look at recursive halving, on the other hand, this doesn't play well with non-commutative operators because the ordering of the communication steps is reversed. This reversal is actually beneficial for all-gather type operations because of its network contention characteristics. So in recursive doubling, you're sending the smallest messages in an all-gather operation first to your closest neighbors. And then at the end of the algorithm, you're sending the largest messages to the farthest distance. In recursive halving, you change that so that you are sending the largest messages the shortest distance across the network. So this example shows for a non-commutative all reduce, the messages grow in size as we go throughout the algorithm here because we can't sort and combine them because you don't have a nice contiguous sub-range of contributions. So we've implemented these and compared them to the current approach of a gather and then sort and apply the operations and then broadcast the result. And what we see is that if you have a nice mapping, like the normal block mapping of ranks to cores, recursive doubling performs well in that case. So it's able to perform about 8x, I think close to 8x better than recursive halving and the gather broadcast approach. And this is due to the fact that the message sizes remain small throughout execution. On the right, I have the same algorithms, but for a fully randomized mapping. And this sort of mapping kind of ruins the ability of recursive doubling to maintain small message sizes. As the ranks are migrated around here randomly, you lose that nice characteristic of the algorithm where things will be applied in rank order. I've also looked at different other sort of mappings that more closely resemble what would happen in an AMPI execution with load balancing. In order to simulate that, I looked at migrating 10% of ranks to one of their neighboring nodes. So this might be similar to a hierarchical load balancing strategy. And we see here that recursive doubling is able to still perform quite well in that scenario. And when we look at 10% of ranks migrating to a random node, we see the performance drop off somewhat significantly just by more randomly migrating those around in what might be more of a greedy based strategy. So what's interesting here is just how drastic of a difference in performance you can get between these different mappings for non-commutative all reduce. So we're looking at different algorithms to do this. So far, we have recursive doubling, recursive halving, as well as this gather broadcast approach. I'm also looking at ring algorithm and Robin Seiffner's algorithm, which is like a reduced scatter all gather. And we're also thinking about how we could apply the same idea to an all gather, but there you would just be sorting the contributions rather than applying a reduction operation to combine messages. Another thing I'm thinking about is how to incorporate load balancing into this. So Ronak talked about position-aware load balancers. You could also have hierarchical load balancers that try to keep migrations within the node or close by as much as possible. And to wrap up, AMPI support for virtualization and shared memory between ranks enables various sorts of communication optimizations. And we're now looking at ways of restricting the messaging semantics in order to enable more concurrency within a node. as well as looking at collective algorithms and the unique challenges posed by non-commutative all-reduce. And that's all I have for today. Thank you.
Thank you, Sam. We're a little bit out of time, but maybe we can take one question.
I see Phil's question. How does the MPI4 API deal with library composition? Yeah, it's per communicator. So they've made all of the communicator creation routines take an info object optionally. So like MPI com create with info. And that's the main way I believe they're working on it. You might also be able to do the MPI sessions thing that Evan referred to in the other comment there. I haven't seen that in any work yet, though.
Right. Any other question? Yeah, I think let's take a break. So this was the last presentation in this session. We now have a break of 10 minutes until 2:15 p.m. Central Time. Then the next session will start. Thanks again for the speakers.
So I think we're ready to start the next session. This is going to be the session on performance analysis. We're going to have two talks. The first one is from PPL's own PhD student, Zane Fink, and he's going to be talking about the performance evaluation of different Python programming models. So Zane, take it away.
Hi, thanks, Ronak. So like you said, Zane Fink, second year PhD student here in the PPL. Today I'm going to be talking about performance evaluation of Python parallel programming models, CharmMPI and MPI for Pi. So just a brief overview. I'm going to start by introducing CharmMPI, including some of the basic syntax and a few of the features, because CharmMPI was created a few years ago, but it's laid relatively dormant until somewhat recently. And then we're going to look into a performance analysis of two Python parallel programming frameworks, CharmMPI and MPI for Pi. And I think this talk kind of dovetails nicely with Alex's previous talk, but here we're coming in from the other side. We're looking to add a bit of productivity to high performance code rather than adding more performance to productive code. And in that same vein, there's been a pretty big recent shift toward productivity in parallel programming language and parallel programming with kind of recent proliferation of domain-specific languages and performance portability efforts. And kind of parallel to that, Python has seen great success in the kind of data analytics, scientific computing, and machine learning communities. And it's more recently drawn the attention of the HPC community. And so, as we know here at the Charm++ workshop, Charm++ is used in a bunch of different applications, but for those that aren't familiar with C or C++ or Charm++ itself, it can be a high barrier to producing high performance code. Not only do you have to know C and C++, but also we have this Charm interface file. And so because of Python's broad success in scientific communities, we have this great space of productive high performance libraries in Python, such as NumPy, SciPy, Pandas, TensorFlow, and probably a few tens of thousands others. And so with CharmMPI, we want to try and get some of the best of both worlds with the high performance and high productivity of Charm++. And also with the high productivity of Python. So just to go over a few of the basic structure of a CharmMPI program, you define char classes in Python. They're just regular Python classes that just inherit from the char. And you create a main driver that will create chars and it'll begin execution, similar to a regular Charm++ program. And then that's it. That's a CharmMPI program. No additional compilation or extra files are required. So to take a more concrete look, here we have a complete hello world example written in Python. Here at the top, we have our basic imports, char, array, and charm to get us set up with writing a CharmMPI program. And we define a char class here, just a simple hello world. And this is a regular Python method, but it's also used as an entry method in CharmMPI. It's just called say hello. It looks exactly like any other class method in Python. And so all this method does is it says hello from char, prints out its index in an array, and then tells you what PE it's on. And so in the main here, it looks like a regular Python main function. We just get the args from the command line through the charm runtime. And so we create an array of hello world chars. In this example, we have 8. And then we just broadcast the entry method to tell them to say hello. And then this is our entry point that we register with Charm++. We tell it to start. And so here's the output. We can see that each of the 8 chars, in this example, they're spread over 4 PEs. They just say hello from char and give their ID. One of the nice features of CharmMPI is this automatic serialization of entry method parameters. It uses the pickle library for custom arbitrary Python objects. So anything that can be pickled can be sent over the network. But for NumPy buffers and other buffer-like data structures, it directly accesses the underlying buffer And this can save some expensive serialization and copy overhead. And so here is an example. We have a remote proxy called a remote object, and we call the function entry method on it, and we pass it a mixture of arbitrary Python objects, param1, and we have NumPy arrays as well, and we can mix and match them as we please. Taking a look at the CharmMPI software stack and how it interacts with the rich ecosystem of libraries in Python and the Charm++ runtime itself. We see here that we have user code that interfaces between the CharmMPI runtime and kind of pre-built, pre-existing libraries such as NumPy, Pandas, or SciPy, or some of the JIT projects that have become more common in Python, such as Numba, PyCUDA. You could also have PyOpenCL and any of the others up here. And so the user code will create and manipulate these objects and define some kernels, and then it'll, using the CharmMPI runtime, it'll interact, pass these objects to the Charm++ runtime, and through entry method invocations, reductions, and so on. And then we have this Python C interaction layer, which the runtime will use to get access to the Charm++ runtime itself. And this is currently written in Python, and so this allows us to bridge between Charm++, the C++ binary, and the Python code written by the user. And so if we want to send a message to another char, we can send a NumPy array, pass it to the CharmMPI runtime system, and then this will be converted into something that can be used and seen by the Charm++ runtime. And then on the receiving end, we just pass it back up to the stack, and we have a NumPy buffer on the other end. A few additional CharmMPI features, we'll just introduce them at a high level. Char arrays, as we've already seen, we have support for the sections in Charm++, also different collective communication operations are implemented, the standard broadcasts and reductions, but also we have barriers and all reduces as well. We have a channel API for point-to-point communication between chars. We have also support for a task pool, so we can create a pool of workers, one on each PE, and from the main char we can just distribute tasks to them, and the runtime will handle task management completion, and you can explicitly specify dependencies between them. I mentioned this earlier, but we have optimized communication routines for NumPy arrays and other things that look like buffers. And then something that's much more recent, and it's not quite merged yet, but we're almost there. We recently implemented GPU direct capabilities, and this eliminates the host staging, the staging of messages that contain GPU resident data. So diving a bit more deeply into that, like I said, the GPU direct allows us to eliminate the extra host copy when sending data that's on a GPU over the network. And as we'll see, this reduces the latency of GPU communication and increases the bandwidth. Here's a more concrete example, just a simple ping pong send and receive operation implemented, shown here for one char. At the top here, we have the host staging mechanism. So we want to send from this device send buffer. We want to send it to a remote char. So we have to first copy it from the device to the host to this intermediate buffer, and then we can send it over the network. And then on the receiving end, we have this channel that's open, and we can call the receive method. And an additional performance penalty is that this receive call will perform an additional allocation on the receiver end. So a buffer has to be allocated, and then it can be transferred from the host to the device, and then it can be used. But on the bottom here, we have our GPU-aware communication, and it's much simpler. It's far more performant as well. We can directly send and receive device buffers. Just going to go over quickly a case study. for the performance of Charm for Pi, comparing it to Charm++. Just to kind of set some baseline expectations. We look at LeanMD here, which is an implementation of the Leonard-Jones potential between particles. It's the mini app that's kind of representative of some of the computations performed in AMD. So we have a 3D space that we decompose into cells, and then we further decompose the interactions between the cells, if you recall from David Hardy's talk earlier. And so in each iteration, the force calculations are done for all pairs of atoms that are within a certain cutoff distance. And so here the communication code is written in Charm for Pi, and the physics code is JIT compiled using Numba. And here we just consider strong scaling performance on blue waters, 8 million particles from 2048 cores up to 16,000. We see that in general, Charm for Pi is between about 10 and 20% of the performance of Charm++. This example is a bit pathological because there's a lot of fine-grained management of sections. And as we'll see, there's some kind of performance overhead in Charm for Pi that makes it perform worse in fine-grained situations. But we're actively working on this case and working to optimize it. So moving on to comparing the performance of Charm for Pi and MPI for Pi. If you're unfamiliar, MPI for Pi stands for MPI for Python. It's the most popular package providing bindings to Python, providing MPI bindings to Python, and it's been in development for a long time in Python terms, since before 2011. And we look at Charm for Pi and MPI for Pi specifically because the kind of way that Charm++ and MPI perform relative to each other is pretty deeply studied and well understood. And so we can kind of use that as a baseline for our comparison between Charm for Pi and MPI for Pi to kind of look at how effectively the Python layer utilizes the underlying C++ mechanisms and what overhead the Python itself imposes over that. And so we talked about earlier about the kind of proliferation of Python in HPC, but there haven't been really good performance studies done on these different systems. And we choose Charm for Pi and MPI for Pi specifically because they provide Python bindings to well-established parallel programming models, whereas many others tend to introduce distributed computing for Python that was only ever existed as a Python implementation, such as Dask or something like Ray. So in this study, we look at some CPU and GPU benchmarks to assess some of the relative performance characteristics between the two. We'll start with Stencil 2D on the CPU and on the GPU with uniform load. And then we'll look at particle and cell on the CPU. And it's a mini app that has load and balance. So we're looking to kind of study how this load and balance affects the performance of the applications, and also to see how effectively Charm for Pi itself utilizes the load balancing capabilities of Charm++. And then we'll look at some kind of fine-grained networking micro benchmarks and compare their performance there. In this study, we look at two different platforms. One is CPU-based, one is GPU-based. We start with StampY2 at TAC. It consists of Intel Skylake nodes, two 24-core CPUs on each node for 48 total physical cores. We map each processing element to one core, similar to how it would be done in MPI. On Summit, we use one PE per GPU. And so the code that implements the communication between processing elements is implemented in the respective MPI for Pi and Charm for Pi, but they share the exact same compute kernels, and we use Numba for both the CPU and the GPU. On the CPU, we use their Numba JIT decorators, and then on the GPU, we use their more recent CUDA bindings. Beginning with the stencil 2D implementation, we look at a 5-point Jacobi iteration in 2 dimensions. Uniform work is assigned to each PE. This is just a standard stencil benchmark. We don't use over decomposition in CharmMPI. As has been noted earlier in the workshop, we found that for this problem, over decomposition results in performance degradation for the sizes of the problem that we studied. We're going to begin with a look at strong scaling. On the left here, we have a kind of smaller scale performance, and on the right, we have larger scale performance. We scale until we hit a wall, basically. We don't want to use up a bunch of our node time, so we stop increasing the number of PEs when we see that performance degrades pretty substantially for one of the frameworks. So on the left here, we have the number of PEs on the x-axis, time per time step on the iteration. On the y-axis, we break each implementation down into the time spent performing the compute in each iteration, as well as time doing the communication. Communication includes packing, unpacking, sending over the network. These error bars here designate the 99% confidence intervals of the means for each respective computation and communication. So we see that at this smaller scale, the performance between CharmMPI and MPI for Pi is identical. And this is obvious because they share compute kernels and the compute time dominates. But looking at the larger scale, up to 128 nodes on StampP2, we start to see that MPI for Pi's performance runs away from CharmMPI as the kind of task granularity decreases. The communication overhead starts to dominate. And we see here, especially at the right end, that CharmMPI, its networking performance starts to become, it degrades substantially and even increases the runtime as we add an extra 3,000 PEs. And we'll see kind of moving forward that this is a pattern in the CharmMPI results, and with some of the micro benchmark results that we'll take a look at later, we'll really illuminate this and then provide some obvious next steps. Looking at weak scaling performance results, between CharmMPI and MPI for Pi, the performance is very similar. There's not any significant measured difference here. Looking at GPU Stencil 2D, I'll note here that both implementations use GPU-aware backends. So we use MPI for Pi built with GPU-aware MPI for Pi, and we use Charm4Pi built with Charm++'s UCX backend. And similarly, MPI for Pi, OpenMPI is built using UCX. So we see as we increase the number of nodes, recall that there are 6 GPUs per node on Summit. We have no significant difference in the communication or communication between the different frameworks. So this suggests that the GPU direct implementation in both frameworks, it uses the same underlying infrastructure. And so it doesn't impose any additional significant overhead, at least what can be seen when we compare directly between CharmMPI and MPI for Pi. Weak scaling is a similar story to the CPU weak scaling. The problems weak scale well. Don't think this is necessarily surprising. We've probably all seen this type of plot before for weak scaling Stencil 2D. So just to take a step back and summarize, CharmMPI is competitive with MPI for Pi on the CPU, and until the task granularity is smaller, and we've seen that the communication dominates, and it becomes a really big problem at higher node counts, and even the performance degrades as we add 3,000 CPUs. And so we've seen with the GPU results that RDMA technology is necessary to match the performance of MPI for Pi. It makes very good use of the underlying mechanisms in MPI. Moving on to the particle and cell code. This is a parallel research kernel. Currently, it's part of the Intel Parallel Research Kernel Suite, and it's used for evaluating the load balancing capabilities of programming models. And it's worth to note that the physics in this kernel are unrealistic, but it's nice for comparing frameworks, as it has desirable verification qualities. And so we'll use it here. For more information on the kernel itself, there's the reference paper, and also there's an adaptive MPI implementation on the Intel Parallel Research kernel page. So we look at performance results on TAC at Stampy2 at TAC. On the x-axis, we start from one socket all the way up to 16 nodes. With CharmMPI, when we use over decomposition, we use 8x over decomposition. We found that this gives us the best performance in our experiments, and we use refine LB. So looking here, we have MPI for pi in the black line here. CharmMPI without over decomposition or load balancing is shown in green here. In red, we have CharmMPI with over decomposition only. And then in blue, we have CharmMPI with over decomposition, and we use load balancing. We invoke the load balancer every 80 time steps. Again, empirically, we found this to give the best performance. So here we can see that CharmMPI is outperformed by MPI for pi in the base implementation with no over decomposition or load balancing. We can trace this back to communication performance, which we'll look at in just a moment. But when we add over decomposition, this alone greatly improves the load balancing between processing elements. And so we get a substantial performance benefit there, just about 2x over MPI for pi. When we add load balancing, explicit load balancing, we see a performance improvement of about 33% here on the left end. But as we move to the right, the performance delta decreases, and we even see here that load balancing has a substantial penalty in runtime of about 2x. We're still digging into this to see what exactly contributes, but our preliminary data suggests that this load balancing, the cost of it is much higher in CharmMPI and MPI for pi because of the time that it takes to serialize the chars, because we pickle them rather than using a pup framework, which can be greatly optimized. The pickle framework in Python can be rather slow. And so kind of our preliminary investigation suggests that this is due to serialization overhead of chars as they migrate. Moving on now to some micro benchmarks. We'll look at the OSU micro benchmark suite, just point-to-point micro benchmarks for both bandwidth and latency. Latency, one-way ping pong, bandwidth, the standard OSU bandwidth, looking at kind of the injection rate of the framework. Looking at intranode CPU benchmarks, on the left here we have bandwidth, on the right we have latency. We look at sizes from 16 bytes all the way up to 4 megabytes. On the y-axis here we have the bandwidth in gigabytes per second. I'll note here that the Charm++ implementation that we compare to, it doesn't use zero copy and it doesn't use SMP mode. We're looking specifically at the overhead of CharmMPI. So this isn't the Charm++ bandwidth that a typical application would see. And so looking here on the left, we can see that because we do host staging, message marshalling mechanisms, the bandwidth that we have in Charm++ and CharmMPI is much lower than what's observed in CharmMPI and MPI for pi. Moreover, MPI for pi itself imposes a much smaller penalty over MPI than does CharmMPI on Charm++. Looking at latency, we see a similar story. The latency of MPI for pi is about double that of MPI at the small end. So we have about a microsecond of latency that's given by the Python layer. And as we move on to larger message sizes, that latency overhead is completely amortized by other factors. But when we look at CharmMPI, the layer is much heavier. Charm++ here is shown at about 7 microseconds, but CharmMPI here is at about 20 microseconds. And so the Python layer in CharmMPI is far fatter than what is in MPI for Pi. Looking at internode CPU, we see a similar story. On the left here, we have bandwidth again. This vertical black line is the bandwidth of the interconnection network of SNAP-B2. Looking here again, we see that MPI for Pi and OpenMPI are able to reach the peak bandwidth of the interconnection network, whereas CharmMPI and MPI for Pi here have much smaller latency. We have about a 5 times difference between the two. Similar story for bandwidth, CharmMPI, fat Python layer. Looking at the GPU, reminder that both MPI for Pi and CharmMPI use a GPU direct implementation. Here we can see that the MPI for Pi implementation does have substantial performance degradation of the OpenMPI GPU-aware implementation. But we do see that MPI for Pi does outperform Charm++ and just CharmMPI. And that CharmMPI and MPI for Pi perform similarly. If we look at latency, we see that MPI for Pi has a much higher latency than OpenMPI here. We're at about 20 microseconds for OpenMPI, or for MPI for Pi, and at about, I think, 40 here for CharmMPI. And this is because both frameworks have to use the array interface that's given by the CUDA bindings to Python. The most popular ones use it. And to interface with a buffer, we have to do a dictionary lookup and to find the address and the size. And so this has a pretty big performance penalty. For the internode GPU, similar story. All frameworks reach the peak bandwidth, but the Python frameworks do impose a substantial performance overhead. And so this is kind of what I've been saying as we've been going along. CharmMPI is a fat Python layer, certainly much fatter than that of MPI for Pi. And that really, one of the biggest limiters in CharmMPI performance is lack of RDMA through CharmPlus's zero-copy API, which we're currently working to support. So in summary, in the interest of time, I'll go over this. I've kind of been summarizing as I go along, but looking forward at the performance of parallel programming in Python, we want to look at more frameworks, particularly those that are less explicitly parallel, such as Dask, Ray, or Legate, which we heard about from Alex earlier. And we focused on some of the more standard HPC benchmarks here, but we didn't look at data analytics or machine learning, and we compared only performance here. We disregarded some of the different productivity aspects of the different frameworks, and that should be explored as well. Some of the recent improvements in CharmMPI, I won't spend much time on this, but there has been recent work. If you're interested in hearing more about it, we have information online. Moving forward, I think one of the biggest sources the biggest pain point in CharmMPI is lack of zero-copy API. That's probably the most important here. And we think that CharmMPI can be used as a kind of implementation engine for other abstractions to kind of bring more productivity to Charm++ programming, while hopefully not sacrificing too much performance, or also maybe we can find kind of a hierarchical abstractions that allow you to progressively lower to get more performance. If you're interested in more information on CharmMPI, we have documentation and the source code is available. And if you think that CharmMPI is something you'd like to use or work with, we're looking for collaboration. So please reach out, I'd be happy to talk. But I'll leave this up. I'm just about out of time, but I'll take any questions now if there are any.
Okay, Zane, thanks. That's a great talk. Anyone have any questions? We have a couple minutes. If not, I have one very quick question. As regards to what Alex was talking about before, what's the story in terms of supporting libraries in Python in CharmMPI?
Yeah, so we have support for, so there's kind of a collection of libraries in Python, and there's an effort in the community to bridge some of the APIs as they kind of interface with things like MPI for Pi or CharmMPI and external frameworks. So we have, for example, like an array interface that these different projects will implement so that it doesn't matter if you're sending a NumPy array or a TensorFlow tensor, you can access them in the framework with the same implementation, with the same code path. And so there's pretty broad support for APIs like that. As far as working between the frameworks themselves, we've had success using CharmMPI and MPI for Pi together, but I haven't seen anyone that's used interworking more broadly than that.
Okay, makes sense. Any other questions? Okay, seeing none, let's move on. Thanks for that, Zane. So the next talk is about a tool to analyze adaptable workloads from a team from Universitat Jaume I. So if you all want to go ahead.
Okay, I can share the screen right now, right?
Yeah, go ahead and share your screen.
Okay.
Okay, everything seems to be working.
Okay, seems to be working. Okay, perfect. So I can start, right?
Go ahead.
Okay, so good afternoon. I'm Iker Martin, and as you said, I'm going to present a synthetic tool for analyzing adaptive workloads. First, I'm going to talk about the motivation that drives this work, and then I will explain the synthetic application that we are developing. Also, I'm going to talk about some results that we have been obtaining, and then I will conclude the work and talk about our future work. So right now in data centers, as you know, the resource managers have a strict policy, and for example, there are times that there are jobs which could be executed, but not with the amount of resources they want. And what could be performed, for example, here is that job 1 could give away one of its resources, and job 2 could start executing. Or on the other hand, if there are no jobs in the waiting queue, job 1 could take the node 3 and increase its performance. And this type of jobs are called adaptable or malleable jobs, and they are based on a stoppings application in one point and creating the new amount of processes and redistributing data to this new amount of processes. For example, if we have here for an iterative application where this stop, it is reconfigured to the new amount of processes, and this new amount of processes start executing. So what we have in mind is a synthetic application which as real applications are very hard to, it's very challenging to recreate, to adapt an application to be malleable. We have created a synthetic application that performs that. And what we have in mind are two steps. The first step is that this application will be able to show which is the best reconfiguration mechanism that delivers the best performance for the application. That means testing different ways to reconfigure the job and tell which is the best one. And our second step is to, from this synthetic application, create an adaptable workload and see how it performs in a system. As I'm going to describe into the synthetic application, it is composed of 3 modules. A commutation model, which simulates an iterative application, a reconfiguration model which takes care of reconfiguring the application, and a metric gatherer which captures times, and later on, at the end of the application, it stores the times, so it can be later analyzed, which is the best configuration. And to decide which is the best configuration with its execution, the user can pass a configuration file, which describes how the application will be executed. Passing on to the first model, the computation one, it is the user gives in the configuration file an iteration time. This iteration time is during this iteration time, two things are being performed. On one hand, it is a computing, simulation of computation, and on the other hand, communication. For the computation, it is performed by different procedures. Right now we have two, a compute bound and a memory bound. And with the selected one, it's calculated how much time takes place this procedure. And from this time, it's calculated how many times this procedure has to be executed to reach the iteration time. In this case, it has to be executed 7 times to reach the iteration, to reach one iteration time. And on the other hand, we have the communication. As normally, a real application has communications. In this case, we allow 4 different communications. One is based on point-to-point communication, another one on collective one-to-all communication, as could be AMPI bcast, and a third one based on all-to-all communication, and a last one for reductions. In all iterations, the user decides, for all iterations, the number of bytes that it will be communicated, in this case is n bytes, and can decide at the same time one of these communication procedures. So to sum up in the computation, you decide which procedure you want to perform, and it is being performed until the iteration time is reached. Then we also perform the communication. Passing on to the reconfiguration model, the reconfiguration is performed in a way that before each iteration, it must be checked if the application should be reconfigured or not. And it takes, for this task, this task is divided in 4. The first one is communicating with the resource manager, then calculating the new mapping for the new amount of resources, then expanding these new processes with this layout, and finally redistributing data from the parents, which is the original group of processes, to the new group of processes that we call children. This demonstrates the same thing, and here I want to show that it's not the job which it's not the job who decides if it's going to be reconfigured or not, but he shows his willingness in his resize point to be resized. And it's the resource manager who decides if the job will be resized or not, and to which amount of resources it will be resized. As right now it's not developed this first step of communicating with the resource manager, and right now we are forcing to resize. That is, after an amount of iterations, it's performed at a resize point with these 3 tasks that I'm going to explain right now. The first one is calculating the new mapping, and we have developed 2 different mappings. One is a balanced one, which makes a well-balanced distribution of the processes among the nodes. And the other one is a compact mapping. In this case, a node is filled with processes before starting to fill a new node. After calculating this process, we spawn the new process. The processes are right now spawned with MPI spawn, but we are still studying another ways to perform this spawning. And with MPI spawn, what it does is creates a new group of processes, the children group, and at the same time it creates 2 new communicators. The MPI work communicator for the children, and intercommunicator that joins the group of parents and children. It's from this intercommunicator that the redistribution of data can be performed. After redistributing the data, this communicator is freed and no longer used. The data redistribution, we are basing it on the MPI primitive MPI also B. And what this function allows is to redistribute data from any process, to distribute any amount of data from any process to any other process. That is, for example, that process 0 can redistribute data, sends 10 elements to its children 0, another 10 elements to its children 1, and 5 elements to its children 2. Another contribution that we have for this work is allowing an asynchronous redistribution. That is, that as what I explained before for malleability, after when it starts, the application is stopped. It creates a new amount of processes, and then it does the data redistribution from parents to children. And when this finalizes, it starts again with the children. But what we are proposing is an overlap this computation of more iterations with an asynchronous redistribution. That is, here, as it can be seen again, more clearly, is after spawning the processes, it starts an asynchronous redistribution, and after each iteration, the parents check if this asynchronous redistribution has ended. When they have checked that it has finalized, they synchronize again with the children, and they allow the children to start the computation in the next iteration. We also have allowed these asynchronous procedures to be performed with in four different manners, which 3 of them are based on MPI non-blocking primitives. The first one is point-to-point, is based on point-to-point communications, and the other non-blocking primitives are based on the MPI I also all B. In this case, there are one difference between them. The first one is considered finalized when the parents have checked that they have sent all the data. While in the other one, it is considered finalized asynchronous redistribution when the children has received all the data, which not always is at the same time. We have also another option which is based on pet reads. And in this case, what it is done is after spawning the new processes, it's also spawned for each parent a new thread. This thread takes care of the data redistribution, while the main thread continues computing. Also, in real applications, we see that data is normally categorized in 2 types. One, data that is constant and doesn't change through the execution, and variable data. Therefore, what could be normal is to distribute constant data asynchronously and redistribute the variable data asynchronously. Variable data cannot be sent asynchronously because it will be invalid, as after each iteration it will be modified by the parents, and the children won't have valid data. Passing on to the matrix gatherer model, it is very simple. It's very simple, and it's based on the function MPI _W time. And what it does is captures some times. These are the total execution time of the application, the spawn time, the synchronous redistribution time, and the iteration time. In the case of the iteration times, it's also stored how many procedures have been executed in this iteration, and if an asynchronous redistribution has been performed. This is because we want to check if the overlap of the computation and data redistribution causes a drop in performance for iterations. Finally, in the configuration files, we define how the execution of the application will be performed. It is divided in three types of parameters, and the first type of parameters are the ones dedicated to computation. In this case, is the iteration time for a sequential application. Also, we have defined 2 parameters for the computation, which is the problem size and which procedure will be executed, and the communication. In this case, how many bytes will be communicated in each iteration, and the type of the communication time has been selected. Also, as general parameters, we have the ones dedicated to reconfigurations. That is the number of resizes that will be performed in this execution. This case is 1. The number of bytes that will be sent synchronously. That could be 0, and if that's the case, there won't be a synchronous redistribution. We also have the same parameter but for asynchronous redistribution. Again, if this value is 0, there won't be an asynchronous redistribution. And for asynchronous redistribution, as we have the 4 options, there is also a parameter to decide which option is going to be used for the asynchronous redistribution. In the last zone, we have the parameters dedicated to each group of processes. That is, for example, as right now this is not implemented, the communication with the resource manager is the number of iterations they will perform, how many processes are there, and the mapping of they will perform for when they are created. And we have one more parameter, that is the factor S. Factor S is for selecting how the application will be the performance of the application for each group. That is because in real applications, when you double the number of processes, the time is not necessarily cut in half. For example, here the application, this is performed it is taking the iteration time and is multiplied by the factor S, which delivers the real iteration time of this group of processes. And in this example, if the sequential time was 4 and the factor S is 0.5, the real execution time for this application or for this group of processes is 2 seconds. To sum up the synthetic application, it is composed of 3 modules and a configuration file. It is launched by a script, so the user only has to create the configuration file and launch this script. And then the application starts, which reads the configuration to know how it must be executed. It computes the data as if it was an iterative application and performs reconfigurations, which is taken care of by another module. These 2 modules are being observed by a third module, which captures times and stores data for later, so it is possible to analyze later which configuration delivers a better performance. Passing on to the results, the results has been performing on 2 nodes with a total of 40 cores. Iterations, each execution has been performed with 11 iterations, 1 for the parents and 10 for the children. And executions could be with 4 seconds of iteration time of 4 seconds or 0.4 seconds, in these cases for the sequential time. Also, all iterations have a communication of 10 megabytes. It is only performed 1 reconfiguration per execution. Factor S is applied to have a perfect speedup. That means if the process number is double, the time is cut in half. Both physical mappings have been used. And also the redistributed data is of 1 gigabyte and could be fully synchronous or fully asynchronous. Also, it has been used P3 option for asynchronous redistribution, and a mean of 5 executions were performed to obtain the times. Passing on to seeing the results, here is shown the times of the total execution time. In blue, we have the time that have been spent by the parents. In orange, we have the time for the reconfiguration, and in green, the time used by the children. The one that doesn't have a path is the asynchronous redistribution, and the one that has a cross path is for the asynchronous redistribution. Also, each bar shows the initial number of processes, the parent processes, and the number of children that it will be reconfigured to. In this case, it is performed with a compact mapping and an iteration time of 4 seconds. The conclusions for this image is that, well, for this result is that the asynchronous redistribution is preferred when shrinking the application, and it is preferred the synchronous redistribution when expanding the application. Also, we have detected that there is an oversubscription problem where on a state where when more than 10 tweets are in one node, this oversubscription state arises. For example, for this last case, we have 40 initial processes and 40 children. And this means that while the reconfiguration is taking place, a total of 80 processes are in a total of 40 cores. Therefore, oversubscription arises. In the case of asynchronous redistribution, another 40 threads are needed to perform the redistribution. Therefore, for this version, there are 120 threads for a total of 40 cores, which made the problem even more noticeable. For a balanced mapping and the other parameters, are the same, we find that the conclusions are the same. It is preferred to shrink the application with an asynchronous redistribution, and it is preferred to redistribute the application with a synchronous redistribution. When changing to a compact mapping and an iteration time of 0.4 instead of 4 seconds, we still find the same conclusions. It doesn't matter the iteration time, it will be always the synchronous redistribution to shrink the job and the synchronous redistribution to expand it. Also, when it is the balanced mapping and an iteration time of 0.4, we still have the same conclusions. But we have found that this the reason that the synchronous redistribution is preferred is because when you start to execute sooner with more processes, the application will be faster. That is that the synchronous redistribution needs less time to reconfigure. Therefore, you will start sooner with more processes. For example, here, going from 2 to 40 processes, you want to start with 40 as soon as possible. And in the case of the asynchronous redistribution, you want to stay with 40 processes a bit more time to perform more iterations in a faster time. Now, comparing how the the malleability is divided, that is the time needed for the spawning of processes in orange, the time needed for the synchronous redistribution in purple, and the time needed for asynchronous redistribution in red, the synchronous one. And for this case, we have a compact mapping and iteration time of 4 seconds. And what we find is that in nearly all cases, the spawning processes is the most expensive operation. And the asynchronous redistribution is always more expensive than the synchronous redistribution. This makes sense as it is being performed as a background task and could need more time. Nevertheless, it has to be kept in mind that we are performing iterations. Also, there is one case here, the exception from the first conclusion, that the iteration, the asynchronous redistribution of data is more expensive than the creating of processes. This is because the processes only check if the data redistribution, the asynchronous data redistribution has ended after 2 seconds. And this causes an overhead, well, not an overhead, but that the asynchronous redistribution could have ended before, but until the parents check that it has ended, it is not considered as so. When checking for the balanced mapping, the conclusions are the same. Nevertheless, we have a better performance than with a compact mapping. That is because as with this mapping, it's less common to find oversubscription states. Passing on to a compute mapping with an iteration time of 0.4 seconds, we still find the same conclusions, but a new one arises, and that is that for lower iteration times, the asynchronous redistribution performs better. That is because it is checked more times if the asynchronous redistribution has finalized, and the children can start sooner. Finally, for a balanced mapping with an iteration time of 0.4, we find the best times. That is because we are using a balanced mapping that normally doesn't arise oversubscription, and asynchronous redistribution is also faster as it is checked more times. As I have said before, we are also storing the times of the iterations, as we wanted to check if the asynchronous redistribution is affecting these iterations. Here is some the time for iteration when an asynchronous redistribution is taking place. As can be seen, the iteration time is normally higher than the expected iteration time, which is in purple, and that's because an oversubscription state in all cases. As there are more threads and cores available, and that happens. Well, this happens more frequently in a compact mapping, and it doesn't matter the iteration time. For an iteration time of 0.4 seconds, the same problem arises. Nevertheless, we found that for when this oversubscription state is not happening, the iteration time coincides with the expected iteration time, and therefore the overlapping the computation of the application with the redistribution of data is not affecting the iterations. Passing on to the conclusions and future work. Well, we have an adaptable systematic application which can be used for expanding, shrinking, or migrating jobs. Also, we can, from this application, we can study which reconfiguration mechanisms preferred depending on the job state. And we have found that from these results that right now the best option for expanding the job is asynchronous redistribution, and the best option for shrinking it is the asynchronous redistribution. Nevertheless, it has to be kept in mind that we have a challenge still, that it's the oversubscription, which reduces the performance of both, but more for the asynchronous redistribution. If this problem were to be resolved, we will check again these results and see if the asynchronous redistribution is better in more cases. Also, we want to, in the future work, we want to allow users to indicate a computational function codes for iterations, allow more complex data redistributions. Right now, it's only for a linear array, and to allow a dynamical SDR and ADR. That is, in different times, the same application in different times could have a different amount of data. And right now, it is performance. This data was always constant. Also, we want to allow an emulation of non-iterative applications, and we have to communicate with the resource manager. Finally, we want to make traces from real applications and test to trace make configuration files for our application to see how it performs and if it resembles the real application. So thanks for your attention, and I hope you enjoyed my presentation. And if you have any question, feel free to ask. Thanks.
Thanks, Iker. Anybody have any questions? If not, I have a quick one. You mentioned at the end potentially using real applications. Do you have any idea of what applications you could use this thing for?
To create a trace, as you mean, right?
Yeah.
Okay. Right now we are still studying it for example, one of them is the conjugate gradient. This is one of the first that we want to check. And we are still studying which applications we could check. We are also, for example, seeing for non-iterative applications.
Okay.
Then
I had another question too. So with regards to the asynchronous redistribution being slower, do you think you could improve that by adding an interrupt or something rather than checking at the end of when a task is done? Could you check more frequently by adding an interrupt or something so that when the asynchronous reduction or when the asynchronous redistribution was done, the application would know that before having to wait?
Yes, we have also I have also think about that, but the thing is that still you you will have one problem is what you do with, say, iteration that is being performed. That is, if you think that with some newer processes, the application will be faster and the variable data is valid, you could go to the children. But if you're not sure about that, it could be better to just finalize that iteration and then change to the children.
Yeah, makes sense. I see. Okay. Anybody else have any questions? Okay, I don't see any. So thank you again, Iker. And that ends the session. We'll rejoin at 3:30.
Could the session chair for the upcoming session let me know whether my screen and video look good and audio is good?
I'm not a session chair, but it looks good to me.
Thank you.
Okay, it's time for the next session. Welcome everyone to this session on GPU computing. We're gonna start it off with a talk by Phil Miller, former PPLer now of Intense Computing. And I'll just go ahead and hand it off to you, Phil.
Thank you, Zane. Hi, so I'm Phil Miller. Today I'm going to be giving a talk on using concurrent GPU streams to support independent progress of asynchronous objects. So this was work done on behalf of Sandia National Laboratories, and most of the other folks involved in this are staff there, or in Matt Betancourt's case, he was on staff and then left, continued working as a contractor for a little bit, and he's now at NVIDIA. The motivating example for the work that we're going to be talking about today is a kind of bucketed sorting kernel. So this comes from a particle in cell code that has a lot of different reasons that it might need to sort the particles that it's operating on. And so this gets called in a number of different places in the code. Some of them are for performance optimization, some are for support of particular physics features, but it appears in a lot of places, so it's fairly performance critical. So the sorting key for any given particle is primarily which cell in the mesh it lives in. So in our case, it's an unstructured mesh, but the same kind of issues apply equally well between structured and unstructured. And I'm actually also working on, in a different project, a structured mesh pick code. So the important trait for the benchmarks that we're running and the problems that we're trying to solve is that there's a very unbalanced distribution of the cell that individual particles live in. So some cells have many more particles than others. And what we found in earlier work on this sorting kernel is that traditional vectorized algorithms like radix sort end up not performing very well on this. And reasons for this roughly come out to many threads on the GPU end up idle while others drag on because of the kind of segmented partitioned nature of the sorting being done. So this ultimately scales poorly as the particle count increases and as the simulations get more dynamic. So we really need to be able to improve on this. It's also helpful to note that the sorting kernel actually ends up being a good proxy for other relevant physics kernels in the application that have similar impacts of imbalances in particle counts on a per cell basis. So an early micro benchmark that we did on this found that when we take on a single process, if we take all of the elements of the mesh and consider all of their particles at once and try to sort them, first by what cell they're in, and then by other subsidiary per particle attributes, we get the sorting kernel runs in about 100 milliseconds, 112 milliseconds. And when we over-decompose that into 8 chunks of the mesh, without using any streams or other optimization techniques described here, we end up going 22% slower. It takes 143 milliseconds. And so the reason that that occurs is that the decomposition into multiple chunks on a single process that are going to be dispatched to a GPU one by one is that we increase the effective load imbalance. That when we were running just one chunk, the GPU could dynamically schedule threads for cells that had lots of particles to keep running all together. But when we decompose to multiple chunks, each of those chunks suffers the maximum imbalance from the most filled cell within that chunk. So we end up exposing more imbalance by decomposing. So we have lots of reasons that we want to decompose that everyone in this workshop is well familiar with. This is the unit of load balancing and of asynchronous execution and so on. So we really need to be able to solve this problem. So our big picture goals for a solution to this problem is that asynchronous objects should make independent progress. And in general, on the CPU, we kind of take that for granted here. But when we're talking about GPUs, that becomes a little bit harder because the most common ways that we see of using GPU kernels has the handlers that these objects are executing, the entry methods or equivalent, end up blocking on GPU progress at various points within the method. And that means that the CPU is going to be tied up waiting for individual GPU kernels to finish. And so we end up not actually making independent progress because each object blocks on its own kernels getting all the way through the GPU from launch to completion. So our second goal is to use the available GPU capacity well. We want to, given that we're running on very expensive hardware and we're trying to ultimately get the best performance out of the system, we want to make sure that we're not leaving performance on the table. Next, we want to have a low impact on the physics folks actually writing the application code. So we want to make it easy for them to work with whatever adaptations we make. We could always hand code all sorts of asynchrony and then have a code that's completely impossible to understand or modify going forward. And finally, and this kind of ties into the physics developer, we want strong ecosystem integration. So we don't want this to just be a one-off solution for an individual application, but we want to build kind of facilities that are going to be portable and applicable for other applications in the future. So the capsule summary of the ecosystem that we're dealing with involves NVIDIA CUDA, which we've heard plenty about over the course of this workshop, Cocos, which has maybe gotten some passing references in some earlier talks. So Cocos is a performance portability abstraction library for disparate node architectures. So that includes multi-core architectures with threads or OpenAPI. For parallelism, it also includes GPUs of various sorts from Intel, NVIDIA, AMD, and so on. And it's expected to also include backends for future emerging offload accelerator types of devices of various sorts. So Cocos is widely used in DOE national laboratory codes, particularly from Sandia and Los Alamos. It's heavily used in the Trilinos solver stack that contains lots of unstructured mesh and linear system equation solver packages. And there's a similar abstraction library called Raja out of Livermore that would have similar considerations to Cocos. And the final piece of the ecosystem puzzle that we're going to be looking at today is the Dharma virtual transport runtime. So that's kind of similar in its role to Charm++. It provides a distributed memory, asynchronous multitasking framework. And we've had an emphasis on using modern C++ syntax and compiler features to keep the the implementation and the API as straightforward as we could make it. And we've aimed for very close interoperation with existing MPI code. So if you want more details on that, there was a talk at this workshop last year illustrating it, and also at one of the supercomputing workshops. So I'm not going to go into too much more detail on Dharma VT background here. So just to give a high-level overview of the things that we're going to do in the work described, we're going to take advantage of modern CUDA hardware that can run kernels that aren't fully utilizing the GPU's execution resources concurrently. So if you have a kernel that spawns 10,000 threads, but 9,500 of those threads exit quickly, and you only have a few tailing along, as exactly occurs in our sorting kernel, it can overlap other kernels along with it, and so get more performance and better utilization of the hardware, and make progress on multiple computations at once. So we're going to, as kind of hinted at, decompose the chunks of mesh and their associated particles to present the sorting as multiple independent chunks, and hence multiple sets of kernels that are going to do the sorting. So we're going to launch the kernels asynchronously. So we're explicitly not going to block any given caller to spin on the CPU polling for the GPU to finish any particular kernel, because that would miss the point of what we're trying to do. To enable the actual concurrent kernel execution, we're going to need to create separate CUDA streams, one per chunk, and specify which stream each kernel launch needs to occur on. And finally, we're going to context switch among chunks so that at the point where they would have blocked because they need results from one kernel to be able to set up the next one, we're instead going to switch to running the control logic for the sorting in a different chunk, so that we keep the GPU's pipeline full. So the changes that we're making, and I'm just going to kind of work through the different layers of the stack here. In the VT runtime, we're adding threading. So previously, execution was purely driven by asynchronous message handlers, essentially entry method driven execution. And VT largely is still going to be doing exactly that. But the change that we've made is that all of those handlers, other than a few special case low-level bits inside the runtime, are running in user-level threads with their own instruction pointer and with their own stack. So this is the equivalent of Charm++ threaded entry methods, essentially. So we have support for suspend and resume of these threads, and they're cooperatively scheduled and initialized when a message handler comes in. And we're clever about pooling and reusing the stacks and so on. So we try to keep this as low overhead as we can. And just like the threads in Charm++, as they're used for CharmMPI, this is based on some bits of assembly code from the Boost context library to actually do the stack setup and the context switching and suspend and resume and so forth. So another addition that we've made to VT to go along with this is that VT's termination detection mechanism, which is kind of a scoped quiescence detection to make it much more usable in applications. This mechanism now understands suspended threads. So rather than a suspended thread looking like, oh, well, the process is idle, so clearly I'm all done, a suspended thread lets it know that, no, there's still work going on, even if no process thinks that it's actively working right now. So having a suspended thread will delay reported termination and continuation launch of whatever the enclosing epoch, which is what we describe as the kind of scope of a termination. So the other part of VT that's changing is that where the handlers, the entry methods, were previously calling Coco's fence to block their execution until GPU kernel's completed, which was, strictly a blocking operation. The CPU was just going to spin at that point. We've introduced this new object called async op CUDA. And what that does is it will insert a CUDA event on the stream that the kernel is launched on, and it will enter, put an entry in data structures for the scheduler, asking the scheduler to poll on that event, and then it has an action associated with it for when it terminates, for when that event is reached in the CUDA stream, and so the kernel is thus done. So this is, as you can see in some of the example application-ish code, this kind of inlines a lot of the layers here. We're going to launch a parallel kernel on the GPU with this CUDA execution space specified. And so that abstracts what stream it's going to be inserted in for the GPU. Then we get the stream that we just launched the kernel on. And we ask the runtime to block the thread, which will just context switch it out until that kernel and any others on that stream have been completed. So we're inserting this event after the kernel has been submitted, and then we're going to poll on when the stream reaches that event to indicate that the kernel is complete. So similar to suspended threads, termination detection also needs to understand pending CUDA events. So if there's a running kernel on a GPU, even if the CPU seems to be idle, there's still work that's being done as part of the epoch that is the termination scope. And so we can't say that that scope is complete until the GPU kernel is also done running and whatever follow-up has had a chance to resume and run. So finally, we added this API in VT called block on async op. So that just says exactly what it sounds like: block the thread, context switch it rather than letting, spinning a CPU. And it turns out that this is a useful abstraction for MPI operations as well, in contexts where we want to embed MPI calls in VT code. So we have an example of that shown over here. So we, typically this is actually going to be MPI one-sided stuff, not I receive, but it's easier to just show for familiarity here. So we make a call with a setup request, and we create the async op object, and we record it with the runtime, and that's really all that needs to happen, because the user level thread running this handler will be suspended. The scheduler will keep track of how that MPI op is progressing. Eventually, an MPI test will return that it's complete in the status, and then the scheduler can enqueue a resumption of the thread. So the way this plays out at the application level is that we now have a CUDA stream associated with each object. So that means each char or equivalent, and we have some machinery to automatically look that up kind of anywhere up or down the stack, even without passing in the object index explicitly. And then we have wrappers around the Cocos top-level functions, so parallel for and reduce and scan and deep copy and fence to automatically dispatch work to the stream within the particular Cocos execution space instance that's associated with the executing object. And there are some notes about these wrappers that posed some implementation difficulty, that Cocos parallel reduce, for semantic reasons, has a handful of cases where even if you dispatch it on a stream, it will, to indicate that you want it to be asynchronous, it might still block and have synchronous behavior anyway. So we've implemented runtime detection using the Cocos tools instrumentation interface to catch cases where that's happening, so that we can revise those bits of code to not be performance bugs. So the most kind of critical Cocos operation to change in the wrappers was the fence operation. So that's what would normally be used in single stream code to synchronize between the host and the GPU, to require that the sequence of kernels launched up to that point have been completed. So if we're calling it from outside an asynchronous handler in existing application code that's just interoperating with the VT code, we just want that to forward to a normal Cocos fence call. But within an asynchronous handler, we don't want to fence at all, because that's exactly the blocking behavior that we're trying to avoid. So instead, we create an event on the stream, as described in the previous slide, and we suspend the thread on that, on completion of that event, and we go on to execute something else. So what this all means is that if code calls these wrappers rather than the native Cocos functions, and makes sure that any operations it does are on the particular stream rather than the general Cocos defaults, then they can run as non-blocking threaded code. So it stays as straight line code without anything special changing the control flow of that code. So the application developers don't really have to see a big semantic change. They just have a syntactic change to call the wrapper implementations instead of the straight into the library. So this is very similar to what Professor Aiken showed in his keynote talk of replacing import NumPy with import legate NumPy. You make a tiny syntactic change to get meaningful behavior changes. So you get a good programmer productivity for the application side people. So because we actually do need to change call sites here, though, there are thousands of these call sites in our application code base. So we obviously can't go through and manually change every single one of them. That'd be extraordinarily tedious. It'd be error prone in various ways. And so that's just not really an acceptable approach. So instead, we developed a C++ transformation tool using the Clang libtooling library. So this lets us parse the source code and do localized rewriting to convert calls from the Cocos library to calls to our wrappers. So this is kind of a bit of sample code of how we would do that. As you can see, it's not all that complicated, and this is generally available with any Clang installation if it's a full build of LLVM. So we do this in kind of multiple passes. The first pass turns asynchronous Cocos calls into asynchronous wrapper calls. And then we have a second pass that detects the pattern of an asynchronous kernel call immediately followed by a fence. And we turn that into just a call to our blocking versions of the wrapper that have the fence internally. And that's just essentially a syntactic simplification so that we don't have 1,000 fence calls scattered throughout the code everywhere that you need to block. So there were also some changes in the Cocos library itself in support of this work. So there were various data structures and library operations that embedded kernel launches inside them, but had no way to specify that those kernels should run on a particular execution space that abstracted and encapsulated the CUDA stream. So we went through the ones that the application was using and added arguments to pass those through to those. And those are all in upstream CUDA now, or upstream Cocos now. We also added some improvements for some containers that the application code uses heavily, where the deep copy operation, which is copying data from one array to another, didn't really make it easy to use the asynchronous launches with a particular execution space to enqueue on a stream. So we added some interfaces to simplify that, and it ended up being just a net improvement to the Cocos code as well. So the Cocos folks were quite happy to accept that. And finally, this was kind of a change made to Cocos inspired by our requests and similar requests from other people for a portable way to do the semantic equivalent of stream creation for all of the various backends that Cocos supports. So this resulted in the partition space function. And so we ended up doing our own thing when we wrote this code, and then partition space appeared in upstream. And so we're going to move to using that so that we'll have portability to more than just CUDA by the time this moves forward to production. So here are some results from our work. So the first two rows are the same benchmark results I showed earlier. So this is 1 million particles with 30 particles per element across the input, but the input within a given chunk is completely scrambled. So there's no initial ordering to the particles. They're a complete jumble. So as we saw earlier, if we just chunked up the mesh and didn't use streams, we got a slowdown. But now with the changes we've made to use streams and the associated non-blocking kernel launches and context switching between chunks to launch kernels concurrently across streams, we're now a little bit over 2x faster than the baseline. And so that means that in addition to eliminating the overhead that we were originally paying to have support for load balancing and so on, and overlapped communication and computation, we're now actually improving performance for this kernel, and this is an indication that we can expect other kernels affected by the same sorts of issues to also see a substantial improvement from the decomposition rather than an overhead. So our application adaptation is still in progress, just because it's a much bigger code than this sorting micro benchmark, which was, I think, like 200 lines. But we're working through it, and we hope to have results on that soon, which we're probably going to write up and get published. So we'll hopefully have a nicer reference for this in coming weeks and months. So looking back at the goals that I mentioned earlier in the talk, so asynchronous objects should make independent progress. We've definitely achieved that. And I don't have the screenshots here, but we've confirmed this in profiles as well. This isn't just, you know, a caching effect or anything like that of, you know, changing chunk size. Using available GPU capacity well, it's still kind of to be determined whether we're really hitting that. We're definitely using it better than before, but there's almost certainly room to improve this sorting algorithm to make even better use of the GPU. And hopefully those improvements will synergize with our changes here rather than kind of conflicting with them. So low physics impact, we're pretty much happy with how that's gone. The application, for various reasons, was going to have to introduce wrappers for Cocos kernel launches anyway, and had in fact already introduced wrappers for Cocos data structures of views and so forth for memory location reasons. So this is not, the need for wrapper calls was not considered a big deal. And finally, ecosystem integration. This is all, you know, integrated in VT and Cocos upstream versions. It's not one-off to the application. So we have kind of a repeatable methodology for achieving this. So with that, I will wrap up there and invite any questions that people may have.
Thanks, Phil. That was really great and interesting work. I think we have time for one quick question. Nikunj, would you like to unmute yourself and go ahead?
Yeah, really nice talk, Phil. I had this one quick question. You're using Clang tools to sort of parse the whole file and then change the names of the functions and so on. Did you try overloading the functions and sort of dispatching, sort of method dispatching that way?
So we thought about doing something like that. We definitely wouldn't want to add overloads directly in the Cocos namespace because Cocos already uses fairly complex overload sets for a lot of different things internally. But that does bring up an idea that we could potentially use argument-dependent lookup and overload in our own namespace to pass our modified policy objects to, you know, that specify the streams to do the wrapping. The challenge there is that there are a lot of places in the code right now where there are Cocos calls that, rather than passing an object as the first argument that kind of specifies what stream it should run on, and so on, it's a very simple call that just says parallel for, you know, of n iterations of the loop, and here's the body I want to run. So there's no argument with a type of hours that we control that we could overload on that would ensure that our version gets called. So we would have to do some source level transformation for that. And we decided that it was preferable to transform the name, you know, the symbol that's being looked up for the call and still take the simple integer argument rather than transforming the arguments, which at all call sites, you know, which would then make simple call sites more complicated for the application folks. Does that answer your question?
Yes, it does. Thank you.
Great. Yeah, thank you for the question.
I actually have one quick question as well. Thank you for the great talk, Bill. So yeah, I was wondering, because this seems like in the same vein as the work that I did for synchronous completion notification that I presented as a poster back in SC17. And we also kind of published a paper at ESPM2 last year. So I was wondering if you had to look at those. I'll provide links to those if you haven't. Yeah.
So I did see the paper from ESPM2. It's definitely very similar work. I kind of regret that I hadn't been familiar with it before we put this presentation together. So I kind of went to check for that as we were getting ready to write this up and saw that that was there. So yeah, it is very closely related work, and there's probably ideas in there that would inform how we evolve this going forward. And maybe there's stuff in our work that can inform your approach going forward as well.
Yeah, so I was
I'm looking forward to your talk right after this.
Yeah, sure. I'm only going to talk briefly about that, but I was wondering if you also tried using the CUDA callback feature instead of the CUDA events to kind of do the completion notification.
So yeah. I think, I at least was familiar with the CUDA callbacks. I think we kind of rejected using them out of hand, in part because they require an extra thread inside the process, if I understand them correctly, and that poses lots and lots of problems for us. And we largely found that the events interface didn't seem to create any substantial overhead for our use case, where we were going to be dispatching on a bunch of streams and we could pull on the events kind of sometime later. We didn't care about getting them right away.
Right. Yeah. Thank you for your answer.
Yep. Thank you.
Great.
So I guess I'll hand it off from there.
So I guess I can get started. Let me start sharing my screen.
So I will end my screen share if I can. Did that end it?
Yeah, it seems like it's already gone.
Okay, great. All yours.
Okay, thanks, Phil. All right. Can everybody see the screen?
Looks black so far. There it is.
Okay, great. All right. Thank you, everyone, for coming to the talk. So this talk, I'll be talking about how we can improve the performance of CharmMPI applications on GPU systems. And this will include a variety of topics. So first of all, a brief introduction on how we can run CharmMPI on GPU systems. So the most straightforward way of doing it is the application programmer can have the char objects offloading the computational heavy parts of the application as CUDA kernels to the GPU. But one kind of caveat for when you're doing this is you need to be able to maximize the level of synchrony and minimize synchronization between the host and device to prevent chars from not yielding to other chars. And this is because we have over-decomposition in CharmMPI, where multiple objects can be waiting, on the same scheduler queue, waiting for their kernels to be executed. So you essentially want to use CUDA streams to kind of make the initiation of the kernels to be asynchronous. And also you want to use something like CharmMPI's hybrid API that allows you to, allows the scheduler to kind of asynchronously poll for the completion of the work that you have offloaded to the GPUs. So the first topic that I want to briefly discuss is how you can achieve communication overlap. So this is part of the work that I published last year at the ESPM2 workshop. So basically, the gist of it is that you want to minimize the amount of synchronization in your application, so that you can achieve the maximum amount of overlap. So you can do this by again, like using CUDA streams and also using the support from the CharmMPI runtime system, such as a hybrid API. And another important factor is you also need to prioritize the communication in your application. that are using that are related to CUDA streams. And these also include not just actual communication over the wire, but also things like packing and unpacking kernels, all the communication related operations. So you want them to be as high priority as possible, because you want them to start as early as possible so that you have maximum overlap, and so that you do not have these idle times in between the iterations of your application. And more details about this can be found in the ESPM2 paper that I linked in this slide. And just to showcase a proxy application that we worked with last year. So these are results with MiniMD, which is originally a MPI and Cocos application. So that uses MPI for distributed communication and Cocos for within node computation, whether it be on the CPU or on the GPU. And it uses those to perform electrodynamic simulations. So in our version, we kind of swapped the MPI layer with CHROM++ so that we can do communication with CHROM++ and also use the over-decomposition feature so that we can kind of have this automatic communication overlap. And we retain Cocos for doing the GPU computation, as well as the host to device transfers. So on the top the figures that we can see here, on the left side, we have the weak scaling results on Summit. So the two reference lines are the MPI versions. So the black line, MPI HS, is a post-staging version of MPI where you are kind of moving the data that's on the GPU back to the CPU before you're doing communication. And then, of course, on the receiver side, you have to kind of move it back to the GPUs. And then MPI CEA, the blue line, that's when you use CUDA over MPI. So you don't have to kind of do that host staging mechanism, and you can instead just directly move data between the GPUs. So those two are kind of the baselines with the MPI Cocos implementation of MiniMD. And then we have the CHROM++ versions where we apply over-decomposition. So ODF kind of stands for over-decomposition factor. And of course, we're increasing that factor from 1 to 8 in these plots, where 1 means that your kind of your CHROM++ program is kind of MPI-like, so that you just have one char running on each PE. And then when we go up to 8 over the decomposition factor, that means we have 8 chars on each PE. So you can see that we can get pretty good overlap with an increased level of over decomposition. And in fact, you can see that with an over decomposition factor of 4, which is the purple dotted line on the left side with the weak scaling plot, that we actually are able to achieve even better performance than the CUDA over MPI version, because at this point, especially at the lower end of scaling, where we don't go to like the 38 for GPUs, we can observe almost full communication overlap, and we don't really see any idle time between iterations. But once you go to a larger over decomposition factor, of course, when we have a more fine-grained application, then we kind of start to see these overheads from the finer granularity. And you can see that we kind of lose the performance benefits that we get from over decomposition. And as you can see in the yellow line, that kind of falls behind the performance of over decomposition factor of 4. Then on the right-hand side, we have the strong scaling plots in Summit. So here, the results are also quite a bit more interesting because at lower scales, until about 384 GPUs or 64 nodes of Summit, you can see that over decomposition factor of 4 performs the best and provides you a good level of speed up against the reference lines as well as the lower over decomposition factors. But once you do go to somewhat higher scales, then you also start to see some of the overheads that come from the finer decomposition. And if you look at the larger scale, at the end of strong scaling, where we run on 3,000 GPUs, you can see that the over decomposition actually does not provide any performance benefits at all. And you can see that the over decomposition factor of 1 performs the best in this case. So here, this kind of tells us that we, at the end of strong scaling, especially, there are some things that we do need to look into to kind of have over decomposition be able to perform better, and also give you more communication overlap. And then moving on to GPU communication, how that's supported in CHROM++. So GPU communication is kind of important for 2 big reasons, I would say. So one is productivity, because instead of users having to manually move the data between the CPU and GPU, it can instead provide GPU buffers directly to the communication APIs, whether it be AMPI or CHARM++ or some other communication layer. And also, more importantly, for performance, we can directly transfer data between the GPUs without having to go through the host memory. And the underlying technologies that are used for this are CUDA IPC and GPU Direct in the case of NVIDIA GPUs. And this is the technique that is used in libraries such as CUDA or MPI. So how do we do this in CHARM++, right? Achieving GPU or communication? And not only CHARM++, we also want to achieve the same thing on with adaptive MPI and CharmMPI, which are the other parallel programming models that build on CHARM++. And we also want to retain the message-driven execution model of CHARM++ in these models. So our approach is to build on the GPU support feature in UCX, because CHARM++ already had a UCX machine layer that supports communication with the UCX library. And we can kind of use the UCX machine layer as a foundation to support GPU communication for all the different parallel programming models in the CHARM++ ecosystem. But one caveat here that we have to work with is that the UCX tagged API, which is the main API in UCX that supports GPU communication, they only cater to MPI send receive semantics. And UCX also does have active messaging API, which kind of fits more with the CHARM++ message-driven execution model. But unfortunately, as of right now, as far as I know, they do not support GPU support. So just to recap how the messaging API works in CHARM++. So we have two chars in this case. So we have the sender's char that is trying to send some data to the receiver char at the bottom. So in the foo entry method of the sender char, it's sending a buffer of 1K doubles to a peer char that is the receiver char. And so that means when the user application makes that call, the data that's on the host side, because this is just a CPU-driven CHARM++ application, that buffer gets packed together with some metadata that has information about the target char and also the entry method that needs to invoke on the receiver side. And once the message is built, it will get sent to the receiver char, the message queue of the P that the receiver char resides on. And once that message is picked up by the receiver PE, then it will execute that method that is encapsulated in this message. And in this bar method, it will have access to the received data in the host. But if we go to the GPUs, so we have built this GPU messaging API to kind of facilitate GPU communication. So in this case, instead of trying to send some data that's on the CPU memory, we want to send something that's inside the GPU memory. So in this case, we have the user wrap the GPU buffer around in the structure that we provide called the CK device buffer. And this structure is also retained inside the CHARM++ frontend system to keep track of this communication. And so this API kind of builds on the zero copy API so that we can preserve the message-driven execution model. But since the chars and the scheduler are all running on the CPU, we still need that metadata so that we have the necessary information, which char this message is targeted and which entry method it wants to invoke, things like that. So we essentially pack this metadata with the other potential host side data that the user might want to send. So that's kind of encapsulated in the step 1 here in this diagram. And then we, at the same time, when we send this metadata message to the receiver, we also send the GPU buffer separately by kind of routing it directly to the UCX APIs that sit inside the UCX machine layer. So there are kind of like these twofold sends of the metadata message on the host side and the send of the GPU buffer. And on the receiver side, once the host side metadata message arrives, the scheduler, it will pick it up and it will see that it's a GPU message. And at that point, it will post a receive for the incoming GPU data so that it can receive that GPU buffer. And then once that GPU buffer arrives, it will invoke the final entry method, which is the regular entry method that is part of the zero copy API. And at that point, when the regular entry method is called, the user is ensured that the GPU data has arrived on the receiver. and can use that data to, invoke GPU kernels or do other things that the user wants with the data. Okay, I'm seeing some comments in the chat. Okay, so there was one question. Okay, yeah, let me just continue with the talk here. Yeah, so with so as you can see, kind of in this GPU messaging API, there's this metadata message that is involved in this, right? That kind of delays the posting of the receive for the incoming GPU buffer. So this is kind of necessary to retain the message-driven execution. But for some applications that don't necessarily need the message-driven execution for their communication parts, at least, we want to support those cases as well, and with with minimal adversarial impact on the performance. So we also came up with an API called the Channel API. So this is kind of similar to the Channel API in CharmMPI, where channels can be constructed between a pair of char objects, and these char objects can use this channel object to send the data, just the data and not any control flow. So that is kind of similar to the send and receive semantics in MPI, where you just have explicit sends and receives of the data that you're moving around. So this allows us to kind of reduce the overhead from having to delay the post for the receive in the previous GPU messaging API that's built on top of the zero copy API. But again, this only allows you to send around data and not the control flow. And this API allows you to use either the features API in Charm++, or you can also pass a callback object, in which case the runtime system will track this communication and invoke that callback when the data transfer is complete. And this feature will be part of the release 7.1. So just to show you what the performance looks like with these GPU communication features. So on the left side, we have the latency plot, and on the right side, we have the bandwidth plots. And these were performance evaluations done on Summit at Oak Ridge. So the baseline is the blue lines, Charm++-H. So they just mean that we're kind of moving data back and forth between the GPU and the host to do communication. Whereas in the zero copy API, that's the GPU messaging API in the red line, that allows us to retain the message-driven execution, but utilize the UCX messaging API underneath to directly transfer the GPU data instead of having to move it back and forth between the host and device memory. And the channel API in the green line is the performance that we've seen in the last slide, where we can only move the data around. That allows us to kind of improve performance. And you can see that the channel API does reduce the latency further from the zero copy API. So one thing we also want to explore is we want to combine the computation overlap work that I just described with this GPU aware communication, because at the time of the computation overlap work, we did not have this GPU aware communication feature. So we want to kind of combine these two together and see if that helps us, especially at the end of strong scaling. And you can also find more details about this in the Ashes 21 paper that we published this year. Okay, and moving on to the more, I guess, research-driven topic, which is Charming, a short for Charm++ and GPUs. And this is aiming to kind of build a GPU resident runtime system. So that allows us to run everything inside the GPU without ever going back to the CPU during the execution. So the motivation for this work is that the computation is moving to the GPU, but the program flow and the communication are still mostly driven by the CPU. We still have these overheads from the interactions that are necessary. These include the synchronizations that needs to happen between the CPU and GPU, as well as the data transfers. And also we want to effectively utilize the upcoming direct connections between the GPUs and the NICs that will be available soon in machines such as Frontier. And so the hypothesis that we kind of want to evaluate is, can we improve the performance by moving the entire execution to the GPU, right? All of the scheduling mechanisms and the messaging, all of those mechanisms as well, moving them to the GPU, if that will help us in achieving better performance. So a notable related work in this area is Juggler, which has been published at PPOP 2018. So this juggler paper employs a per SM task scheduler. So we have a task scheduler that is running on each of the SMs of the GPU. And then so this is kind of a task-driven model where the task dependencies are resolved on the fly and entirely on the GPU without ever going back to the CPU to fetch tasks to be executed. But the main limitation of this work is that it's limited to a single node. And also it's not quite modularized. The runtime code is kind of tied together with the application, so that you need this duplication for different types of application where you have to duplicate the runtime system code across the different applications. So charming, again, short for Charm++ and GPUs. So the goal here is we want to develop a fully GPU resident runtime system, but using the principles of Charm++, and those include over decomposition, allowing the user to have multiple logical objects mapped to each scheduler instance, and also adopt asynchronous message-driven execution, which gives us benefits like communication overlap, and also migratability, so that we can move objects around for load balancing and potentially for fault tolerance as well. So we want to enable these adaptive runtime features without doing any interaction with the host CPU during the execution. So we do have a working prototype that I'll briefly explain in this following slide here. So these plots show the diagrams show the system design of charming. So on the left side, we have the current prototype, where we just have a single scheduler instance running on each of the GPUs. So we treat each GPU device as a processing element. And of course, we map chars to these schedulers. We can have multiple chars per scheduler. And each scheduler looks at the corresponding message queue to fetch the messages that are targeted for the chars that are mapped to the scheduler. And the communication between the GPUs, or the Ps in this case, happen with mbishmem, which, as far as I know, is the only communication library that allows you to perform GPU-initiated communication. And on the right-hand side, that is the future design that we're kind of working towards. So that is a more complex design where we have a more flexible scheduler design. So instead of confining a scheduler to be just one instance per GPU, we can have one scheduler per SM or a subset of SMs, one scheduler per 2 SMs, for example, so that we can kind of have this flexibility and in assigning the schedulers to the SMs, and also the flexibility in moving objects around these schedulers. So in this case, we kind of need this hierarchical structure of message queues as well, so that we want to have a GPU-wide message queue that kind of aggregates all the messages that are targeted to a certain GPU. And then we might also want message queues that are specific to each scheduler instance. And if we want, and for the communication between the schedulers that are in the same GPU, we want to use global memory and atomics to perform that communication. So digging a little bit deeper into the scheduler design. So currently it's designed as a persistent kernel, and we just utilize a single thread per GPU, which is of course not ideal, but that's just the first step in this design. So when we want to start off the user application, we do that with P0. So using thread 0 on GPU 0 to execute the user's main function. That's also written as a device function, executed entirely inside the GPU. And that main function will create the char objects and spread it out across the different schedulers, the Ps in the system, and then initiate the program flow by invoking entry methods, just like in Charm++. And then all the Ps in the GPUs will keep receiving messages and executing the entry methods until the termination. But one kind of feature or capability that we have to worry about is that the users will write, the users can have these separate kernels to enqueue new work that is data parallel on the GPU. And currently we handle that by launching the user's new kernels by using CUDA dynamic parallelism that allows us to launch new kernels from other kernels inside the GPU so that we can perform the user's data parallel tasks inside the runtime system. And also looking at the message queue that is implemented here currently. So it's currently implemented as a multi-producer single consumer ring buffer because we have to work with a fixed mbishmem allocation that is allocated before the invocation of the scheduler kernels. So that's also a limitation of the current design. So yeah, so we use this space as a ring buffer. And how this works is that the producers, which are the remote PEs that will want to kind of put messages in the target PE's message queue. So the consumer is the target PE or the scheduler on the target PE. So first, the producers will try to acquire space in this message queue by using enrichment atomics. And then once they do acquire that space, they will transfer the actual messages by using the one-sided put operations in the enrichment. And the consumer, which is the local PE or the scheduler, will consume the messages in this ring buffer starting from the lowest address. And we're also looking at the single producer, single consumer queue based implementation, because the current MPSC implementation requires a lot of atomics that is kind of degrading performance. But of course, the SPSC based implementation will trade off more memory usage in terms of, because we will need like an ON squared memory usage in terms of the number of PEs in the system. But we'll be able to, we'll just need less number of atomic operations to send the messages. So we're kind of evaluating the two different mechanisms here. And this code block shows you how you can write the Jacobi 2D proxy application with charming entirely in the GPU. So the syntax is not super clean. We're still working on making it more clean. But on the left-hand side, we have, first we have the GPU kernel that would seem very familiar to those of you that are familiar with CUDA, that the user application programmer will use to invoke the data parallel Jacobi iteration work. And on the left bottom, we have the definition of a block char that kind of represents a block of the two-dimensional grid that is simulating. And you can see that similar to Charm++, it has the various entry methods and constructors. So the send boundary function here is essentially not really an entry method, but just a member method of the block char, where it will try to send its boundary data to the neighboring char objects. And the receive ghost function is the entry method that will be used to kind of receive the incoming GPU buffers from your neighbors. So that's also kind of straightforward. And once you receive all the ghost data from your neighbors, you will perform the update function. And that will execute the new Jacobi kernel, which will be executed using the CUDA dynamic parallelism feature. And one potential kind of drawback to performance here with this approach is that we need to use the CUDA device synchronize call to kind of ensure that this newly launched kernel is completed before we move forward. So that's also a potential place we want to fix to kind of improve the performance and minimize the level of synchronization needed in this application. So that's the Jacobi 2D proxy application, how it would look like in Charming. And then this is the preliminary performance, so it's not great. So this is running the Jacobi 2D proxy application on the last computer at Livermore, using up to 64 nodes or 256 B100 GPUs. So we're comparing the performance Charming against MPI, which uses non-blocking CUDA or MPI to kind of also overlap computation and communication together. And as you can see on the left side, we have the weak scaling, and on the right side, we have the strong scaling plots. So we have a lot of room for performance improvements. And we believe that most of the source is coming from the communication as well as the runtime system overheads, because we're just utilizing a single thread for the scheduler. So there's a lot of room for performance improvements here. So the current status of this Charming GPU resident runtime system work is that, that we have a prototype working on NVIDIA GPUs. So we're currently using C++ templates to support user-defined char types and enrichment for device-initiated GPU communication, and for the dynamic parallelism to launch new kernels. And in terms of future work, like I said, we want to have much better performance. So we want to analyze and improve the performance by looking at the various stacks of the runtime system, such as the communication layer, the scheduler, and the launching of user kernels. And we also want to explore computation overlap, which we believe would be a major benefit of this approach with over-the composition. So in summary, just to kind of recap everything we talked about in this talk, I've talked about the GPU features that are available in Charm++. That allows the Charm++ programmer to utilize synchronous execution and completion notification using CUDA streams and hybrid API, well as a GPU communication using two different APIs, GPU messaging API, which should be available right now in the current release of CharmPlus Plus, and the channel API, which will be available in a future release. And Charming, which is a research-driven topic of utilizing GPUs to be fully GPU resident and running a runtime system there. Yeah, so that's it for my talk. Thank you for tuning in. Please let me know if you have any questions.
Thanks, Jaemin. That's really exciting work. Are there any questions from anybody in the chat? I don't see one, so I think I'll go ahead and ask one that I have. Do you have the sense for maybe kind of the best case performance of Charming? Do you have kind of a...
Yeah, so if we are able to, in an ideal case, we should be able to like utilize most of the threads or many threads in the GPU to do the scheduler execution, so that we can kind of process messages in parallel. That would help a lot. And then we also want communication to be much faster. And in the case of MVishMem, it's comparable or even faster at times to CUDA AMPI. So there we see like a 2 microsecond ping pong time. But of course, we would have the runtime system overheads here with Charming. So I expect that to be roughly in the 10 microsecond range or lower. But yeah, if we are able to like fully utilize the GPU instead of this kind of single threaded approach that we have now, we should be able to fully utilize the computational kernels, which wouldn't be any faster than a CPU driven approach. But we would expect the communication and also the runtime system mechanisms to be much faster than the CPU-driven ones, because we don't have to move data around between the CPU and GPU, and we don't really need any synchronization between the two, which often has to go through this expensive PCIe bus. Yeah, so that's kind of what I would expect to be ideal performance for this work.
I see. And do you think that there could be any productivity benefits to this kind of unified on-device approach, as opposed to CPU plus GPU?
Right. Productivity-wise, I think the best we can do is similar to CharmPlus+, because I think CharmPlus+ already has a pretty good productivity. And as you can see, the syntax that we have now is kind of, because of the limitations of a totally GPU-driven approach, I think it's kind of worse than what CharmPlus+ can provide right now. But yeah, ideally we want to be, at least as good as CharmPlus+, a CPU-driven CharmPlus+ in terms of productivity.
Okay, sounds good to me. Thanks, Jaemin. Wait just another moment if there are any last-minute questions, but if not, then I think we'll go ahead and take a break. We're just gonna cut this next break short. So we'll still return at 4:45, and when we get back, we'll have a session on applications, and then we'll have a bit of a discussion on CharmPlus+, new features, and hope to have a good discussion there. And then we'll have a few closing remarks from Sanjay. But we're gonna hit the break now. So thanks everybody. This was a good session.
All right. I think we should be ready to start the next session. So Eric, are you here?
Yep.
Great. Yeah, so we'll start with Eric Mikida's talk. Eric is from CharmWorks, and his talk will be on XM2M, a scalable mesh and adaptive mesh-to-mesh transfer. And please go ahead, Eric.
All right, let me just share my screen. All right, can everyone see the presentation? Hello?
Yeah, looks good.
Okay. So yep, like Jaemin mentioned, I am Eric Mikida. I work at CharmWorks, and I'll be doing a brief presentation today on XM2M, which is our scalable and adaptive mesh-to-mesh transfer library. So the library is originally being written as part of our collaboration with the Quinoa team. As we saw a little bit yesterday, Quinoa is developed by Joseph Picosi at Los Alamos. It's a CFD application developed in Charm, and their long-term goal is to combine CFD with structural mechanics. And a big part of that is going to be using parallel collision detection for performing mesh-to-mesh transfer, which is where XM2M comes in. So XM2M is going to be our Charm++ based library for transferring solution data from one mesh to another by interpolating from the source mesh points to the destination mesh. The sequential algorithm was developed by Joseph Picosi, and the parallel implementation is being implemented in Charm as a collaboration between us and Joseph. And it also utilizes an existing collision detection library in Charm++ that was written a number of years ago, and we're now sort of reviving it and repurposing it for this purpose. So the basic algorithm has 5 steps. The first step is setting up the mesh data. Originally, we wrote XM2M just as a standalone application as a proof of concept. So you just read in the meshes and partition them with Zoltan or something like that. And then store those meshes in char arrays. We've recently converted it to also be executed as a library. So now you just receive mesh data from the calling application. Then once you have this mesh data, you pass it to the collision detection library. So you take the bounding boxes for the tetrahedron of the source mesh, which is where you already have your solution values, and send those bounding boxes to the library. You also send the bounding boxes of the vertices of the destination mesh, and then the library will return you a list of potential collisions. Then we redistribute these potential collisions to the destination mesh, where they fill in their actual vertice data. And then we send those vertices to the source mesh, and the source mesh does the actual more fine-grained collision detection to determine which ones actually collide, and then do the interpolation for the solution and return that value to the destination. So mostly what we've focused on so far, and what I'll be talking about mostly in the talk, is the collision detection library and its use in Charm++. And so basically, what I just described is an example of 2-phase collision detection. Phase 1 is the broad phase. We do sort of quick and dirty collision detection, just checking for bounding box collisions. It's a very general case, and this is what's handled by the Charm++ collision detection library. It's quick to determine potential collisions, but the collision detection isn't super accurate. For example, in the little shapes I've shown there, we can quickly rule out the star as not colliding. However, the circle and the triangle look like they may potentially collide because their bounding boxes overlap. Then phase 2, that is the application-specific part. So that is what XM2M is handling, which is the narrow phase. There we weed out the false positives from phase 1. It's more expensive to do this collision detection, but again, because we've already weeded out a lot of false positives, a lot of non-collisions in phase 1, we should have a smaller list to check through. And in this case, we had to rule out the circle, and we find our collision between the triangle and the parallelogram in this case. So again, the broad phase detection uses the collision detection library in Charm++. So this particular library was actually written I think over a decade ago at this point. And there's applications for collision detection in computer graphics, physics, robotics, a bunch of different domains. But in our case, we're actually, instead of checking for collisions per se, we're checking for overlap between two meshes. And this slightly different use case has caused us to reevaluate certain parts of the library, which I'll get to later. But basically how the library works is based on the principle of voxels. So voxels are just regular cuboids in a 3D grid. And so as the library gets past a bunch of bounding boxes, it distributes these bounding boxes to the voxels. The voxels are a char array in this case. So just like with any Charm++ program, these char array elements are spread across your execution domain. And they're also populated on an on-demand basis. So when you start out, the library has no chars in it. And then as you pass it these bounding boxes, the chars automatically get populated. But that also means that if you have no objects in a particular region of space, then you won't end up creating chars in that particular space. As shown here with the little hole in the middle there, no chars needed to be created in that particular part of the grid because there are no objects that overlap. So once the voxels are populated, then in step 2, we can do the very cheap and quick serial collision detection. So each voxel will run through its list of elements that it knows and do collision detection using bounding boxes. So in the particular example on the right, a bunch of these voxels can automatically they basically have a no-op because they only know of one element, and we're left with these bounding boxes doing just a few quick checks on the elements they know. Step 3, once we've gone through that and we have a list of potential collisions based on their bounding boxes, we can then do a reduction to concatenate this global list and return this list to the caller for further processing in their narrow phase computation. So then the narrow phase, that's where we transfer back to XM. We now have a list of potential collisions. And again, in this particular case, we are colliding vertices with tetrahedron, or in this case, triangles for a simplified view. So what we show here on the right would be a potential example. So each destination mesh char, which has the vertices that are potentially colliding, sends these vertices out to the elements of the source mesh, which has the tetrahedrons. And then the source mesh would determine what the actual collisions are. So in this case, the 4 vertices I've shown are the ones that are actually colliding. The other ones only collide based on bounding box. And then the source mesh can take the data from its points, its vertices, and interpolate it to the vertices of the destination mesh and send that solution back. And we have our interpolated solution. So that's the basic principle behind the two-phase algorithm. The broad handled by the Charm++ collision detection library, the narrow occurring within XM. So in the last workshop, we had some initial results without any actual scaling data. We just pretty much had run for correctness with 2 48 million cell meshes. In this particular case, we were doing an overlap between a sphere inscribed within a cube. And now we've gone a little bit further and gotten some scaling results here. And based on those scaling results, had to make some tweaks to the library. So we did runs on the Cori machines on up to 2K cores. And here are some examples from our strong scaling of those 2 meshes. So basically 3 things we get out of this plot here. So this is just showing as the core count increases what the execution time is of 4 different parts of the algorithm. So the first part, the blue, is the compute portion of the broad phase algorithm. So that is within the Charm++ library. That pretty much just entails the creation of the voxels, the sending of the bounding boxes, and then the local checks inside the voxels for where the potential collisions lie. And as we see from this plot, that part scales pretty favorably. The problem we see here is actually in the red and yellow portions of this graph, the red being that large global reduction to gather up the list of potential collisions into one master list. And then the yellow is actually the sequential processing of that list. Basically how the library was written when it was written a while ago. The list would be sent back to processor 0, and then it was up to the application what to do with that list. So in our case, we went through that list sequentially and parceled out each collision based on which mesh element it was dealing with, and then sent those back out to the mesh elements. The fourth part here is just the narrow phase, which for the most part doesn't particularly scale, but is also generally a negligible part of the computation, except for when we hit the higher core counts, that part of the computation blows up, and that is something that we are still currently looking into. But for this part of the talk, I want to focus on the sequential bottlenecks we see in the yellow and the red portions. And again, here is just the compute of the broad pulled out into just a regular log-log plot to show that the scaling is generally, again, pretty favorable up to 2K cores. And at that point, we are probably, we suspect, starting to hit the limits of we just have too little work for the cores to do. And there also may be some load balance problems, which is another thing that we'll be looking into in the future. So how do we choose to deal with this bottleneck? And why does this bottleneck even exist in the first place? So like I said at the beginning, the collision detection library has a number of different use cases. But with its original inception, those use cases all generally were looking for collisions as some sort of unique phenomenon they were trying to detect in some sort of simulation. And so these collisions were expected to be very few in number if they occurred at all. And so when you're doing a reduction to make a global list of just a handful of collisions and then processing that list, that didn't cause a bottleneck in any of its original use cases. However, again, for mesh to mesh, especially in the example we showed where we have the circle inscribed in the cube, we generally expect potentially millions of potential overlaps. In this case, the sphere being the destination mesh, we expect all of its vertices to have potential overlap, and we're just trying to determine where exactly they overlap. So for our particular use case, doing this sequential processing of the results is not really feasible. And on top of that, the consumers of this data, the mesh data itself, is already going to be distributed. So we don't need to centralize this data just to immediately send it back out. So our solution for now was keep the results distributed across PEs, so modify the Charm++ library so that each PE, when it does its local checks, it keeps those results and then we send them out from there. And so after making some of those changes earlier this year, these are some new scaling results we got doing similar runs on Quarry with the same meshes. So here again, we have the red line being the ideal. And then the blue and the green curves are the important ones here. The blue is basically the entire broad phase computation in the centralized scheme. So that includes the reduction and the processing. And we see that it's a pretty flat line that doesn't scale because as we go higher in core count, that reduction tends to dominate. And then the green is the distributed version of that same computation. So now that we've cut out this global reduction and returned the results as they are computed, we again achieved that pretty good scaling that we saw from the broad compute. However, now the total runtime of the entire algorithm, still we see scaling problems. And again, this goes back to that issue we're seeing with the narrow phase where it starts to blow up at the end of the computation. So we've roughly dealt with half the problem. Now we still have the other half to continue to work on. The other issue we're starting to see with some of these results and some of this scaling is a little bit of a load imbalance. So it's another thing we have to look into because just because we have the mesh partitioned well for each individual mesh, even if the amount of elements per PE are roughly balanced, that doesn't necessarily dictate the amount of work done for the collision detection on each PE or the amount of data that then needs to be sent back out per PE. So that's something else we're going to be looking into. Some additional milestones we've kind of hit since the last time I presented on this work, in addition to converting the collision detection library to a distributed reporting. We've also converted XM to an actual library rather than just a standalone application. And so this, again, uses actually some of the stuff that Alex was referring to this morning or afternoon in his keynote. The nice thing about Charm++ is that this library does not depend on where you store the data at all. So by using bound arrays in Charm++, as long as the user has their meshes stored in a char array, the decomposition can be however they see fit. The mapping of the char array elements to the cores can be whatever they want. And then the XM library just creates an array bound to the user's array and can then directly access the mesh data via pointers without any extra communication. And even throughout things like load balancing, if the user's application does load balancing between iterations and the mesh gets moved around, again, the XM chars will move in coordination with those automatically without the user having to care about where their data is. So the library is completely agnostic to their partitioning of the array and their balance and placement of the array for storing their meshes. We've also moved on from testing just the ball and sphere to testing within the entire Kinoa application. And those tests so far have been promising for a single iteration. We still need to add support within the library for repeated calls over multiple iterations to make sure that all the bookkeeping gets correctly reset between calls. We also need to add support for multiple meshes. So Kinoa, in some cases, may have multiple source meshes or multiple destination meshes that we want to do transfers between. And for both multiple iterations and multiple meshes, the basic framework is pretty much already in place. We just need to iron out a few details. And then one of the bigger things we want to do within Kinoa is make sure that the library can operate completely asynchronously. So right now it's partially asynchronous. There's some synchronization required by Kinoa when they're doing multiple instances of the transfers at a time. But we want to eventually move to a place where this can be fully asynchronous. They can send off some calls to the library for mesh-to-mesh transfers and then continue on doing whatever they want. And the library will report the results back to them as they compute other stuff in Kinoa, and that will all work fine. That's also related to the other bullet point I have up there about the library is one thing that is still a work in progress with the library itself is completion detection. So the one nice thing before about the centralized scheme, of course, is that when you did that global reduction to get your full list of collisions, that was also when you knew that the library was completely done and you had every collision. Now, since we are no longer doing that, we have a completely decentralized scheme. The calling application is going to get multiple lists of potential collisions. They'll be getting them from potentially multiple different processors, depending on how the bounding boxes ended up mapped to processors. And so right now, there's not really a great way for the user of the library to know, when the heck is this library done? Is it going to keep sending me collisions, or has it found everything? And so that is something we still need to address within the library version. So future work that we hope to start completing as the year comes to a close is some more large-scale tests on some Kinoa, some larger production runs. Once we sort out these multiple iteration and multiple mesh problems, the elephant in the room obviously is diagnosing what the heck happens in the narrow phase once we start scaling up further. Right now, the narrow phase is implemented pretty naively with just a lot of all-to-all communication. So hopefully we can address that quickly. And then again, some more robust synchronization within the library and load balancing. So one thing that is tricky about load balancing the collision detection library, but maybe aided here, is the fact that it's sort of a one-shot computation. So by the time you realize there's a load imbalance, you've already done the computation. But because Kinoa and potentially other users of this library will be calling it over repeated iterations, we can keep the voxels around persistent. And as the application within Kinoa evolves, the use of the voxels will evolve, and we may get different bounding boxes, but we're hoping we still have some principle of persistence so we can actually load balance within the collision detection library itself, and hopefully smooth out some of those remaining scaling issues. So I think that pretty much covers everything I wanted to talk about today. So if there are any questions, I'll take those now.
So Jaemin had to step out for a second, but I think there are a couple of questions in the chat.
Okay, I don't know where my chat went now that I'm screen sharing.
So whoever wrote in the chat, they can unmute themselves, or I can read the question, whatever they prefer. So there was one question by Zane, I think. What baseline is used for the ideal line?
So the ideal line was just if we get perfect log-log scaling. There's no particular, nothing particularly fancy there. It's just, it was more the slope of the line rather than the actual specific location.
But where does the line begin? At one processor, right? I guess the point is what's the leftmost point there.
Yeah, so the line was generated from what we expect the results to be at one PE.
There was a comment by Phil who said that for synchronization completion, the stuff we've done for termination detection in VT should be a very helpful point of reference. And the code is BSD licensed.
Okay, yeah, that would be very useful, because that is something that for example, if this were built into just a regular Charm++ application, what we would have done, and what we actually do now, just to sidestep it for the time being, is use quiescence detection, just to fully synchronize on that. But we don't want to use quiescence detection within a library if other users of the because then users of the library wouldn't be able to do quiescence detection themselves. So that would definitely.
Hey, Phil here. Our termination detection is fully localized, composable, et cetera. It doesn't rely on any global quiescence property.
Okay, thank you.
Yep.
Do we have any other questions?
Yeah, for that narrow performance issue, could it be that there are multiple chars all trying to work on the same object or voxel, and that communication is just spiraling out of control?
So at that point, once we've reached the narrow phase, the voxels are pretty much out of the picture. I do think it's probably related to communication spiraling out of control, but it's not based on multiple chars working on, for example, the same voxel.
We've actually seen what might be a related problem in a collision detection for solid mechanics application in the Dharma project. And we're implementing something that's kind of an evolution of the ideas of CK cache for the mesh transfer parts for use in the narrow phase. So where you actually communicate the detailed set of tetrahedra or points or whatever. If too many things collide with one thing, then that becomes a big communication bottleneck.
Yeah, I suspect we'll have to look into some sort of caching as well, or some sort of aggregation of messages, because right now, like I said, the narrow is just a very naive, I have a list of points, I'm just going to send my points out to every destination mesh char that needs them, and vice versa. And I could see that blowing up pretty quickly, especially as the chars get more and more fine-grained.
All right, unless there are any further questions, thank you again, Eric, and let's go to the next speaker.
Thank you, Matt, for taking over.
Okay, go ahead.
Yeah. So the next speaker is Dylan Wood from the University of Notre Dame. So he'll be talking about modeling for storm surge and coastal flooding. Whenever you're ready, Dylan.
Okay, thanks so much for the intro. Let me bring up my slides here real quick. Can you guys see my slides?
Looks truncated on my end. Yeah, it looks good now.
Oh no, okay, sorry. I think my computer was just lagging a little bit. Anyway, yeah. So yeah, what I'll be talking about here today is some of the applications we've been using for Charm++ within the realm of hydrodynamics. I'm Dylan Wood from the University of Notre Dame's Computational Hydrodynamics Lab, and we do a lot of work primarily with large-scale meshes of the Western North Atlantic Ocean, and now moving on to a global scale where we're simulating hurricane storm surge primarily, and feeding these models to places like NOAA and the National Hurricane Service for use in flooding risk assessment. So we'll be talking today about the model that was developed by my advisor, and we typically use in my lab, the advanced circulation model, which is based on solutions to the shallow water equations. This is used by several different agencies currently to evaluate storm surge risks. The Coastal Emergency Risk Assessment organization runs a website, cera.org, where there's a screenshot above, where they publish simulations from AdCert pretty much daily for storm surge. And this is a screenshot from Hurricane Ida earlier in August of this year, and the storm surge off the coast of Louisiana. So they're running these very large scale models pretty regularly, and it's very important for them to be able to get their results out in a timely manner. And so, like I mentioned, these are all based on solutions to the depth integrated shallow water equations. It may not seem like these applications are shallow water because we're modeling the open ocean, but when you consider that the open ocean is many kilometers wide and only a few deep, that actually does mean that the shallow water equations are applicable here because it's all about the relation between the horizontal and the vertical length scales. So we have primarily as our solution variables just the water surface elevation and the velocity of the flow. And those things are solved on a grid that looks a lot like this, where there are many finite elements involved, these linear triangular elements, and most of the nodes and triangles are concentrated in the region of interest for the study. So this mesh is applied towards studying storm surge in Louisiana. So we can see a lot of detail going on the coast of Louisiana in this one, and especially in the Gulf of Mexico. Now, this is going to lead to an inefficient implementation currently in terms of using MPI because of the fact that in these very, very detailed meshes, most of the nodes in the mesh are actually concentrated in the study area, and a large portion of those are above the water. They're actually dry. So the model has to classify every node, every finite element as either dry or wet. There is no in-between state. It's either above the water or below the water. And anything above the water, we don't need to solve those equations on because there's no flow, obviously. So that in and of itself leads to a pretty significant load imbalance because of the way that these meshes are decomposed currently. It's completely uniform. Every subdomain just has roughly the same number of nodes, and they're all of the nodes are weighted pretty much the same. So that means that there are some subdomains which are going to contain many of these nodes that are completely dry. They're not even going to be underwater unless a storm comes through that specific area. So that means that you're waiting on all of the subdomains, for example, out in the ocean or the Gulf of Mexico, where all of the elements are in fact underwater, and we have to solve the equations. So some of the subdomains have a lot of work to do, and many of them have little to no work to do. And we have to wait on all of the ones that have more. So if we were able to decouple our subdomains, well, a subdomain is mapped to a rank, and in MPI, a rank is mapped to a single core. If we decouple the rank to core mapping, as AMPI would allow us to do, we would be able to actually balance that load more effectively. So as a quick example, this is one of our more detailed grids we use in our lab, which contains a lot of elements that are above the waterline. Anything that's this dark green color is not underwater initially in the mesh. And they're around, so this mesh has almost 5.8 million nodes, and around 3.5 million of those are this dark green color. There's so much detail concentrated on those floodplains that's actually most of the nodes are above water. So if we're just using regular old AdCert, for example, on 1,000 cores, and typically actually these things are run with even more than that, sometimes in the like 10,000 core range, then the load imbalance ends up being 157%. So we could be doing this more than 100%, with more than 100% efficiency if we could balance the load. So we considered some strategies for how we could do that, and primarily that just concentrates on over decomposing the land areas more so than the not land areas, the ones that are initially underwater, because at that point we'd be in a much better position to be able to balance this load evenly across all the processors, and to be able to migrate things as they become wet or dry. So for example, if we have this domain on the left split into many different subdomains, we could chop up all of the land portions, the gray ones, into more boxes, so that as those change state, they can move around more, even though one of the big things to consider is that only a few of those in one of our storm surge simulations are ever actually going to change state. For example, wherever the hurricane's going to come through, and all the rest are pretty much just going to stay dry the whole time. So as long as we know that we have the balance loaded initially, and that the subdomains are placed close in memory to the nearby shore regions, for example, we'd be in a much better position to be able to actually do this efficiently. You would just maybe have some small imbalances due to the actual transitions between wet and dry states throughout the course of the run, but it'd still be a lot more efficient than what we're doing now. What would probably be even better is if you know where the hurricane is going to go, which we do when we're doing a hindcast study. We're simulating a past event, which we do relatively often. Then we can focus on just that region of interest where we know that there's going to be transitions between wet and dry, and only over decompose there. Whereas the other outside of the region of interest, the other subdomains are practically equal in size, and they can just be loaded onto that. They can just be load balanced on their own. And so then once we have the region of interest decomposed, it would be very, very easy to migrate those ranks around as the storm evolves in time. The only thing we'd have to worry about here is perhaps some memory overhead costs or communication overhead, because we'd have many subdomains which are nearby one another in physical space and need to communicate with each other that might be relatively far away in memory space. So you can even do that somewhat more efficiently just by allocating one processor as our kind of parking lot for all of the nodes that we want to migrate, which is definitely doable in AMPI as well. So those are our ideas for how we can move forward with applying this. For now, we've just considered how viable all of this is and how much improvement we could get from AMPI just with our current decomposition strategies. And we've still got some pretty decent improvements just from those by looking at some ideal cases. So I'm actually going to show some results of using an AMPI implementation and the performance gains we've got just on this ideal case for now, where it's just a very, very simplified case where we have this kind of beach area in the back and a very idealized channel that smoothly narrows out as we go upstream, and this large kind of bay area where there's a tidal range forced on the open part of the bay at the very bottom of this image that just oscillates the water level by around 1 meter every 12 hours or so. It's around 8 meter depth out here and 2 meters above sea level over here. So there's roughly a transition range halfway through this beach area where the tide is going to come up and down. This idealized case wasn't particularly suited to studying the performance gains on its own, because of the fact that there's a very wide transition of nodes, which are going to vary. So the resolution of this one smooths out as we get to land, but the transitions in our actual meshes are not always so smooth. There's typically a lot of refinement up in the land portion, and then not so much out in the sea, and there's not necessarily a very smooth transition between those. So what we decided to do with this was make an artificially refined mesh, where I've now increased the horizontal resolution on the land part a lot more than out in the ocean part, where on the land we're getting around 6 meter widths, and in the ocean it's around 130 meters. Whereas before, on the other case, it was around 4 times that much on the land. So in this case, we've got over 95% of the mesh starting dry. So this was kind of an extreme version of what we had before in our large-scale finite element meshes for the more realistic cases, just so that we could see very clearly the performance that we could get out from using MPI to do the load balancing. So there's now around 11 times more nodes above the 1 meter mark up on the beach than below, including out in the open ocean area. So ideally, that means that if we're balancing the load right, we should be able to run it around 95% faster than just the regular AdCert with no AMPI load balancing. At first, we were having some trouble with this just simply because of the fact that we were having trouble detecting the load imbalance. It turned out that there were parts in the code that were pretty inefficient, where they were still evaluating our governing equations on the dry nodes, but just zeroing out the solution at the very end. It was going through all of the solver routine, and at the very end, it just tacked a factor of 0 on the front of the right-hand side. And so that meant that the code was actually doing a lot more work than it needed to. The runtime system wasn't really detecting any imbalance because of that. So that called for bringing in some more logic into the code to basically just skip those computations on the dry nodes. And we coded that up so that it would simply just take all of the loops that are currently in the code that loop over every node and every element to solve those equations. And now they're only looping over the active or the currently wet nodes and elements. This is, of course, even going to improve our efficiency even without the load balancing, which we'll observe in just a moment. And we can also observe from the profiling results above, where before we're reducing our, in solving both of the governing equations, remember there are 2 of them, we're reducing our time spent there by almost 100% just by skipping all of those, the 92 to 97% of the nodes which are dry in this mesh. So that was really good to see that, we had to make the code a little bit smarter to be able to actually do the load balancing. But that in and of itself is, an efficiency gain. So now we wanted to ask ourselves the question, now that we know we can detect the load imbalance, that it's actually going to be there, when we do the load balancing, how does that help us? And these are a summary of those results, where we have the runtime in hours versus the number of cores on that overly refined case that I showed you guys. The top line is no AMPI and without the skip dry logic I just mentioned, just regular AMPI AdCert as it existed before this project began. The dashed red line is me putting in the logic I just discussed in the previous slide. So that in and of itself gave efficiency gains, which are shown in the middle column on this table. And then, of course, by applying the MPI load balancing, where we have different levels of virtualization, this is just saying 2 times the number of cores, 4 times, 8 times, 16 times in terms of the number of ranks we're using. we're seeing very high degree of improvement in terms of the efficiency. The maximum relative speed up is even getting very close to that 95% value, that I just mentioned on the last slide. So this is very, very promising to us in the hydrodynamics community to see how much efficiency we're getting from just using AMPI load balancing, even without the decomposition strategies that I mentioned before. And it even only requires just one load balancing step at the very beginning of the run, because this is a really predictable test case with just the tidal range varying every 12 hours or so. So there is a specific set of nodes which are just going to stay dry the entire time. But the one thing we did notice was that as you go down this column, this table, as you go down the rows in this table, you'll notice that the amount of speed up we're getting, the relative speed up is decreasing with the number of cores. Though that was to be expected, not only due to overhead costs in terms of communication, but because of the fact that we hadn't implemented the decomposition strategies that I had just gone over. So if we implement those types of strategies, we're anticipating we're going to see many more entries on this column get closer to that ideal value, because of the fact that as you get more cores, you're more likely to end up more cores and more ranks. You're more likely to end up with more of these subdomains that don't have any dry nodes. There's just one subdomain, maybe that's completely in the ocean area and does not have any transitionings, and that's the one that's slowing you down. Whereas if we just over decompose in the land area and that's it, we can have just a few subdomains out in that open ocean area that are doing all of those work, and then balance appropriately as the state changes. So to tie all of this up, AdCirc currently, as it exists, exhibits significant imbalances for the storm surge model, the versions that all of these agencies are currently running, due to the large number of dry nodes that are typically existing on these meshes used for storm surge due to the MPI implementation. So this calls for our over decomposition strategies and a dynamic load balancing with AMPI. And as we discovered, also calls for making the code a little bit smarter with regard to how it considers computations on the dry elements, so that we don't actually have to do any computations there. So we implemented all of those things and we got the nearly ideal efficiency gains on this idealized case, but we still need to think about implementing our over decomposition strategies and doing that part differently. So that's pretty much our next step for working, although there are still a few other things that we need to iron out first. So for future work, we need to solve some issues with output. Currently, we're not actually able to obtain the solution variables from the AdCirc model with AMPI. There's some bugs in IO that need fixing, but we're getting through those, and we're really just focusing on those performance gains for now. And we also need to move on to make sure that if we do this on a realistic large scale scenario, especially with the skip dry logic that I mentioned, we're not going to corrupt the solution in any kind of way. So we need to study this on a non-idealized domain with storm surge, for example. And then once we confirm that all of that is going to work, then we're going to start implementing these schemes for over decomposition, so that we can not only reduce the initial imbalance in the model, but also facilitate more efficient load balancing. So yeah, that's all of my talk. Thanks you guys for listening, and yeah, welcome any questions.
Thank you, Dylan. Great talk. It's really encouraging to see adaptive MPI giving you a lot of performance benefits. Yeah, so I'll open the floor to any questions you might have for Dylan. Yeah, Phil, please go ahead.
Yeah, so given the ability of AMPI to completely virtualize the subdomains, is there necessarily any reason to not kind of do one very fine over decomposition on the whole the whole mesh once and just always run with that number of virtual processes, and so not try to do it like bespoke in the application, just write a partitioner that takes account of all the things you might consider and run with 2,000 or 5,000 virtual processes and just let the load balancer notice which ones are mostly empty.
Yeah, that's correct. That was a scheme that we've initially considered for testing out on especially those large scale like ocean models like I showed before. The only issue with that is the way that communication currently works in the AdCert model. It creates a halo around each subdomain of ghost nodes that are shared with neighbors. And so as you increase the granularity of the decomposition, you're decreasing the volume to area ratio.
So your communication volume goes way up and your memory footprint goes way up.
Precisely. So that's what we're trying to avoid. We're going to initially try exactly that strategy once we've ironed out the output bugs, I think, and we confirmed that the skip dry logic works on these large scale cases. But we want to be a little bit smarter than that.
Thanks.
Is there a second question?
Yeah, I guess so it's sort of related to that. This is a really interesting talk. We're also doing hydrodynamics, but in the relativistic astrophysics case. And so for us, the over decomposing, you really notice a penalty from the message overhead from that. So I was wondering, sort of a few different questions, and it might be of use both for us to maybe share some more information at another time. But what type of methods are you using, sort of in a little bit more detail, maybe?
Oh yeah, sure thing. I didn't have enough time to go into that specifically, but we're using a continuous Galerkin finite element formulation with, I believe, just finite difference in time. So it's relatively low order approximation. I think just first order, when I think about it. Yeah, it's just first order. So there are other methods out there that are really similar. There's a discontinuous Galerkin model, for example, that does almost exactly the same thing as AdCert and can produce much higher order solutions. And I think in general, in my discipline, things are starting to move in that direction.
Okay, that's interesting. So the sort of thing we've been thinking about a little bit in this direction is, right, the sort of standard proven thing is, so we're using discontinuous Galerkin in space, and then in time just Runge-Kutta or Adams-Bashforth type time stepping, because it's a little bit easier to get truly conservative local time stepping with a multi-step method. But what looks really promising are these aider schemes. I don't know if you've encountered these.
No, yeah, that's new to me. We're typically using the DGRK as well, if we're going to use the DG method.
Yeah, so the idea with aider is you do DG in time as well. And so what this basically means is, rather than solving just a spatial problem, you solve a space-time problem.
That's really interesting.
This drives up the computational cost per cell significantly, because rather than taking, within your RK3, 3 or 4 substeps, you're computing all of that work at once with zero communication. So this is just something to keep in mind, that might be of use. And generally what I've seen in the literature is that the aider schemes scale much better than Runge-Kutta, just because of the reduced communication overhead.
Yeah, that makes a lot of sense. That's actually really interesting. And of course, in a relativistic sense, it makes sense to solve space and time in the same way.
Right, exactly. But yeah, even in non-relativistic applications, this is seems to be a very promising route for driving up the computational cost per communication. And then I guess the other question is, what are you hoping for in terms of your subdomain sizes? I think ours are maybe 6 cubed to 10 cubed are sort of the largest, and this seems to be even a little bit on the small end. And we're solving 60 coupled nonlinear PDEs, each with somewhere around 3,500 terms on the right-hand side. So they're very expensive, and even here, it's not clear this is enough work yet.
Yeah, that's actually another relatively open-ended question, because for now, it hasn't been something that they've even thought about. They just say, okay, we have as many subdomains as cores, and that's how large they're going to be. That just governs the size of them, obviously. So now that we want to have more flexibility with that, I think that's going to just have to be something that we'll need to consider and think about in the future. And I'm not sure that we've really pinned that one down yet.
Okay, no, it'll be really interesting to see what works in your application, because this just seems to be a recurring theme.
Yeah, makes sense. Well, anyway, yeah, that's really interesting, and I might be sure to bring some of that up with my advisor. I'm sure he would love that whole the Aider idea. That seems fascinating.
Yeah, no, like I said, it looks very promising as a way of dealing with increasing, not artificially, but increasing the cost of the solves. So
yeah, that makes sense. Yeah, thanks for sharing.
Okay, thank you, Devin and everyone. Should probably move on to the next talk. Yeah, so I think Eric is going to lead the discussion on the new CharmMPI features.
Hello. Is my screen visible?
Yep, can see there.
All right. So, this is, I'm not actually presenting all of this. I'm just sort of providing the wrapper function. So we are going to be going over the new features in Charm, basically kind of a review of what's in the current master with a focus on the 7.0 release and a few items that are already in there looking towards 7.1. And as we transition through the various contributors for PPL, I'm going to be taking over to talk about the specific features. So overall, we're going to go through the TreeLB, the GPU, some rework of futures, the buffer API, changes to adaptive MPI, the zero copy post async API, and changes to projections, and then a cornucopia of tiny changes at the end. So over to Ronak to discuss TreeLB.
All right, thanks, Eric. So TreeLB, most of you, I assume, have probably heard about before, but the current state of it effectively is that things are effectively done. So TreeLB is sort of the crown on top of the big LB rework that we've done over the past couple of years. This involved changing a lot of the internals of how the LB infrastructure worked. And a lot of that was in pursuit of these research goals we've had for several years, because the way that the framework had gone so far, it made it very difficult to continue in the same lines of research that we wanted. So TreeLB kind of fixes those problems, and it does a couple of things. So in particular, it improves the efficiency of passing LB stats around. So we just do this by doing more compression and passing less data. This leads to faster speeds when it comes to actually running load balancing. So it's a net win for all applications. From a more research-oriented perspective, it allows for really easy customization. So we get better ways of controlling strategy choice, controlling the frequency of load balancing, and the domain. And what I mean by domain is you can balance now very easily over a particular node or a set of nodes, whereas earlier doing such a thing was quite difficult. You can see on the right here, I have an example TreeLB config file. So you can still use LB the same way that you used to in the old system with Charm. All of those things have been brought forward and are backwards compatible. But now under the hood, they'll use TreeLB. And you also now have the option of using TreeLB directly with this config file. So basically, you can pass in this JSON file that lets you select a tree, lets you select different frequencies for different levels of those trees, lets you select particular strategies, as you can see here, lets you set the PE that a root is on, for example, and various other options that we've outlined in more detail in the documentation. The big thing, as I said, this is sort of the bedrock for future LB work, including the vector stuff I presented, meta LB stuff that's been in the works for a while, node-oriented execution, and other things along those lines. And this is sort of the future where we anticipate taking all of load balancing in Charm. As of right now, we still have centralized, we still have distributed, all these things are still exist, but we're slowly adding things like the position API that I talked about, communication graph. So our slow transition to using tree LB for most every LB case in Charm. And this will be coming out in the new 7.0 release.
Jaemin, if you would describe the GPU messaging API.
Yeah. Yeah. So I'll recap this again. There we go. Yeah. So in this case, we have two chars in this example. We have the sender char and the receiver char. So to use the GPU messaging API, which is in current Charm++ release, you want to wrap the data buffer that you want to send that's on the GPU with the CK device buffer construct. And also in the CI file, you need to annotate the parameter that you're sending as a no copy device. And that should be outlined in the documentation that's linked here. So yeah, once you do that, the runtime system will kind of pack the metadata it needs to send, which is sent to the receiver char. And then at the same time, it will also send the sender's GPU buffer. And when the receiver char receives the metadata message, it will invoke a post for the receive of the incoming GPU buffer. And where that destination GPU buffer should be is it should be denoted in this post entry method that's in the middle part of the diagram here. And then the runtime system will the control will go back to the runtime system. And once the GPU data arrives on the receiver, it will finally invoke the regular entry method, which is the bottom diagram here, the bottom box. And at that point, the bar entry method will have access to the data that has been received. Yeah, so that's how you can utilize the API. So it's very similar to the zero copy API. Next slide, please. Yeah, so this kind of recaps the performance that we see from using the APIs. So yeah, if you look at the red lines, which are the zero copy API or the GPU messaging API that we just seen, it performs significantly better than the host staging mechanism where you have to move the data to the host memory first when you're doing GPU implementation. And then there's the channel API, which we haven't discussed here, but yeah, it will be released in the next Charm++ release, version 7.1, where we kind of opt in for a more data-driven communication, and we don't really transfer the control flow from the sender to the receiver. So as you can see, these APIs result in substantial improvements in both latency and bandwidth. Yep, so that's it for my part, I think.
All right, over to Justin to discuss the revision to features. I think you're muted, Justin.
Are you able to hear me?
Yes.
Okay, great. So one of the new additions to the API are typed features. So we can now declare features with a template argument indicating their type. So you can say CK future, open template int close future. And then if you want to set the value of that future, you can just say .set somewhere else. This is compared to the previous C-based API where you had to manually build a message. So I show that here where you may have to allocate one using CK data message, set the data, and then send it off. Next slide. The next feature that we added is the ability to use futures as callbacks. So you can declare a CK callback and pass it a future to initialize it. And this is sometimes better than using CK callback resume thread because you can actually get a value, and its CK callback resume thread can be a little bit buggy in some situations. The next thing is operations on collectives of futures, particularly wait any, wait all, and wait some. So wait any will take the first future in a collective that's available and give you the value back, as long as as well as a pointer to that future in the collection. So here, if you use an STD vector, you can say begin and end to CK wait any, and then you'll get the first one back as the first you'll get the value back as the first argument, and then the iterator within that collective as the second one, so you can take it out and know which one you got the value for. Wait all will wait for all of the futures in a collection, and then wait some will take any ones that are immediately available, and that can be none, just like MPI wait some. All right.
Okay, so this is me. We've implemented this pup buffer API to provide zero copy functionality within pup methods. As it stands, it's basically just good enough for what AMPI and isomalloc need. We got some feedback, thanks Nils, since we introduced this at the last workshop. Basically, standard function is bad. It always heap allocates, and the way we're using this API kind of abuses lambda captures a little bit. So you're free to try this, but be prepared for it to change in the future. Basically, you provide the methods for how to allocate and how to deallocate the buffer. Like for AMPI, for isomalloc, we need to use mmap in a specific place for every buffer. But other than that, it's just a big block of raw data containing the call stack and the globals and the heap. And there is future work by Justin that may supplant this anyway. So this is about as much as we're going to document of this for now.
Yep. For AMPI, we have made a number of advancements since the last release. The probably biggest one is the development of Pi globals as a more fully automated global variable privatization method that has been merged, and instructions on how to use it can be found in the CharmMPI onboarding tutorial that's linked there. We've also added a number of enhancements to improve portability and usability, such as making isomalloc sync the default. And that used to not be the default because it relied on a shared file system to exchange information at startup. Now that's done using converse node level reductions. So it's more efficient and that can therefore be turned on by default. We're also using the pup buffer API, as Evan just mentioned, to do in-place pup migration. That's particularly important for AMPI applications that have large memory footprints. And as always, we're continuing to improve the standard conformance of AMPI to the MPI standard. And lastly, collective algorithm enhancements, as I mentioned in my talk, are a work in progress and should be in 7.1 release.
Okay, so the zero copy post API has been there in the current master of Charm, and it basically allows the user to directly send data from a source buffer to a receiver buffer without the intermediate copies. So in the previous case, the receiver could post the receiver buffer only in the post entry method as shown by Jaemin for the GPU version, but this is the CPU version of it. But with the async feature, we support more asynchronous posting, pretty much like what MPI offers, where you can have the receiver post the buffer either before the post entry method or inside the post entry method or after. And this is done using two corresponding CK post buffer and CK match buffer calls. So as shown in the example, when the sender sends the source buffer wrapped in the CK send buffer call, the metadata message is received on the receiver, and inside the receiver, the user has to specify a CK match buffer call with a particular tag using the no copy post object that is present in the overloaded post entry method. And at any point, either earlier or later or inside the post entry method itself, there should be a corresponding CK post buffer call passing the receiver buffer and a size with the same corresponding tag that was used for the CK match buffer call. So a set of two corresponding match and post calls ensure that we know which metadata corresponds to which of the receiver buffers, and after the second of these two calls are completed, in whichever order the execution happens, the runtime system performs the rget and then the actual entry method is called. So this provides flexible matching and posting of buffers. And so the PE level variants are simply post buffer and match buffer, and the node level variants where you can have posting and matching happening on different PEs of the same node are CK post node buffer and CK match node buffer calls. And this should be a part of CHARM 7.1. That's it for my part.
So we've done a couple of things for projections, which is CHARM's performance tracing tool. The two big pushes we've made is one for performance. So in particular, this is both computational performance and memory usage. So in particular for timeline, we've made really big improvements in both of those things, performance and memory usage. The performance, it's difficult to quantify, but subjectively speaking, we've made it much more responsive. And we've done mostly this by fixing some bugs that we had in the rendering side. For memory, we've made a big reduction in memory usage. By my measurements, it's been about 50% of what it used to be for logs of reasonable size. And this ends up saving a lot of performance because two things. One, we would often hit memory bottlenecks just in terms of heap size and things like that, especially as users run larger and larger jobs on larger machines. But also the garbage collection that would happen in Java started being a big problem for runs with those logs. So reducing memory usage has really improved that. And we've done some things in particular to help not only reduce memory usage, but also try to reduce garbage collection in the JVM. So it's much more usable from a user's perspective. And then separately, in addition to the full projections tracing that most users use, there's also a summary or some detail mode. The point of summary or some detail is that we can trace less data. We do this by bucketing things rather than tracing every single invocation of an entry method or every single communication. We aggregate these into temporal buckets. The trade-off here is that we get less detail, but we get the lower overhead and we get better scalability, especially again for bigger jobs. So one of the issues with this, which has been around for years and years, is that it didn't always work with all the tools that projections had to offer. So you could get a some detail view, but then you could only use it with 2 or 3 of the tools inside projections. So we've made a big push this past summer to increase the compatibility of summary and some detail logs with the other projections tools. Now, almost every tool that projections offers other than timeline is compatible with summary and some detail logs. So this makes it much more useful for the sort of high level first cut profiling or profiling on very big jobs. And it almost brings it up to par with what timeline gives you. So now it's much more usable and users can more reasonably make the choice between getting something that operates fast with low memory requirements and something that operates with much, much more detail in regular projections.
Thanks all. So we've been shifting over to using more and more decentralized tools, particularly the GitHub discussions as the venue for discussions, as the mailing lists had kind of faded in use. So we would direct people to use the GitHub utilities, either the issues or discussions as appropriate. We've switched over to using Simeng as the default. It works for almost all cases. It's stable. We have initial support for the Apple M1 ARM, initial support for the Cray Shasta, and as of 7.1, CharmMPI supports arguments that contain spaces. And CharmRuns now support the +N feature, which makes it a lot easier to configure many runs. There's been performance improvements for high-frequency synchronization, particularly the CMI node barrier and CMI node all barrier. As the BlueJean queues are basically gone, so too our machine learner will be deprecated for that. The common LBs now includes Metis LB. We've integrated OpenPMI X to facilitate portable runs for OFI and UCX. And PUP has added the is checkpoint and is migration functions, so that makes it more flexible for your PUP configurations of those conditions. And last but not least, CharDebug is now a bit more useful that you can flush entire queues when you're inspecting messages, so you can kind of push past various points until you get to where you want to see what's going on. And that is the high-level summary of changes to Charm. We're open to questions you may have on any of those, or anything discussed in this, or anything Charm related. In this current view, I can't see if there are any hands raised.
Somehow the load balancing changes did not make it to the list, but I think also they are slowly getting merged with the new tree stuff, new distributor strategies, and so on. I think what I would like to do is not here, but separate in a separate meeting. Everyone who is interested in load balancers, I know that several of these Astro projects are either doing their own load balancers or looking to see what we can provide, and we will have a separate meeting for that. But any questions on that or anything else Eric said so far?
This looks great. Thanks for all the work and really being receptive to feedback and implementing things. That's really fantastic from a user standpoint. So really thank you a lot for that.
Thank you for the feedback.
Yeah, it's really,
and being patient with us. Thanks, Phil. Yeah, it will be great for similar-minded projects like the VT project and others to figure out what can be shared. That will be great as well.
Yeah, there's definitely many points of potential overlap there.
I guess a question sort of for the projections things. So changes Ronak has made to projections recently have made profiling Spectre much easier, and this is very much welcome. And so we can actually now get good, nice looking traces with projections and understand what's going on. And I was wondering if, well, we have a lot of template parameters, and usually we need, we basically just care about one of these, and these are basically one of the template parameters is basically what effectively tells us what the name of the entry method. Would it be possible to have maybe like an offline database that we could feed into projections or into Charm at runtime, or something that would allow us to remap the Charm internal names to names that we want to be displayed inside projections?
Yeah, it's certainly possible. You can do that right now in a kind of a crude way by just changing the STS file. That's where all the mapping happens.
Okay.
But we could also get a more polished interface of doing that. I'll talk to you offline about what we can do and what exactly would be helpful for you all. But yeah, it's a good idea.
Yeah, that would be great.
Changing STS file would not trace the distinct entry method names, right?
Well, if you're just concerned about displaying them in a particular way, you can change them there if you know what the mapping is between them. And we should generate different entries for different template parameters already. I think there's one bug around that we're trying to fix, but it should in general work. But yeah, in any case, we can do some customization there, and it'll be useful to know in more detail what exactly you're looking for. So I'll talk to you offline, but it's a good idea.
Okay. Yeah,
Along
it's really,
the same lines, I think it will be good to have be able to name, say, converse threads, user level threads in some fashion, so that we can give them names. This is just purely for converse programs, or probably other, to avoid the dummy thread EP thing in Charm that I think we are already on the way to solving, I believe. Threaded entry methods are labeled correctly, but other generic threads. What's the status on that, Rana?
We made some fixes for how those things are traced. So this is particularly for threaded EPs. But there are some other things we can do in terms of labeling that we haven't implemented just yet, but we had some discussions about what to do about things like that, about naming things that right now are auto-generated, but don't give you a good handle of what they actually are. So we can pass in user parameters or strings like that to more accurately describe those things.
And Nils, have you used some detail? Yeah, with a new.
We have not
tool?
used that yet, no.
Yeah, that might be good to get some feedback on as well for largish runs. And there is another thing that I don't know if it's 7.1 includes it, but we are also trying to do some kind of analysis report called perf report, which will basically draw your attention to salient performance issues. It's work in progress in many ways, but it should be now better than it was before. Okay, I guess maybe a good point to stop this discussion. Oh, sorry, go ahead.
I guess, yeah, one detail that I'm not sure on, this might be a red herring, so I won't spend too much time on it. For local entry methods, it wasn't clear to me looking at the generated files that not everything is passed by const reference, and that might produce copy issues in some cases, but this is something that I haven't looked at in detail. So this is sort of a, Ronak, this is sort of in response to, we did the local entry method so that we could trace all of our individual actions, even so we could trace functions that aren't doing communication, but are doing a lot of work. If you remember, we talked about this in one of our calls. So.
Yeah, no, understood. As far as I know, we should be doing the right thing there in terms of, I think, maintaining types that you specify.
Yeah.
But there might be some machine generated code. It's very possible. So if you do find that, we'd be glad to take a look.
Okay, great. Thank you.
All right, I think closing remarks.
Yep. I'm tempted to say closing remarks. I'm done. So, but thank you everyone for sticking around to the end. And next year, we definitely will be doing it in person. I mean, I speak with an optimistic heart, but I think that's reasonable expectation. We have another branch on academic side, Abhinav Batele's group at University of Maryland. I was hoping there would be a presentation, but somehow we missed that. Next year, we will have a good participation from them as well, and we'll have some newer applications, I'm hoping. So, so thanks everyone for coming, and well, this is not the only time we talk. We will continue talking. There is one definite occasion when I hope you will come and join, which is the Birds of a Feather session at Supercomputing. Ours was approved just recently, like a week ago, not approved in the sense of giving its time and so on. And so maybe we'll send a separate email about that, about the time and other details. But please do register and show your presence there. This is remote, so they should be easier, probably wouldn't require you to register or pay for anything. But you showing up and registering for the BAF is considered a support and is a factor in allowing its continuation year on year. So please do come for that 1 hour Birds of a Feather session at Supercomputing. It will be hybrid. That means there'll be some people in person there, and there'll be many others who will be virtual. So once again, thank you very much. And this concludes the workshop. Bye.
Bye, everyone.
Bye.
Good, everyone. Thanks all.
Bye.
Bye. Take care.
Have a good evening.